Okay, I just got the notification that it's getting live streamed.
Right.
Okay, I just got the notification that it's getting live streamed. Yeah, I just got the notification. Great, I found the live stream. Oh, nice. And am I right in thinking that it's Mohit and Alec that have pre-recorded their talks? It's not any of the early speakers. Yeah. Okay.
Uh, do we need actually to allow participants to join, so or they can just log in directly if they have access to the Zoom link, manually accept the join?
I think so. So otherwise, under maybe they're under more, maybe you can allow or disallow waiting room, and if that is enabled. So hello to everyone in the Zoom and on YouTube as well. I think we're going to give it a few more minutes for people to arrive, and then we will start.
All right. Hi, everyone. My name is Mohammed Al Hosseini, and on behalf of my fellow organizer, Anya Rubrick, Andrew Brown, Zhen Wang, and Marcus Rubrick, I would like to welcome you to the fourth edition of the ICCD workshop on closing the loop between vision and language. And as you may know, that this topic has gained a significant growth in the past few years. Closing loop not only between like images and language and tasks like captioning and dialogue, but also more recently has explored growth in other domains like video, point clouds, etc. And we have seen some of the topics, some of the methods in language in inspiring vision, like transformers started earlier in natural language, and then inspired a lot of follow-up works on computer vision. And the opposite also true, like in convolutional neural networks, was earlier proposed in the context of computer vision, later later influenced like some use of convolutions in natural language as well. And today we have a fantastic lineup of speakers that are experts in both computer vision and natural language, will guide us through state-of-the-art advances in this domain. Brian Plummer from Boston University, Lisa Ann Hendricks from DeepMind, Alec Redford from OpenAI, Cordelia Schmidt, INRIA, and Mohit Pansa. We're very lucky to have them today. And we had an exciting event. Thank you very much for joining us today. And we're going to have later a panel discussion where we'll have them joining us. We're going to cover two like exciting challenges. One is on condensed movies. This like challenge focuses on long range understanding of high-level narrative structures in movies. And we're going to have like a session, 40 minutes session that covers this challenge, its definition, and also the winners. We're going to have also another challenge, called value, and it's a benchmark that have a collection of resources in training, evaluation, and analyzing system for understanding both like video and language, and it covers tasks including text-based video retrieval, video question answering, and video captioning. And that will also cover in this session the benchmark details and also the winner talks. After covering, like, we're gonna also have a spotlight presentation poster session for the accepted papers in the workshop. This included two tracks, the archival track, and with that we have 7 accepted papers that are going to be covered. These are the list, and you can also see the links for the papers and the supplementary materials on the workshop website. For the non-archival track, we have 5 like papers. You can also see the details on the workshop website. And to just summarize, this is a picture that shows the exciting day that we have ahead of us. We're going to start by the talks and Brian and Lisa, and followed by the challenge. We're going to have 2, in conclusion, we have like 5 talks and 2 challenges, and we have 2 breaks, one right after the condensed movies challenge and one right after Mohit's talk. And after later on in the day, we'll have a panel discussion that will be moderated by Anya and others. And after that, we'll conclude by the poster spotlight and then the poster session. And without further ado, I would like to introduce our first speaker, Brian Plummer. Brian is an assistant professor at the Department of Computer Science at Boston University, and is a core faculty member in the Artificial Intelligence Research Initiative in the Rafik Hariri Institute of Computing. And he obtained his PhD in the computer vision group in the University of Illinois Urbana-Champaign, where he received a fellowship and an NSF GRB honorable mention. Brian's research includes significant work on vision language understanding, including applications in phrase grounding, multilingual reasoning, detecting manipulated media, and disentangled and structured learning representation. And with that, I would like to welcome you, Brian, to the stage. The stage is yours. Thanks for joining us today.
Great, and thank you for that introduction. I'm gonna try to see if I can share my slides. If you can disable your screen share.
Yeah, of course.
All right, let me get rid of this. Can everyone see my screen okay?
Yep.
Great. All right, so again, thanks for the great introduction, and I'm really excited to be here. And so today I'm mostly going to be going over some of the recent work that we've been doing at Boston University, and it's really getting into, you know, when I think about a lot of the vision language problems that we've been looking at, we've had a lot of really great successes. And, you know, we've seen, you know, great gains in a lot of different tasks, anywhere from, you know, relatively simple tasks, like just being able to match images and sentences, to, you know, more complex, like embodied tasks, or ones that require a lot more reasoning. And but when I go back and I see essentially where we're still having some struggles, one of the things that has really kind of, you know, manifested itself quite a bit for a lot of the applications that I care about, like, you know, trying to deal with personal robotics and things like that. You know, and it can be kind of illustrated in this particular example, right? So if we're just doing the kind of classic, you know, vision language task of just captioning a photo, and we're trying to, let's say, choose between, you know, two phrases, right, that are very similar to each other, right? So in this case, we have, you know, let's say we just, you know, we have to choose between either captioning this as two siblings who are walking across this river, or if it's two boys. And, you know, on one hand, they're very similar to each other, and it's not clear necessarily if these are actually two boys, or, you know, but most people would say that, you know, one of them is more than likely a girl, and so that would not quite be the correct, you know, phrase here. Although, you know, most people would say, you know, I could kind of understand it, and, you know, you got the basic gist of this right. And so, you know, one you know, method that folks have of course been using to try to, let's say, improve this is just to be able to say, okay, you know, instead of focusing on the whole image, let's focus just on a particular region, right? So we can actually, you know, identify the exact, you know, kind of objects that are going to be in the scene, and you can even use, let's say, a phrase grounding method to identify, you know, the exact regions that are relevant to these particular phrases. But, you know, for the most part, the way folks have been using this is that they've just been using this to identify essentially the important regions, but it's not actually telling us if this phrase exists or not. And, you know, and if you had a method that could do this, then you could sit there and say, well, you know, these aren't necessarily two boys. I have really low confidence in this, but two siblings, great. This is a good caption for this image. And, you know, this of course got me thinking a bit more into, you know, this question of what happens in the null case, where a query, you're given a query for some vision language task, and the query itself is not actually possible. And, you know, and kind of this question of whether or not these models will be able to handle this question. And, you know, this, of course, there's, you know, been some early work, you know, relatively early work that's looked at this. And, you know, essentially, you know, what this paper did for this NeurIPS workshop in 2018 was just basically take, let's say, an image and a question for, let's say, visual question answering task, and just, you know, make sure that just the question can't actually be answered by the image. And just seeing, you know, how these models handled this. And this is actually a case where, especially in the case of tasks like vision question answering, where the answers themselves, it's kind of like overfit to the task, right? Because a lot of these models just, you know, take, let's say, the top K most popular answers and just select between them. And so if the answer is not in that distribution, then of course you can't choose that answer. So if you don't actually have a null case in your answers, then it's never actually going to be able to properly answer these questions, more or less, that these are just not possible. This is at least a relatively straightforward case where you'd say, well, the easy thing to do, or at least a straightforward thing, the thing that seems like it's a relatively easy generalization is just to say, well, let's just give it that extra category, or let's just add this as an additional case, and these models should more or less be able to train and handle them if they're a good model for this kind of task. And so, we started out by looking a little bit farther into this and saying, okay, what really happens when we actually do this, where we adapt models to try to support these null cases, support these infeasible queries to see if they can distinguish between them. And, and for this study, we just looked at this task of phrase localization, right? So it's this grounding task that we were looking at before, right? Like on this, early slide, right? So just given a phrase, if we can localize where in the image it is, right? So it's a relatively straightforward task. In this case, we basically look, at a few of the recent methods, and generally speaking, the 2 on the left did much worse than the 3 on the right. And we have, let's say one of them, that's the winner, and we say, okay, great, this seems like it's a good task, or a good model for this grounding task. But then when we just take that step farther and say, okay, well, now let's make this more like detection and not just be able to localize these phrases, but also be able to say if they're actually relevant to the image or not. When we do this, essentially everything kind of flips on its head, right? Now all of a sudden, the 2 methods that did the worst, now they're doing the best. And the 3 methods that were doing really well at the localization task are now doing much worse. And this is kind of a demonstration of how the models have somewhat overfit to a lot of these tasks, and overfit in such a way that if you just make these kind of small tweaks and make the problems a little bit more realistic, that in the end the ranking of all the methods will change significantly. And this is one of the things that we noticed in this area, and we wanted to essentially try to address it, right? And of course, there has been some work that has introduced data sets and even vision language data sets that address this kind of null queries. And a good example is the VisWiz data set, right? So these were, of course, anyone unfamiliar, these, of course, images with questions, and the questions are actually posed by people who have some visual impairments. And so you'd imagine if someone who can't really see, or at least can't see very well, are taking photos, they're going to end up in a lot of photos that might not be possible, or might not actually have the kind of information to be able to answer the question that you want to. But one of the things when I go through this data set and I look at it, a lot of the kind of unsuitable question answer pairs, or image question answer pairs, don't require a lot of the fine grained, like kind of semantic reasoning, right? A lot of these, it's dealing with blurry images, or images that essentially either don't have any content at all, or just at least some of them, it's about whether or not we have the correct content, like the example over here on the right. But for the most part, a lot of these could be answered with essentially just some low level, like image quality kind of question. Okay, anyhow, so because of this, we actually wanted to take a step farther and actually really be able to try to address this answer of, or at least this question of task feasibility. And to do this, of course, we need data. We end up having one of my PhD students, Andrea Burns, work on this in collaboration with some folks at University of Illinois Urbana-Champaign, of course, and another professor at BU, Kate Sanko. And here we were really trying to delve deep into how can we address these null queries, and if we can collect some data that will help us, try to understand and be able to model this kind of task. So if we think about the kind of desired data set qualities, right? So here our goal was to kind of build a good AI assistant that could handle both valid queries and invalid queries. And so of course we wanted to be able to capture a realistic complexity. We wanted it to be a real task. And not only do we want this task to be plausible, but we actually want, let's say, the kind of language that is in this data set to be natural, right? To be real. We don't want to necessarily just rely on building a bunch of templates. We also want this to be a bit interactive with some kind of goal-oriented commands. And this means that, if let's say we have this AI assistant and we want to be able to accomplish something, we don't want to require that the user to be able to give us step-by-step actions, right? Because no one's necessarily going to want to use an AI assistant that's going to do this. So we want to be able to give it, let's say, some high level goal, and then it to be able to essentially complete all the subtasks that are required to accomplish this, or to be able to say that it is not feasible. And of course, we want to have some visually complex environments in this. We wanted to be a rich data set so that we'd be able to learn quite a bit from it. And as we said before, we wanted to represent real use cases. So by this, what we mean is that we wanted to be able to handle when a request isn't possible. And this can be that either the task itself just cannot be done in the setting that was requested in, or it could be that it's simply just ambiguous and we might actually have to query the user again to try to clarify what they actually want. And from this, we said, well, doing this with a lot of natural images, collecting this kind of data would be very challenging, but we can get a realistic version of this data set by essentially using, let's say, either websites or mobile phone applications. Both of these are there's lots of a very wide variety of types and visual environments, and it would give us this opportunity to be able to, let's say, represent an entire space. Like if we wanted to have it be more like a vision language navigation task, right? We'd be able to represent the entire space or at least a large part of the space that we would be able to explore, while still have it be a meaningful task. And so for this, we ended up starting to collect this data set we called Motif. And the first step of this was just to decide which were the applications that we were going to use for this. And for the most part, we just ensured that they came from 10 different categories of mobile phone applications, and ensure that they were very popular applications as well. So we ranked them also by popularity with some minor manual filtering. And then of course the second step was just to collect some of the tasks, some let's say things that people might ask an AI assistant to be able to complete in those applications, and then actually be able to have people demonstrate them. So then our AI model can essentially watch what the person's doing and be able to learn how to accomplish that task, whether or not it's actually finishing this task, or whether it's being able to explore the task enough to ensure that maybe a task isn't feasible or not. And of course, the last step of this is to actually ask, more or less, is this task feasible, or do we need to actually, ask a follow-up question? Because these were, asked of, just random users, and in the end, they might not actually give us, very good initial tasks. And so for this first step, like I said, we filtered out essentially by popularity and category, and we got a good set of applications. And this would give us a nice, rich environment with, at least a variety of the different kinds of tasks that we'd end up being able to support. And then for all these tasks, we just asked users, okay, what are some of the tasks that you might ask an AI system to complete in these applications? So we gave them, one of the applications and asked them to give us a list of these tasks. So we got a whole bunch of them. And then from there, we started collecting these, task demonstration, right? And so we basically take one of these commands. And one of the things to note is that when we took these commands, we didn't necessarily give it just with the application that it came with, because with the application that task came with, we would assume that over time we'd be able to go through all the different individual sub steps until at the end we finish the task, and then we say, okay, yeah, we were able to actually accomplish this, right? But in addition to pairing these commands with the actual application it came from, we also asked, oh, okay, what if we took a different command and paired it with just another application, and just to see if we could also accomplish it in that application as well. And in the end, if we go through all the individual steps, and let's say in this case we go to settings, and it's just there's just no nothing there to be able to accomplish it, then we'd say this task is not feasible, right? And so the kind of key point that we're getting at here is that when we're annotating this data set, we're actually trying to get essentially a dense annotation for all these kinds of actions. We'd at least like to get at least for all the similar sets of applications, whether or not that task is possible, right? Because there can be, even between similar applications, there can be some differences between them, and we'd like to be able to understand essentially when a task is feasible, when it's not, so that we can address this kind of task. And unfortunately, when we went to actually see if we could predict whether or not these tasks were feasible, and we used a relatively simple model, just a multi-layer perceptron with an LSTM, and we tried different sets of features, some that were kind of generic image features, other ones that are more specialized for this task. Despite this kind of care that we ended up taking, we found that there wasn't, that these models ended up not performing very well, right? Just at being able to predict whether or not this task is feasible. And this is somewhat disappointing, because we'd like to be able to say, hey, we at least the models can handle this relatively simple case that seems like it would come up a whole lot in a lot of different applications. But at the same point, this does demonstrate a significant opportunity for us to be able to try to handle these null cases kind of going forward, so that we can actually apply them to these kinds of applications. All right. So from here, okay, we're getting into this idea of this mobile application task. Maybe in the end you're saying, well, I really only care about natural images, and so there is actually a really good opportunity, with some kind of natural image data, or at least natural video data that's on the web, that and that basically has at least loosely correlated image and text pairs, right? Or at least in this case, it would be video text pairs. And specifically, the ones that we were kind of interested in looking at here was these online narrated videos, or the ones that essentially the like how-to 100 million style videos, right? So it's they're instructional videos. They're trying to teach you how to do something. And so we have seen kind of in the past where folks have tried to essentially take these transcriptions and say, okay, so each one of these instructions, it almost by definition has to be related to what is going on in the video, right? Because the whole point of this is to be able to teach someone how to do something in kind of video form. And in this, we're saying, okay, this is what folks have looked at in the past, but can we make these features more discriminative? Can we learn something else, or are there other opportunities for learning here? And one of the things that we notice in this is that when these videos are talking about, let's say, mixing the batter or cutting the bagels, and we're looking at the visual information, there's a whole lot of information that's necessarily not specifically relevant to just these queries. And for the most part, it's actually just very specific regions of the video that are actually the ones that are the most relevant to these queries, right? So like, in the center example here, there's two people, both of them are doing something, but when they're talking about cutting the bagels, it's actually just going to be the person on the right, and essentially just the part of the counter where this cutting action is actually happening. And so we looked at this, and this seemed like a really good opportunity to at least take a little bit step closer to having, let's say, more discriminative features that hopefully then we'd be able to identify things like feasibility in the future. So at least for this kind of second work, our goal here is to let's say be able to spatially localize the kind of interactions in a video, and then see if we can transfer this representation to some downstream tasks. And so this is work that's going to be presented at NeurIPS, and it's done in collaboration with with one of my PhD students and some folks at Adobe. And so when we were looking at this problem and looking at, let's say, some of the challenges that might come up with it, one of them we noticed is that of course, because we're trying to get at spatial localizations, there is no, let's say, known correspondence between the individual regions and the words, right? So of course here we have let's say 3 different objects, and there are, let's say, 3 different regions, but let's say only one of them actually is dealing with, let's say, the interaction going on. So we have to, this is at least one of the challenges that are coming up in this problem. Another one is that whenever we're looking at these narrations, they're actually not exactly aligned with the videos. So what'll happen oftentimes is, let's say, because these are instructional videos, they might, let's say what the action is going to be taken first, and then they might do it afterwards, right? Or, sometimes it'll be kind of vice versa. They might start doing it, and then they'll let's say talk about it in more detail. But kind of regardless, we can't, let's say, say that at any given point, wherever someone says something, they're actually doing that at that point right there. It's probably going to be some points nearby in time, but not exactly at the same time. And of course, some of these, let's say that some of these transcriptions, they might describe multiple actions that they're taking at the same time, right? So there might be essentially a single query that actually corresponds to, let's say, a relatively long video that has many different interactions that are going on. And so when we started looking at what some of the prior work was doing on this, right? What we noticed is that especially when we're getting into using some of these big transformers, a lot of these models, let's say, use a single cross attention layer. And when we started looking a little bit deeper at what the attention, or like how these attention blocks were implemented, for the most part, what we noticed here is that they were using what we would refer to as full attention, right? And one thing that what we noticed here is that when we're looking at, let's say, this full attention block, when we're, there's nothing that forces the model to actually consider both modalities, right? So if for example, you were dealing with, let's say, the language features, and you're trying to update the representation of the language features, if you're doing full attention, i.e. between both the language and the video features, then in theory, it could just say, well, I'm just going to look only at the word features, because maybe the video features, are harder to distinguish between. And so this can actually end up in a case where essentially you're starting to kind of collapse your representations. You're not really doing cross-modal attention in these kind of models. And so to try to fix this, or at least try to address this problem, what we introduced was this contrastive multi-layer multimodal attention block, right? And essentially it has 3 pieces. And the first piece and the last piece are these cross-modal attention blocks. And so to avoid the problem that we were seeing before, so that we can actually separate the cross-modal attention, let's say, from the self-attention, so that we can actually take both pieces into account. is that we were saying, okay, so what if instead of let's say doing full attention, we'll have these cross-modal attention modules. So whenever I'm, let's say, looking at a word, I'm only going to take into account, let's say, the updated, or at least how that the visual features correspond to that word, right? So when I'm looking at the attention block, I'm only going to be looking at these two pieces together. And so in this way, so we can kind of iterate, and we can say, okay, so how do all the video frames, let's say, affect, let's say, what I think about this word, and similarly, how do all the video, how do the videos consider all the individual words that we're looking at, right? So this is a very similar idea that, you know, lots of us have been looking at in a lot of different tasks and a lot of these vision language tasks. And here we're going to apply these essentially to these kind of more transformer style architectures. And what we actually found here is that it's actually best to do two of these blocks, right? So here we're going to iterate between cross-modal attention and self-attention. And you know, for this, as I kind of alluded to earlier, we're going to pre-train on the How-To 100 million data set. That's how we're going to get some initial features, and then we're going to, you know, fine-tune, you know, use these features to fine-tune a model for some downstream task. And you know, one of our main evaluation settings that we used on this was U-Cook to interactions, right? So these are just annotations of essentially where the interaction is going on in some instructional videos. So this is going to be, you know, very similar to the kind of data that we're training on. And you know, as we said, you know, especially compared to let's say some of the prior work, we're getting a really good boost. And this is this is essentially just using one of our cross attention blocks, right? So we can see that you know, going from one cross attention block to two of them actually really gives a good boost. So this is you know, really indicative that having, you know, multiple levels where we can kind of learn this interaction is really important for a lot of these tasks. And you know, last thing I'll note is that, you know, of course, the data set that we were looking at was very similar to the one that we were training on, but this kind of task, this kind of model can generalize to other tasks like the phrase grounding task on Flickr 30K entities. So in this case, it's weakly supervised, so we're only given during training, we only know what phrases belong to an image, but we don't necessarily know where in the image that they appear in. And here we can get, you know, a good boost over some of the related work on this task. So to kind of summarize, so I hope at least that we have a better idea that we do have a need to have more of these robust vision language models, especially ones that can help these null queries. And here I kind of introduced at least a data set that would help us you know, address this task, as well as a new cross attention module that will help us, you know, learn better interactions between vision and language research. And with that, I want to say thanks and ask if there are any questions.
Thank you so much, Brian, for the inspiring talk. Now, I think time for a question. I think we have a question in the chat. Let me read that out. Some methods are utilizing large pre-trained vision language networks such as CLIP for re-ranking of the results. For example, DALL-E will use CLIP to compute if any generated images are actually relevant to the text conditioning and use that to filter out irrelevant generated images that are not related to the text. Could a similar method be used to assess when a question is not relevant to an image, i.e. use CLIP to assess the relevance of question to image?
Sure. So, you know, to this, the short answer is like, you know, of course you could use one of these large transformer models if they're available. There's a whole lot of applications for where this is not possible. So let's say you're in, you know, trying to do some, let's say, on-device inference on your mobile phone. Unless you have a connection to the internet, you're probably not going to run CLIP on your phone, at least not now. You know, maybe sometime in the future. The other thing that I would note is that, you know, CLIP is great, at a high level, right? It's able to capture a lot of information that we wouldn't necessarily think, a priori that it would be able to do. But it's also not trained to do a lot of fine-grained reasoning. And these kind of fine-grained reasoning tasks, it might work for, let's say, some questions. There's a whole lot of different applications for where it's not suited, and it's unlikely to help very much, right? And to give an example, right, if you're trying to decide if, let's say, something is, let's say that the question is, let's say some blind person was, took a photo of, let's say, a shirt, and just said, okay, is this, shirt red or is it maroon? Maybe Clip will be able to distinguish between this, but it sounds like it'd be challenging. And this gets even more detailed when you get into like even more intricate questions that might come up that require like really fine-grained reasoning in the task, or especially ones that require OCR. This happens a lot for the VQA problems specifically, but even for other ones like the phrase detection task, there are a whole lot of phrases that come up where it's really it's really having to distinguish between, let's say, an older person and a teenager, or like a lot of this fine-grained reasoning that Clip was never really designed to do, and it would be hard to at least solve all those problems just using this model. Yeah.
Hi, I have another question. Can you hear me?
Yep.
So I was wondering, I like the first part of your talk was the trying to understand what part the models, which tasks are actually infeasible. So what do you think about what would be the sort of the follow-up? Would the model just say it's infeasible, or say why it's not feasible? And how do you see that? And also, especially given that it's so inaccurate at this point, how much does it help to say something is feasible versus not feasible when you're actually not sure it's infeasible?
So at least for that task itself, there is this kind of ambiguous setting where you might actually ask the user before you actually finish a task. So that of course has some of it, and I will put a caveat that I wasn't 100% sure what your question is, so I'm going to try to respond and hope, but let me know if I don't quite get to it. So yeah, so there is this question where if you're not sure if the task is necessarily feasible or not, you can query the user. We'd like to reduce that quite a bit, but when we think about, let's say, how we can maybe model this a little bit better so that we have fewer let's say fewer false positives that come up, because this is really the challenge with the feasibility problem, is that the number of false positives that come up is really, it's a really high number, right? Because there's a lot of very similar queries that are really hard to distinguish between, and the models just can't really do that very well. But one of the things that we notice is that for a lot of these problems and a lot of these tasks, it's not that it doesn't necessarily ever identify the correct query. It's just that the difference between the correct and the incorrect one is really small, or something that's feasible or infeasible. The difference might be really, really small. So finding a single threshold is a little bit hard. But if you go but if you can, let's say, organize the data such that you can identify, let's say, mutually exclusive things, right? So saying, more or less like this can be let's say the settings or the profile button, but not both, right? So if you're trying to distinguish between these two, you have to choose between one or the other. And when you do, and if you train a model to be able to do this kind of fine-grained reasoning, you're able to, at least some of the initial experiments that some of my students have done has shown that you're able to distinguish between these a little bit better. So this is at least one way we can kind of get there, but the problem is really reducing the false positive rate is a really hard problem.
Yeah, makes sense. Yeah, I think it looks also a very hard task because you have all the different steps in this navigation. I love those slides where you showed where you have to navigate through multiple steps and up. That seems really hard.
Yeah. I think on average there was 14 steps to the average task before, or at least that's how many steps that people were doing. And we might be able to optimize that to be a little bit fewer. But it is a really challenging problem. And if you imagine that if the feasibility F1 score is only 37, if we're actually trying to look at what the accuracy of actually completing the task itself, it's also pretty low. So it is a really hard problem, or at least the data set we collected does represent a really hard problem that hopefully is good to continue working on. Yeah, thanks.
Okay, great, thank you.
Thanks a lot, Brian. Let me see if there are more questions.
Okay, well, thank you very much, Brian. That was a great talk. Our next keynote is Lisa Ann Hendricks. So Lisa is a research scientist on the language team at DeepMind. She received her PhD from Berkeley in May 2019 and a Bachelor of Science in Electrical Engineering from Rice University in 2013. Her research focuses on the intersection of language and vision. She's been awarded an NDSEG Fellowship, a UC Berkeley Chancellor's Fellowship, a Huawei Fellowship, and an Adobe Fellowship. She's particularly interested in analyzing why models work, explainability, and mitigating and measuring bias in AI models. Thank you very much, Lisa, for talking at the workshop. We're super excited, and over to you. I think you might be muted, Lisa.
I'm seeing a thing that says when I share my screen, I can no longer share my audio, which seems problematic. So let me try.
Sometimes when you click share screen on Zoom, there's a share sound tick box in the bottom corner. Have you seen that?
Aha, yes, there we go. All right.
Great.
Can you see things and also hear me?
Yep.
All right, excellent. Okay. So one of my least favorite things about presenting virtually is that I will not be able to see anybody while I present. So I guess if there's anything you need to stop me for, just feel free to interrupt and yeah, make some noise. All right. Okay, yeah, so thank you for the introduction. So I'm Lisa, and today I'm going to be talking about digging deeper into multimodal transformers. And to start the discussion on multimodal transformers, I want to share some motivation from the language only in the NLP community. So in the NLP community, what we found is that we can pre-train language only models, and then we can use these language only models, these pre-trained representations, for a lot of downstream tasks. And the way we pre-train these language only models is we have a data set, so curated text from the web or Wikipedia. We have a model, transformers are sort of the exciting model of the day, and a pretty simple objective like predict the next word in a sentence. And we can use that to train pre-trained representations that we can then use to start off, we can then use to fine tune and then do well on a large variety of downstream NLP tasks. And the performance gain that we've seen in the NLP community is due both to architecture as well as innovations, as well as having access to larger data. All right, so I'm in a multimodal workshop, so I probably don't need to explain to people why multimodal learning is interesting, but just in case, so multimodal pre-training, the ability to ground language to vision, is useful across a range of tasks, so things like visual question answering and applications, so things like generating descriptions for the visually impaired. Also, if we pre-train, if we have multimodal representations that we've learned, there's some evidence that these can help us with vision-only tasks and language-only tasks as well. So it's not just about our multimodal applications, but other applications as well. All right, so we've seen that in the language-only community, we can pre-train models on language data, and then we can use these pre-trained representations and use them for a lot of downstream tasks. And one natural question is, well, can we do this in the multimodal domain as well? So let's think through what we need to pre-train a language-only model and how that might change when we go into the multimodal domain. So first, our data set. So in language-only modeling, in language-only pre-training, we can just take a curated data set from the web or Wikipedia, and we can use that to train our model. In a multimodal domain, we need to have pairs of image and text. So for example, here I have image text pair from the conceptual captions dataset. You can see this image and then a sentence which describes this image. In the language-only domain, we'll have models like BERT in the GPT-3 style models, and these tend to be transformer models. In the multimodal domain, we have additional design choices we can make. So for example, how do our two modalities attend to each other, and how do we want to pre-process our images? Finally, in the language-only space, we'll have losses that are basically just predict the next word in a sentence. Again, in the multimodal domain, we have additional design decisions we can make. So for example, we can have loss functions that are specific to the image modality, as well as loss functions that are specific to image text pairs. All right. So I guess 2 years ago at this point, people started working with these multimodal transformer models, which were taking the transformer style models like BERT that worked well in the language only space and transferring them to the multimodal space. And here's sort of a high level version view of what a multimodal transformer model looks like. And I'll walk through it just to make sure we're all on the same page. So in a multimodal transformer, we'll take an image and a text pair. We'll take our sentence and we'll tokenize our sentence or break it into words. And we'll take our image and we'll also break our image into visual words. And the way that we're going to get visual words is we're going to take a detector and we're going to extract bounding boxes from our images, and those will be our visual words. We'll take our visual words and our text, and we'll feed this into a multimodal transformer. I'll go into some of the details about the multimodal transformer architecture later on, but for now, it's just think about it as a model where the image and the language modalities, they can attend to each other and they can update their representations. We feed this through our model, and we train our model with 3 different losses. We'll have a language modeling loss. So this is something that we adopt from the NLP models like BERT, and this tries to predict what the value of a masked input language token is. We'll have an analogous image modeling loss where we'll try to predict, we'll mask out a region in our image and we'll try and predict what that masked out region is. And finally, we'll have an image language matching loss. And for the most part, the image language matching loss we use is a pretty simple loss. It's just a classification loss. So we'll take an image and a sentence pair, and if the image and sentence pair match, we give a label of 1, and if the image and the sentence do not match, we give a label of 0. All right. So if you look on the right-hand side of this model figure, you'll see that what we have is something that looks a lot like BERT, which is something that we know worked really well in the NLP community. All right, so multimodal transformers, they seem like they'll potentially be really useful because they're kind of an extension of this thing that worked in the language-only domain. And practically, we saw that that is what happened. So BERT was proposed in a NAACL 2019 paper. It was archived in 2018. And pretty much right after this was put into the world, we started seeing models like VideoBERT and LexMERT and VilBERT and CBT and Uniter and all of these multimodal transformer models. And they all achieved really promising results on a large variety of language and vision tasks. And in particular, all of these multimodal transformer models share the same general backbone. So they all look like that model that I showed on the previous slide, but there are slight differences in loss design and pre-processing. And so given this, me and my colleagues really wanted to understand what exactly contributed to these model success. So we know that multimodal transformers learn representations that are really helpful for lots of downstream tasks, but it's not clear exactly what they learn and what it is about the models that help these multimodal representations be so good. All right, so with that, I'm going to talk about this work, decoupling the role of data, attention, and losses in multimodal transformers, which was accepted to tackle this year, and we presented it at ACL 2021. All right. So in particular, I'm going to think about 4 questions. So first, are the results that we see in our multimodal transformer models, are those really due to a better architecture? Or is it just because we're training on really large image text data sets? Next, I want to think about what makes a good pre-training data set, if the crosstalk between the modalities via attention is important, and how the adopted losses from the language and from language models work for our multimodal transformer models. All right, to do this, I'm gonna, in our paper, we looked at 2 tasks. We looked at image retrieval and visual question answering. So in image retrieval, you have a sentence like gray-haired man in black and yellow tie, and you have to find the image that matches the sentence best. In visual question answering, you have a question like who is wearing glasses, and you have to be able to answer that question. In this talk and also in the paper, I mainly focus on zero-shot image retrieval tasks because it directly evaluates the goodness of pre-trained representations. Representation quality after fine-tuning can depend on things like experimental setup and the size of your fine-tuning data set. So if you really want to understand what's learned during your pre-training step, we focused on the zero-shot image retrieval tasks for that. So in the paper, we have results on image retrieval on Flickr and MS Coco, image retrieval when we add in a fine-tuning step, as well as VQA. But in this talk, I'm mainly going to be focusing on our results that look at zero-shot image retrieval. All right, so for this first question, are the results that we see due to advances in architecture or large pre-training data sets? To answer this, I'm going to take a multimodal transformer model on the left and train on this large image text data set called conceptual captions. And I'm also going to train a simpler baseline model called the dual encoder model on the exact same data set. And the dual encoder model works in the following way. I'll take an image and I'll encode it into an image embedding space. I'll take a sentence and I'll encode it into a sentence embedding space. And then I'll have an image language matching loss that tries to get those representations to match if the image and text match. And the reason why we were interested in looking at this particular architecture is that prior work had shown that it had worked well for retrieval tasks. In particular, here I'm citing a CVPR 2020 paper that was using a very similar model for video text learning. So what did we see? Well, what we saw is that the results when we trained on our multimodal transformer model were a lot better than the results on our dual encoder model. So even though we have the same data set and all this, we fixed all of this, the results with the multimodal transformer model are a lot better. And popping out and looking at the other kind of work that's been happening in our community, we see it sort of a similar trend. So what I have here is I have different models plotted with performance on Flickr retrieval on the y-axis and the number of images on the x-axis. And I'm looking at two different kinds of models. So in the blue, I have multimodal transformer models, and in the yellow, I have dual encoder models. And if we look down at the bottom left corner, we have the MMT model from our work and a dual encoder model, and you can see that when we're training with the same number of images, the multimodal transformer model is doing better than the dual encoder model. All right, so if we look at some of the other work that's happened in the community, I have clip and align plotted here as well, and you guys have probably heard of clip and align. They're dual encoder models which were trained with lots and lots of data. And what we see is that they do really well on the Flickr retrieval task, but if you compare Uniter and clip, Uniter is a multimodal transformer model that's trained on a lot less data, but it's getting very similar performance to clip. So this leads us to think that the dual encoder models can be really powerful, but perhaps they're not as sample efficient. And really, this multimodal transformer architecture is really very powerful and helps us get really good results. All right, so are the results we see due to advances in architecture, or is it just that we're training on larger data? And at least in the case of multimodal transformers, the architecture is really helping. All right. Next, I want to talk about what makes a good pre-training data set. And to do that, I'm going to train my multimodal transformer model on a few different data sets. So first, we're going to use language and vision stable, the MS Coco data set. So this is pairs of images and sentences. We'll also look at the MS Coco and Open Image Narratives data sets. So here we have images, and people were asked to give summaries or narratives around the images. So the text annotations tend to be longer and more in-depth than the kinds of things you see in MS Coco. And I'll also look at visual genome. And in visual genome, we have sort of noun phrases that are linked to different parts of the image. So for example, we have small round yellow frisbee, and we have a bounding box for where that small round yellow frisbee is. All of these data sets are manually annotated, which means that a person went and actually annotated what was in the image. So we expect that they're going to be fairly clean in terms of image text correspondence. We expect when people mention things, they're actually going to be in the image. This is in contrast to data sets like conceptual captions. So conceptual captions is a data set that was automatically curated from the web with a bit of post-processing to make sure that things sort of corresponded. And data sets like SVU captions. So SVU captions is a data set that's automatically curated from Flickr. And these data sets are from the wild in that they're not manually annotated, and sometimes that means that the captions will mention things that aren't actually visible in the image. Okay, so how does our model do when we train with all of these different data sets? So on the y-axis, I have my retrieval results, and on the x-axis, I have my data sets. And here I've organized my data set in order of how many images are in the data set. And the first thing that we can see is that the performance is not directly correlated with the number of images. There are some data sets that are better for pre-training that have fewer images than other data sets. And one particular interesting place to look is the MS Coco narratives, MS Coco, and visual genome data sets. So all three of these data sets have a similar number of images, but they're getting very different performance. And in particular, if we look at MS Coco narratives and MS Coco, these have the exact same images, but they have different text. So this led us to hypothesize that maybe the language similarity between your pre-training task and your downstream task could explain the performance difference. And we ran a little experiment where we tested this out. So we trained language models on the MS COCO narratives, and visual genome data sets. So these language models were language only. So we just looked at the language from the data set, not the images. And then we tested to see if what the perplexity was on the language in the Flickr data set. And indeed, we saw that this could explain the results. So not only should we be thinking about data set size, but the language similarity between your pre-training task and your downstream task can also influence your performance. Okay, another interesting pair of images to look at is the OI narratives and the SBU datasets. So here, SBU is larger than open images, but it has worse performance. And if you think back to that slide I showed where I was presenting the different datasets, you'll remember that the SBU dataset is a dataset which is automatically curated. And so, so it's not manually annotated. So we thought that perhaps the SBU dataset was noisier and that the images don't always match the text perfectly, and this could lead to this discrepancy. And indeed, we ran a little experiment where we looked at the objects that were detected in open OI narratives and the objects that were detected in SBU and compared this to their captions. And we did see that the SBU dataset appeared to be a bit noisier than the open image narratives dataset. All right, so what does all this mean? Well, when thinking about what makes a good pre-training dataset, things like the level of noise and the language that's in your pre-training dataset matter. All right, next I want to think about if the crosstalk between the modalities via attention is important. So if we go back and think back a few slides, I had that sort of cartoon of image of what a multimodal transformer looked like, and I just had that big block that said multimodal transformer. Now we'll dig into what the attention mechanism within that transformer actually looks like. And perhaps the simplest kind of attention that you can have is something that we call modality-specific attention. And here, your two modalities don't actually attend to each other. There's no crosstalk between them. So the vision modality can attend to other vision inputs, and the language modality can attend to other language inputs, but there's no crosstalk between the vision and the language. A more complex form of attention is what we call asymmetric attention. And here, only one modality, for example, language, can attend to another modality, in this case, the image. And one thing I want to point out about the asymmetric attention is that this is sort of similar in spirit to the kinds of things we were doing before the MMTs. So if you go look back at the older literature in the language and vision community, so attention mechanisms like those introduced in the Show, Attend, and Tell paper, there one modality was getting updated by an attention mechanism and the other modality was not. So clearly the way that we implement attention and these sorts of things are different because we have a transformer model, but I just want to point out that this asymmetric attention is sort of similar in spirit to what we were doing before we had the multimodal transformers and our multimodal attention. All right, next level of add another level of complexity to our attention mechanism, and we have co-attention. So in co-attention, each modality attends only to the other modality. So you can think about this as two asymmetric attentions, and this is a popular attention mechanism. So I think Vilbert and Lexmer both use what we would call a co-attention mechanism. And finally, there's merged attention. And in merged attention, each modality can attend to both modalities. So sort of everything can attend to everything. This is the kind of attention that they use in the Uniter paper. And you'll hear it in the literature, you'll hear people refer to this sometimes as single stream attention. I'll refer to both co-attention and merged attention as multimodal attention. So multimodal attention, to me, in this talk, just means that both modalities get to attend to the other modality. All right, so let's see how these different attention mechanisms impact our results. So if we compare our merged and our co-attention, we see that co-attention is slightly better than merged attention, but it's not that much better. And in particular, when we compare our merged and co-attention, merged attention and co-attention to our asymmetric and modality-specific attention, it's clear that both merged attention and co-attention, so both of these multimodal attention mechanisms, are much better than the asymmetric and modality-specific attention. And at least for me, this was actually a bit surprising. When I ran these experiments, I had expected the asymmetric attention to be worse than the multimodal attention, but not this much worse. All right, so we sort of see these three groupings of attention. So our multimodal attention is doing better than our asymmetric attention, and having some kind of attention where the modalities can attend to each other is better than no attention whatsoever between the two modalities. So you might think, well, maybe this is just because your more complex attention mechanisms have more parameters. So in our experiments, we compared when all of the attention mechanisms had six 6 layers, and 12 attention heads. But what we found is if we compared to a co-attention model with 1 multimodal layer or a co-attention model with 6 attention heads, our co-attention model was still doing a lot better than our asymmetric and our modality-specific attention mechanisms. So really what this is telling us is that these attention mechanisms are not particularly strong, and it's not just about the depth and number of parameters. So it's not just throwing a lot of parameters at these models. The form of the attention actually really matters. All right, so is the crosstalk between modalities via attention important? Yes, we found that in particular, this multimodal attention, where both modalities can attend to each other, is really important in the performance of these models. Okay, so finally, are the adopted losses from language models good enough? So one thing we were really curious about understanding is whether or not all of the losses were needed. So going back to that cartoon version of the multimodal transformer, remember we have 3 losses: an image modeling loss, an image language matching loss, and a language modeling loss. And what we found is that if we took away the language modeling loss, it was pretty hard to get good results on our Flickr task. So here we have numbers at around 20.2. However, if we made sure we had the right hyperparameters, we could get rid of the image modeling loss. So here we got results of 41.1, and that's sort of on par with the kind of results we saw when we're training with all 3 losses. So basically, this image modeling loss doesn't really seem like it's doing that much. Another thing we were really interested in looking at was a contrastive formulation of the image and text matching loss. So we were interested in thinking about this because contrastive losses have been really helpful in the unsupervised learning world. So very brief overview of how a contrastive loss works. You'll have one positive pair and then many negative pairs, and you want to train your model to give a higher score to the positive pair than all the other negative pairs. So it's a pretty simple loss, and it can really improve your results in some cases. So here I have a modality-specific, a model that's trained with a modality-specific attention mechanism, so a simple attention mechanism, and I have a classification loss versus a contrastive loss. And indeed, we see that the numbers go up on our zero-shot Flickr retrieval. However, if we do the same thing, except we have a multimodal transformer instead, we see that the contrastive loss doesn't really help us that much. So what this tells us is that the contrastive loss can help for simpler models, so when we have our modality-specific attention, but not for more complex models. And you'll note here that the multimodal transformer I'm using only has 1 layer, and the reason why is these contrastive losses take a lot of memory. So not only is it not really helping us that much, it's also a lot harder to train. So the classification loss, to me, surprisingly, since it's a very simple loss, actually works quite well. All right. So are the adopted losses from language models good enough? Well, in particular, we found that perhaps a little bit more thought needs to go into how we build our image modeling losses. All right, so some takeaways. Blindly training on more data is not always better. The dataset noisiness and language similarity to the task are important factors. Additionally, performance is not just due to depth of a model, but many layers of multimodal interaction. And finally, contrastive losses, which have been important in the world of unsupervised and self-supervised learning, are less important for multimodal transformers than they are for other image text models. All right, so some discussion points. The zero-shot task that we are looking at doesn't really allow us to explore specific failure modes. In particular, it's not really clear why what it is about one model, what it is that one model is capturing that another model isn't capturing if we do well on the Flickr zero-shot task. So we feel like there's a need to have better controlled and larger zero-shot tasks. Additionally, in this work, we treated all of our image text data sets with different degrees of noise similarly. And it seems that if you know something about the noise in your data set, you might be able to build a better model. And this perhaps relates to the prior talk where Brian was talking about the work he had done with how-to. And finally, adopting losses from language models is not ideal. The image modeling loss doesn't seem to contribute to the results, so it feels like we can do something better there. In the last remaining minutes of my talk, I want to focus on this first discussion point about how we can build better tasks for probing whether or not our models have a good understanding understanding of different kinds of concepts after pre-training. And to do that, I'm going to talk through this paper, Probing Image Language Transformers for Verb Understanding, that I had with my colleague Ida in the findings of ACL 2021. All right. So I've been talking about this image retrieval task for throughout this talk, and I want to think a little bit more about what this image retrieval task actually tests. So in image retrieval, we'll have a sentence like "person is riding a horse," and the goal is to find which image matches the sentence best. So we expect a good model to understand that the image on the right matches the sentence best and the image on the left does not. However, if you think about it a little bit more closely, you'll realize that this doesn't really require fine-grained multimodal understanding. If the model understands what a horse is, it'll be able to understand that the sentence matches this image best without really having an understanding of what it means for a person to be riding a horse. So instead, we proposed a new data set called SVO probes, where we try to get at this fine-grained understanding a little bit better. So we'll take a sentence like a person is riding a horse, and going back to our grade school grammar or learning about English grammar, we can break this sentence into a subject, a verb, and an object. And what we did is we tried to find example images that had the same subject and verb, but a different object, or the same subject and object, but a different verb. So for example, we might take this image, which includes a horse and a person, but the verb that relates the horse and the person is different. And what we want to do is we want to make sure that our multimodal transformer models can accurately predict whether or not the image on the left matches the sentence and the image on the right does not match the sentence. And of course, we can have examples where we change where the subject is the thing that is different between the two images. So here we have an animal lays in the grass, and examples where the object is the thing that's different between the two images. So here we have a woman running on the beach versus running on in the forest. All right, so to evaluate on our data set, what we're going to do is we're going to use our multimodal transformer model, and we're just going to use the pre-trained model. We're not going to do any fine tuning, and we're going to look at the score from our image language matching loss. And there's two things that I'm going to think about. So first, what kinds of examples do our multimodal transformers struggle with? And second, do models which perform best on image retrieval perform best on SVO probes? All right, so let's look at the performance on our SVO probes data set. So 50% is chance. And if we look at examples where we're probing for the verb, our accuracy is 60%. So it's above chance, but not great. And in particular, if we compare this to examples where the subject is the negative, our results are much higher for the subject example. So it's a lot easier for our models to differentiate between subjects than it is for verbs. And if we look at objects, we see that our model performance goes up even more. So it's easier for our models to differentiate between objects than it is for subjects or verbs. If you look at the average accuracy across all subjects, verbs, and objects, you see that it's hovering around 65%. So there's a lot of room for improvement. Okay, so here we're seeing that verbs seem to be harder for our model to differentiate between than subjects and objects. And we wanted to make sure that this wasn't just due to something in our training. So for example, were verbs seen less frequently in training or something like that. So we controlled for a lot of things, so including frequency, word embedding similarities, similarity to pre-training examples. And what we saw consistently is that verbs are harder than nouns when you control for all of these different things. All right, so what kinds of examples do MMT struggle with? We found that our models really struggle with fine-grained verb understanding. All right, so the models which perform best on image retrieval perform best on SVO probes. So here I have a plot where on the y-axis, I have performance on my SVO probe data set, and on my x-axis, I have my performance on Flickr, and I have my MMT model plotted there on the right. We can look at models which have weaker attention mechanisms. So here I have my modality-specific attention, and I'm comparing to my asymmetric attention. And one thing that's interesting here is that the models that we're doing look substantially worse on Flickr are actually doing okay on the SVO probe data set. Additionally, I can look at examples where I have where I take away my image modeling loss and my language modeling loss. And again, something interesting happens where my model that does not have the image modeling loss, even though it was doing about the same on Flickr as my MMT model, it's actually outperforming the MMT model on the SVO probe data set. One thing that's interesting is that the models that are doing surprisingly well are the models that have weaker image modeling. So these models are doing better on SVO probes than we would expect them to do. And we wonder if part of this just has to do with having poor image modeling in the transformers, so that when we have the weaker, basically poor image modeling in the transformers in general. All right, so I think the big point to take away from this plot, though, is that just because you do well on Flickr, it doesn't mean you'll have the exact same performance on other kinds of probing data sets. And having different kinds of probing data sets can give us different kinds of insights on where our models are succeeding and failing. All right, so the models which perform best on image retrieval perform best on SVO probes, and we found no. So there's value in having these additional probing data sets to really understand where our models are succeeding and failing. Okay, so the takeaways from this work. MMTs struggle to differentiate verbs, and we think that this might make them a really good test bed for measuring multimodal understanding. So a lot of times in language and vision, we think a lot about objects, but verbs are also really important. Having a good understanding of verbs seems to be something that our transformers are struggling with. Additionally, our retrieval results don't directly correlate with SVO probes, and we believe this illustrates the need for having controlled data sets to better understand model weaknesses. So when we collect new data sets for probing, we'll probably see different kinds of things, and we would be able to see if we just looked at Flickr. All right, so to finish off my talk, I want to just bring up some questions that I think are particularly interesting. So first, how can we make better use of our data sets? So right now, we'll take data sets like conceptual captions and we'll pre-train our multimodal transformers, and we'll do the exact same thing with and we'll treat the conceptual captions data set the exact same way that we treat our COCO data set, even though we know certain things about our conceptual caption data set, like we expect it to be a little bit noisier. And it seems like if we know these things about our data set, we should take that into account when we train our models. Additionally, different data sets have different kinds of annotations, and we're not really taking advantage of that when we are training all of our models. Second, it's not clear what the right losses are for multimodal transformer models. So the language modeling loss seems to be really helpful in the multimodal transformer models, but it seems like we can do better in terms of image modeling losses. And finally, I think it's interesting to think through what the ingredients are to have improved verb learning in our models. So I think every single year when we're at conferences like ICCV and CVPR, we see all of these great new data sets that are being proposed. And I think a lot of times we think that we need to make our tasks more complex to see where our models start to fail. But really, there are some very simple things that our models aren't great at still. And it's interesting to figure out exactly why that is and what that means about the architectures that we have and the data that we're training them on. All right, so with that, I will take any questions, and thank you very much for listening.
Great. Thank you very much, Lisa, for that great talk. Yeah, really, really good. I think on a personal level, that first paper that you talked about was so filled with intuitions. It was a great read, I found. So a reminder to everyone in the Zoom, if they have any questions, to ask them in the chat, and we can convey those to Lisa as well. I had a question to get us started. So, sorry, Anya. So I think there were a couple slides when you noticed the sort of data set discrepancy, the discrepancy between training on different data sets. And also there's these results that the dual encoders do far better having trained on far more data. I'm wondering to what extent test data set leakage into these really large data sets is somewhat accountable for that. I'm wondering that in these massive data sets, if there is some leakage, then that could explain this discrepancy. I'm wondering if you thought about that in this analysis.
Yeah, so for our analysis on the data sets, we did do like sort of a rudimentary thing to try and cut out examples that appeared in MS COCO and Flickr. So what we did is we looked at URLs, and we tried to make sure that we didn't have any URLs that matched in like in the conceptual captions data set. There wasn't a URL that matched a URL in the data sets for evaluation, so the Flickr and the MS COCO data set. So we did do a little bit of rudimentary experimentation there. I think it would be good to sort of make sure, like do something a little bit more sophisticated than what we did. So I do think it's a concern. I feel like it's probably a bit more of a concern when you get up to like the CLIP level and align level models, because they're like those data sets are massive. So I was showing things on a log scale, there, I think you might need to be a little bit more careful. But at least for the results that we showed, we did at least a little bit of rudimentary checks to make sure that we weren't training on our test sets.
Yeah, great. Really interesting. It seems like a big problem with those large data sets, maybe. Right. Anya, did you have a question, or we can move to one in the chat as well?
Sure. Let me jump in. Hi, Lisa. Very nice talk. So I guess when you talked about the last portion about the issues with the verb learning, like, recognizing verbs, I was wondering, so these experiments are all with images, not with video, right? So I was wondering, so it's like a question and a comment at the same time. One may think, one may posit that perhaps if we look into these video and language models, they don't have these issues. So I'm wondering if you looked into it, and like some of our experiences are that the issues kind of still remain, basically. If you want to come up with the difficult case, you can easily come up with it. But like, I'm curious what your experience was.
Yeah, so the reason why we were looking specifically at images is just because we had this model that is working so well on image tasks, and we sort of wanted to understand what was going on there. I think looking at videos is really interesting. In particular, so yeah, so at least in our data set, we did have a human annotation step to make sure that humans could actually differentiate between the verbs. And some of them are like jogging versus lying. You can tell from an image. I do think understanding verbs in the context of video is interesting. And in particular, one thing I'm really curious about is if we could find like particular verbs that are easier to understand from video versus verbs where we don't actually need the video context. Like that would be something I'd be really curious to see, like where exactly does video help us? Or does it help across all different verbs? Or are there some verbs where it actually isn't that helpful? And getting a good feel for why that might be would be super interesting, I think.
Thank you.
Yeah, really interesting. I think there might be a paper examining the verbs in the kinetics data set and which could be classified correctly just looking at one frame. That getting to that. So we have one question from the audience actually. So this member asks, do you think the same observations would hold that you made in this talk if we test zero-shot transfer to other vision and language tasks, for example, VQA and referring expressions?
Yeah, so when we were doing this, doing all the experimentation, like, so I explained in the talk why we were interested in this zero-shot setting, because we really wanted to make sure we were looking at the pre-trained representations and not confounding with other fine-tuning. And at the time, we didn't know that there wasn't really a great way for us to think about how to cast like VQA as sort of a zero-shot task. So right now, it's not clear how you would just repurpose your multimodal transformer to the zero-shot task in a way without doing any kind of fine-tuning, or at least it wasn't clear to us when we were writing the paper. Maybe with referring expressions, you could actually get at that. So that so that's the main reason why we didn't do that, is that we had to do a little bit too much. There wasn't really an obvious good way to do that, but I do think that would be interesting. And in particular, one thing that we didn't do that I would have been eager to do is to play around a little bit with like how much. So with VQA, I think you have, on the order of tens of thousands, maybe 100,000 images, if I'm remembering my numbers correctly. So you actually have quite a lot of fine-tuning data, and I'd be curious to maybe play around with having less fine-tuning data. I'm not sure if somebody has done that and sort of examined the differences, but that would be something interesting that's not quite zero-shot, but maybe gets at some of the same things.
Great. A question from Mohammed, I think.
Hi, Lisa. Very nice talk. It's sometimes hard to define what zero shot is when we have an open vocabulary, right? And some zero shot could be harder than others. And for example, is it a zero shot when the combination is unseen? Is it when two pieces are unseen? Is it when the verb only is unseen, or the verb and the subject are unseen? What are your thoughts about that, and how did you approach that in your benchmarks or evaluations?
So I guess I should say that we're sort of the term zero shot. I feel like people sort of use it for different purposes. And when we said zero shot image retrieval, it's just they basically were using data that was not our trained data. We were using an evaluation set. I think the kind of zero shot learning that's the more traditional zero shot learning, where you have a new object or a new combination of objects, is like also very interesting. And I guess like in terms of all of these different forms of zero shot learning, I feel like zero shot evaluations and zero shot learning, I kind of think that they all have a place. So that's kind of maybe an unsatisfactory answer. The final thing that I wanted to know is that with our SVO probes data set, the reason why we actually collected a new data, or one of the reasons why we collected a new data set as opposed to going out and looking at a pre-existing data set, is we wanted to test the understanding when we knew that our model had seen things at train time. So basically the idea was that, well, let's see if we know that our model has seen examples of person writing for us at train time. At test time, can they actually recognize this? And if they can, then the thought was that, well, we'll go on and we'll try and do something that's like a zero-shot compositional thing, where we see different new compositions of objects and test our model that way. But it turns out that our model even struggles when it's seen those combinations at train time, so we didn't end up doing that.
Great. Thank you very much, Lisa. I think we might be out of time now, but if there are any more questions in the chat, then perhaps Lisa can answer those after. So thank you very much for that great talk, Lisa.
Yeah, thank you. And thank you for listening.
Okay, so the next part of our part of the workshop is on the Condensed Movies Challenge. So I will just share my screen now. Okay, can I get a confirmation someone can see my screen? Mohammed, maybe? Okay, great. Okay, so hello everyone, and welcome to the Condensed Movies Challenge. This is the very first edition of the challenge, and hopefully there'll be many more to come. And this is the first of the 2 challenges that are in this workshop. Okay, so the layout of this part of the workshop is as follows. So I'll start by giving an introduction to the Condensed Movies Challenge and dataset. I'll then announce the leaderboard and the winners of this first edition of the challenge. We will then hear a talk from the winning team on their method, and this is followed by a live Q&A where audience members can ask questions. After that, there is a short coffee break in the workshop. So if anyone in the audience has any questions about the challenge as well, then we can answer them in the Q&A as well. So please just ask those in the chats. So the challenge this year was organized by me, Andrew Brown, and Max Dane from VGG at the University of Oxford. So big shout outs to him for all of his help with this. So the introduction is going to be in 2 parts. I'll first introduce the motivations for this challenge and the Condensed Movies dataset. I'll then go over the challenge mechanics, so things like rules and metrics. So first, the first motivation of the Condensed Movies Challenge is to enable long-range video and story understanding. So there's been an increasing effort in the community to develop video understanding techniques that go beyond action classification from cropped short temporal snippets, as shown on the left, to learning from longer-term, more complicated videos with higher levels of abstraction. But progress in this difficult task in the community has, however, been slow. This is partly due to the unavailability of suitable data sets, but also the difficulty of framing the task. So what kind of high-level abstraction are we even interested in? And where can we find this relevant annotation? So we find that movies and TV shows actually provide the ideal source of data for testing this sort of story understanding through the understanding of long-range storylines involving complex high-level concepts like character motivations and character interactions and relationships. So understanding all of these high-level concepts in video is necessary for understanding the storyline. However, there are some difficulties with this still. So copyright issues mean that it's difficult to publicly release TV show and movie datasets, and it's still not clear how to obtain the necessary annotations for these high-level abstractions. So in 2020, we released the Condensed Movies dataset with the goal of resolving these difficulties and better enabling research into long-range story understanding. So it's the largest freely available movies dataset available for research today. Okay, so what's in the dataset? So the Condensed Movies dataset, or CMD for short, contains roughly 35,000 movie scenes from 3,600 different movies. So each of the scenes are 2 to 3 minutes long, making this a long-range video understanding task. And each scene has a corresponding high-level semantic caption, which describes the storyline. This includes descriptions of the motivations of the characters, actions, scenes, objects, interactions, and relationships. So each of the captions contain sort of concise, high-level abstractions of the storyline in that scene. Below, we see 5 different example scenes from CMD with the accompanying caption written below. So as you can see in the first caption, for example, it demonstrates intent in the video. You know, Sean wants to sulk alone. The second caption includes information about a relationship, the therapist. And the third one includes high-level abstractions such as emotion. Barbara Jean succumbs to her stress and anxiety on stage, and so on. These captions also contain reference to high-level semantics in the past or future in the movie. So the dataset contains roughly 10 ordered key scenes per movie. These key scenes are chosen to represent the moments in each movie that are most important to the storyline, with the most important interactions, often displaying the strongest emotions and the most important relationships. CMD therefore provides a condensed snapshot into full-length movies. So an example of the 8 key ordered key scenes from the film Karate Kid, the 1984 version in CMD, is shown below. Okay, so now for the actual task. So we frame the story understanding task as a text to video retrieval task. So given the high-level semantic captions in the dataset. The task is to retrieve the correct corresponding 2 to 3 minute key scene from the retrieval test set. And this task is the focus of the Condensed Movies Challenge. So first, the dataset splits for the Condensed Movies dataset challenge. So there are roughly 30,000 video caption pairs in the training set, 2,000 in the validation, and 1,000 in the test set. So the training and validation sets were public, so ground truth correspondences between videos and captions were made public, made available to participants. The test set was also provided to the participants, but the ground truth correspondences between captions and videos were not provided. Okay, so here we show some interesting statistics from the movies in the Condensed Movies dataset. So first, the histogram on the left, you can see there's a very diverse set of genres represented, from drama, actions, and comedies to musicals, romance, and fantasy movies. These films have been released over almost a century, as shown by this second histogram, demonstrating further the diversity in the dataset. We can see from the caption lengths that these are fairly concise, from 10 to 30 words, describing these high-level abstractions. And from the video duration, they roughly range from 1 to even 4 minutes, making this a very long-range understanding task. Okay, so the second part of the motivations was to widen access to video language research. All right, so one additional barrier for the wider research community in researching long-form video understanding tasks like this is the computational cost of directly training from raw data inputs. And this puts a constraint on who can actually take part in this research, because who has the available resources. So in order to alleviate this cost and hence broaden the access of this challenge to a wide range of researchers, the goal of this challenge is to train the retrieval system entirely from pre-computed visual features extracted from a wide range of pre-trained expert models. So participants could only train on these provided pre-computed features. So let's see which ones we provided. Right, so we provide to participants 6 different features for each video in the Condensed Movies dataset. For each, here we've written the dataset that they were trained on, the architecture, and the abstract objective that the expert model was trained on this dataset for. So this includes 2 different ImageNet pre-trained expert models for visual recognition, an expert trained on Places 365 for scene recognition, 2 experts for action recognition trained on Kinetics and Instagram 65 million, and an audio recognition expert model as well. Video features are extracted frame-wise at 1 frame per second in the interest of the dataset sort of being a feasible size for participants to use. So as you can see, these experts cover a wide variety of different tasks and surely contain sort of sufficient amounts of complementary information to each other. You can see by the architectures that they add a lot of implicit depth to the sort of cheaper models that the participants will train. And this should hopefully alleviate some of the disadvantage of not training from raw inputs. So that covers the features for the video data, so visual and audio, but there's also textual data in the dataset. Obviously, it's a text-to-video retrieval task. So due to the low computational cost of encoding textual data, we don't provide expert features for it, and instead provide all textual data in the Condensed Movies dataset in its raw formats. So this includes the captions for each clip and also the video subtitles. So this allows participants to choose any pre-trained model for the textual representations. Okay, so on to the second part of the introduction, the mechanics of the challenge. So right, there were a couple of rules for the challenge, mainly with regards to the data inputs. So in line with our motivation to have lower computational costs, participants were not allowed to extract their own video features from the videos, and were only permitted to use the features provided. However, participants could use any pre-trained model they wanted for extracting textual features. Participants were also allowed to use any form of augmentation or pooling on the provided features that they wish. Participants submitted to the challenge via CodaLab, and they were allowed a total of 10 different submissions. So very lastly on the introduction is the metrics. And in this task, we measured performance using geometric mean. So in detail, for an evaluation set with n different samples, we compute the geometric mean as per this equation here in the brackets. And this is computed via this cube root of the product of 3 different recalled K values for each sample. So 1, 5, and 10. And this is averaged over all samples in the evaluation set. Okay, so that is it for the introduction. So now the time has come to reveal the winning team for this year's challenge. Okay, so in the first year of its existence, we had 19 participant teams with a total of 5 submitting viable results to the challenge. Okay, so the winner of the 2021 Condensed Movies Dataset Challenge is Team Iona Croy. So massive congratulations to this team. This was a joint work from Iona Croitoru, Simeon Vlad Bogolin, Marius Leordianu, Hailin Jin, Andrew Zisman, Sam Albani, and Yang Liu. Massive congratulations to this team. So this was a joint work from multiple institutions, namely VGG at the University of Oxford, the Institute of Mathematics at Romanian Academy, University Polytechnica of Bucharest, Adobe Research, University of Cambridge, and Peking University. So massive congratulations to these guys. So here we show the top 5 leaderboard from CodaLab. Here we show the geometric mean of the winning submissions and a breakdown of the different recall at K values. It's worth noting here that our provided baseline is shown in 5th place, which was implemented using a mixture of expert embeddings model. The winning team, the winning participants, outperformed this by a very impressive amount, taking the geometric mean from just 3.5 to over 23. So massive congratulations to them. And as a reminder, we're next going to hear a live talk from them, no, a pre-recorded talk of their method and techniques, and people in the audience can ask questions and we will be able to ask them in the Q&A after. Okay, so now it's time for a talk from the winning team. So like I said, if anyone has any questions, please ask them in the chat. Okay, I'm just going to share my screen with sound. Okay.
Hi, my name is Ioana and today I'm going to talk about our method for the Condensed Movie Challenge called Multiple Text Embedding for Text Video Retrieval using TishText. Firstly, I will present a short overview of how the majority of retrieval methods work. This idea is used for all of our models that we train for this challenge. So we have a text query and a video. The process begins by extracting textual feature using a pre-trained text embedding. A similar process happens for the video side as well. After having the features, it is time to train the retrieval model. The final goal is to learn a joint embedding between text and video using a ranking loss. For this challenge, we simply use a mean aggregation over the time dimension on the provided video features, and we focus more on the text side embeddings. As already stated, our primary goal is the usage of multiple text embeddings for the text video retrieval task. In order to do this, we take advantage of the TishText algorithm that was firstly introduced this year at ICCV. Moreover, we use inverted softmax to mitigate the hubness problem, and lastly, we propose a simple way of ensembling several models in order to boost the performance. But first, let's talk about the intuition behind our approach. From this extensive study, which was done on several datasets, we can see that the retrieval performance varies drastically when changing the pre-trained text embedding. Let's take, for example, the LSMDC dataset. A gain of more than 6% can be obtained just by choosing to use the OpenAI GPT instead of Word2Vec. Moreover, we can observe the opposite for the condensed movie dataset, where the performance drops when using OpenAI GPT. The variance in performance both intra and inter datasets suggests the presence of complementary information among different text embeddings. Now, we will make a brief summary on how TishText works. Let's start with a baseline model. This model uses only one pre-trained text embedding and one pre-trained video embedding. While this model achieves relatively good performance, recent work started using multiple video embeddings. As it comes to the performance, this approach brings a significant boost as compared to the baseline. In contrast, our focus is the usage of multiple text embeddings for the text-video retrieval task. We show in extensive experiments that not only a similar boost can be obtained using multiple text embeddings, but we are able to achieve this gain by using the additional information only during training. For this challenge, we take one step further and we will demonstrate that by using teach text, we can create a strong ensemble with models that use different pre-trained text embeddings. Here is an overview of teach text. We leverage the side information brought by different text embeddings through generalized distillation. We begin by training several teachers. All teachers share the same architecture, but use different pre-trained text embedding at input. Now, we compute the similarity matrix between all the queries and all the videos from the training set. In this way, we obtain one similarity matrix for each teacher. Next, we aggregate all the teacher similarity matrices. In our final experiments, we use a simple but effective mean aggregation. Inspired from this, for this challenge, we use the same aggregation method to form the final ensemble. Now, it is time to train the student model. In addition to the retrieval loss, the student learns to mimic the aggregated teacher similarity matrix using a distillation loss. So, teach text is an algorithm that combines multiple text embeddings for the text-video retrieval task. By making use of generalized distillation, there is no additional computation cost during inference. Moreover, this algorithm can be easily combined with recent works, and it is not limited to using a particular model for both the student and teachers. Now, let's look at the main results for the challenge. Firstly, let's see how changing the text embedding affects the performance on the condensed movie dataset. All the models are based on the CE architecture and use the same video embeddings. As you can see, there is a big variance in performance when changing the pre-trained text embedding. On this slide, we present the results of using teach text. As it can be seen, using teach text boosts the performance. As observed in prior works, hubness is an issue when it comes to retrieval models. More exactly, after learning the joint embedding, some points have high probabilities to be nearest neighbors of many other points. In order to mitigate this problem, we use inverted softmax. Here, you can see how the performance varies when using the inverted softmax. In most cases, using inverted softmax brings a boost in performance. For this challenge, our best performing model is an ensemble of multiple students that use different text embeddings. Inspired by the teach text teacher aggregation, we compute the mean similarity matrix of multiple models in order to form our final ensemble. On this slide, the performance on the validation split of our best models is shown. We present the results with and without using inverted softmax for our best single models and our best ensembles. The best performance is obtained by assembling 8 models and using inverted softmax. The ensembles are formed from different students with and without teach text. All the students are using the same video embeddings, but they use different pre-trained text embeddings. In conclusion, by leveraging the usage of multiple text embeddings, we are able to achieve a strong boost in performance. Moreover, inverted softmax helped in mitigating the hubness problem. Thank you for listening. Code and data for teach text are available online on our project page. If you have any questions, please do not hesitate to contact us.
Great. Thank you very much for that. And I think the first author of that work should be on the call now. Iona, are you there with us?
Hi, yes, I'm here.
Great. Thanks very much for that great talk. The the sort of first comments from us on the organizers side is that we're really glad that we said that participants could encode their own text, because this is such useful and important insights that different text embeddings are so useful here. So just a note to everyone in the audience, if there are any questions, then please ask ahead. So there is one actually now from Max Bain, and he says, great work. Did you try fine-tuning any of the text models, or was this not feasible due to scale or memory?
Hi, yeah, thanks very much. Thank you very much, firstly. And to answer the question, yes, we did try to fine-tune the text models. We tried to fine-tune also for other data sets, not only for this condensed movie data set. For this challenge particularly, we fine-tuned GPT-2 large, which is not the best model among the GPT family. But yeah, due to scale and memory issues, we only managed to fine-tune this one, which is a medium-sized model. And in fact, yeah, fine-tuning helps. And if you, I presented some results, I didn't point it out in the pre-recorded video. I presented some results for the fine-tuning, and it helps around, depending on the data set, with around 1% or 2%, depending on the data set.
Yeah, great. Thank you for that. I had a question as well. So I guess to me, what seems like such an interesting result is this complementarity between different text embeddings. I'm wondering if that's and sort of demonstrated by there not being this clear hierarchy of performance across different embeddings that is shared across the different data sets, but there's a different one that's best in each data set. I'm wondering if that was a result that had been reported before, or and if so, or if not, what do you think is the relationship between these different data sets and the text embedding that performs best on them? So why is that different between data sets?
As far as we know, this difference, like a very in-depth study of the difference in the performance of different text embeddings it wasn't done. But as far as we try to understand we had the same question and we tried to understand it, we saw that there is a major difference in pre-training in the data that the text embedding was trained. So some of them are trained on text that have longer sentences, longer paragraphs, and so on. Some of them are trained on books. Some of them are trained on Wikipedia and so on a lot of different things. And there are some relationships that we saw, like, for example, some text embeddings that were trained on longer sentences perform better on data sets that had longer captions and so on. But yeah, we tried to study the difference, but in fact, it's a very hard question to ask and to have a lot of experiments for that. We have some of the intuition and some more motivation into the paper for the ICCV paper. So if anybody else is interested, you can check a more in-depth analysis and talk there. But yeah, we haven't answered to the full length that question. Yeah.
Yeah, and I guess what is even more interesting is that it seems to be not related to the size of the pre-training either, because that seems to vary massively from, say, Word2Vec to the most recent GPT. Yeah. So we have one question from Mohammed, and he asks, so how did you use the inverted softmax? It seems that it mitigates hubness in language domain by inverting the softmax and normalizing the probability over source words rather than the target words. Source words is vision here. So if so, how did you normalize?
So the idea of softmax, this is not, we haven't introduced softmax or so on. So it's another work that introduced this softmax. The idea is that to try, so we use softmax on the similarity metrics. Where is the similarity metrics between the vision and the language, like the video and the caption. And the idea is to scale down the similarity if there is a hub there, meaning that a text retrieves a lot of videos or a video retrieves a lot of a lot more captions.
Great. Did that answer your question, Mohammed?
Okay, I'm just not sure when you compute you divide by the denominator. Do you sum over the visual, by the videos that you sample from that you sample in your current mini batch, for example, instead of the predicted words? So
it is over text.
Over text. So how different do you handle, like, would be your denominator in case of standard softmax versus inverted softmax?
So yeah, for the standard, you look at the source, if you can say like that, and for the inverted, you will look at the target domain.
Thank you. Thanks, Iwan.
Great. Thanks again for all of those questions, and congratulations again for winning the challenge. So massive congratulations to you guys. And thank you to all of the participants as well in the Condensed Movies Challenge. Okay, so now the workshop heads into a short coffee break for the next 15 minutes. We will see everyone again in about 15 minutes.
I just wanted to test if that works.
Really excited to be here today to talk at the closing of the loop between vision.
Is it working? Okay, great. So I'll wait a few more minutes before we start the talk. We can maybe. Yeah, we're about to start the second part of the workshop. We will wait 1 to 2 more minutes for everyone to come back. Okay, maybe we should get started. Welcome everyone back to the workshop. And I'm really excited to have Alec Radford with us. Alec is a research scientist at OpenAI, and he's focusing on generative models and doing scalable learning. And he has been doing several impactful works, including DCGen, GPT, and most notably for this community, CLIP. And we have already seen lots of follow-up work on this. And even in an earlier talk today, we saw people looking and understanding CLIP. So with this, I'm excited to give Alec the stage. And just as a reminder, if you have any questions during the talk, you could post them, but unfortunately, Alec won't be here to answer them, but we'll collect them and then share them with him, and he can offline answer them. Thank you so much.
Be here today to talk at the closing of the loop between vision and language workshop. Hi, folks. I'm Alec Radford. Really excited to be here today to talk at the closing of the loop between vision and language workshop. A lot of my own research for the last few years has been focused on natural language processing, and more recently, kind of how do we leverage improvements in that space for other domains. And so the title of my talk today is about leveraging natural language for computer vision, and I'm really excited to chat with y'all. Yeah. So as a quick disclaimer, this talk is an opinionated take on what I think is a promising route for future research in computer vision. It isn't meant to be totalizing or to suggest other research agendas are not promising. And as I mentioned, I'm mostly speaking as an excited novice here, especially on the computer vision side. This is my first conference in the space. So yeah, I think kind of to start with and introduce kind of the questions and line of thinking here, it's really a high-level question of how should we go about supervision? How should we go about training computer vision models? Where do we get supervision for them? What are the right things to do? And I think, briefly, if you were to ask anyone kind of at a high level, probably their gut reaction would be, the answer so far has been, supervised learning. The ImageNet data set is kind of the canonical example of that. It's kind of, what everyone points to as kind of the breakthrough that, really kicked off modern deep learning in this space, and deep learning in general. And, at its core, it's a very high quality crowdsourced labeled data set where a bunch of different photos for a bunch of different classes are each associated with a unique ID. So we might have a bunch of flowers and they're class 532. There's a bunch of elephants, they're all class 781, et cetera, et cetera. And we train the system to predict these human labels as a multi-class classification problem. And that's kind of been the backbone of a lot of canonical computer vision systems used widely across the field. And to some degree, it's been like the ImageNet decade. It's actually about a decade now since like the major conference and results that kind of have kicked it off. And you can see we've made a ton of progress. There's been a ton of research and development and findings on architectures and techniques and regularization and all these different strategies that have been kind of really built off of and benefited from having such a high quality data set. And so, we've made a lot of progress, but if you kind of look at these curves, you kind of notice that actually things are somewhat plateauing. The ImageNet data set when it came out was extremely impressive and kind of, a heroic undertaking. But with some of the, more modern results we know, sometimes it's showing its age now. So where do we go from here? If ImageNet kind of helped drive a lot of the progress of the last decade and kind of this crowdsourced, multi-way classification, predicting discrete classes kind of was the dominant strategy for learning representations and features. There's a lot of discussion in our field now about where we might go from here. There's a lot of excitement and research on self-supervised and unsupervised learning, but that's not really the focus of my talk today. So instead, what I want to kind of just talk about is a little bit more maybe pragmatic or kind of near term. So there's this great paper, Deep Learning Scaling is Predictable Empirically, from a bunch of folks at Baidu in 2017. I think often this work goes a little unnoticed compared to other scaling research that's more recent, but this is actually covering both computer vision and NLP. And what they find is these kind of very smooth prediction curves as a function of training set size for performance across all the different metrics you might kind of use standard, cross entropy, top 1 accuracy, top 5 accuracy. There's a little bit of a breakdown in the low data regime, but beyond that, we see just that as you collect more data, you get these very predictable trends in performance. So kind of that just says that if you want to have better systems, collecting more data is a super promising route. And if we look at kind of the last few years of computer vision, there's been a lot of different work and attempts in this space. So the JFT 300 million data set from Google is kind of, one of their first versions of this. And so what they do is they move beyond, kind of crowd labeling, the way that ImageNet is constructed to kind of these weakly supervised automatic construction techniques. So they've scaled much, much farther. There's this kind of great graph on the left showing how, a lot of progress has been made, but the data set sizes were fixed. And kind of this paper studies how much improvement can be derived from scaling weakly supervised methods to 300 million images with 375 million labels. It's still this kind of, I think there's like 40,000 different label classes. It has a hierarchy, but it's still predicting kind of discrete labels for pre-existing categories. Facebook has also had some really great work where they've said, we could use hashtags on Instagram as supervision. So this gets kind of into an interesting middle ground where it's user-generated data and it's moving towards natural language. It's still maybe hashtags, it's still categorical prediction, and they kind of map it back onto ImageNet. But they show that leveraging 1 billion of these tags or 1 billion images results in much higher performance than just using only pure standard ImageNet in this graph on the right, and has much better scaling properties. So, really this talk is about what about if we actually use language? What does that get us? What can that buy us? Why might we prefer that? And, I think for context, a lot of these results were coming out back before a lot of the modern breakthroughs in natural language processing happened. This is before BERT. This is, before a lot of the modern transformer-driven generative pre-training kind of approaches really took off. And so we didn't really have, the techniques to leverage natural language. And so you see that these papers kind of instead go back, and look more like ImageNet. They discretize and tokenize and kind of just like extract these, very narrow sources of supervision that kind of fit the techniques we had at the time. But I think with all the advances we're seeing in the field, it's really exciting to start using language natively as supervision instead of maybe dicing it up or slicing it and fitting it back into kind of the computer vision mold. And so, yeah, at the core of this, these are random I went onto Wikipedia and just kind of went through my browsing history and quickly pulled some photos paired with their captions on Wikipedia. And so you can kind of see from this already that instead of just predicting, class 532 or class 781, it has no connection to language. It's just a single discrete label, or, you get like 9 bits from an ImageNet label. You can kind of try to work towards using full natural language. And there's a lot of richness and diversity here. You have, on the left, pets and their owners gather at Sea Ranch Dog Park. You have geolocalization supervision here. You have supervision about nouns. You have supervision about, verbs. What does gathering mean? Well, you kind of can see that a bit in this photo. There's maybe even world knowledge here about pets and their owners. And, if you could disambiguate, you can know that the people are the owners of the pets. So there's a ton of richness here that we just don't have in a lot of these classic computer vision data sets. In the middle here, we have supervision about style, the Queen Anne style. And on the right here, we have supervision that could help maybe learn OCR, reading the words Kelly in the diagram could help with predicting the text here. So, this is hardly a new observation. There's been work here for decades. And there's actually, I think, this great paper that kind of, it's surprising actually how early this was tried. This paper is almost 6 years old now, where they basically said, hey, there's, Flickr and there's lots of these photos paired with captions. How can we leverage them? And they kind of showed that, at the time, this is still like GoogleNet was still pretty new. And, they were able to get really good performance actually, just by using this weakly supervised data in place of ImageNet. But the technique didn't really catch on at the time. And, it kind of really, I think it was primarily just because we didn't have the natural language side figured out for prediction here. So they would discretize all of the words in the sentence or description and do these kind of bag of words softmax predictions over them. So why using natural language supervision instead? And and again, like here, the terms are a little weak, they're a little vague, but it really means treating language as a whole and not doing these destructive transforms and kind of, again, probably trying to leverage the more modern techniques. So kind of to keep pitching on this point, language is a native medium for human supervision. Like these examples weren't created for computer vision systems. These were created by people to help other people. And if we can have systems that can understand that human supervision, we can kind of leverage that and kind of, instead of having to go and necessarily create and label and generate our data ourselves, we can just try to build systems that learn much more closer to human learning and then leverage all of the great content out there that humans can learn from. It's also, as I was kind of mentioning, a very rich source of supervision. It's diverse, it's multitask, and it's general, it's broad coverage. And I think a good little sketch of this is kind of, on the left is like a very old school canonical data set like MNIST. And you can kind of think of this like plane as like task distribution space. So MNIST is like this one peak. It has a ton of dense data for the task of MNIST. There's 60,000 labeled 0s, 1s, 2s, 3s, 4s, 5s, 6s, 7s, 8s, 9s. That's way more than a person learning digits would ever get. But it's extremely narrow and it's extremely specific. And a lot of what we struggle with nowadays with computer vision and machine learning in general is robustness and generalization and generality. And by contrast, the internet is kind of, I think, this like, much broader landscape of supervision that's primarily through natural language, as these captions kind of show. There's another reason, which is natural language is a general interface. So, and this has kind of been more developed in the natural language space, but this paper from August 2017, I think is kind of one of the first times we really see this in computer vision, where they take kind of the same setups as the 2015 YFCC 100 million paper, and then they show that they can actually zero-shot transfer these systems to ImageNet. So, it's purely a generalization test. They never train on ImageNet, but, they've learned all these n-grams and words that they've associated vision features with language. So then at test time, they can just go and slot in ImageNet classes and see how well a system could do. And I think this is, again, really exciting from a generalization, from a robustness, from a transfer perspective. And it's using natural language as this general interface the same way we do to communicate a task or specify a goal to a system and then evaluate how it does. And so that kind of framework here in this kind of sketch picture, again, is like we train over this broad natural language distribution on the left, which is kind of all the different photos and captions and tasks that you might do. And then on the right, we're evaluating it back on our more standard computer vision or machine learning data sets. There might be a cluster for object classification. There might be, eval for geolocalization or OCR. And how do we get systems that can do well across all these tasks is kind of, a core interest of mine and OpenAI in general. Another thing I think that's really important to point out is, when the JFT 300 million authors kind of discuss one of the problems with the data set is that it's noisy, because they're taking, this web data and this image search data, and they're trying to extract it back down to single classes, which are like single words or pairs of words. And so they have this funny example where for like one of the tortoise classes, or one of their classes, they actually have both tortoise the animal and tortoise the tortoiseshell sunglasses or glasses. And their system by default can't disambiguate these, but a natural language system that sees a full context of a sentence, and uses modern machine learning techniques is probably actually not really bothered by this. It can figure out from the context whether it's the tortoise the animal or tortoise the glasses. And suddenly some of that noise and difficulty, we might have said, internet data is too noisy to use. A good natural language understanding system can actually leverage context to get around that issue. And so kind of now that I've spent a lot of time trying to talk about what I think are some of the advantages of natural language supervision, I want to kind of talk about some of our research, motivated by these beliefs and kind of trying to test them. So this is about CLIP. So CLIP stands for Contrastive Language Image Pre-training. And so what we do briefly is we go and find a bunch of image text pairs across the internet. We have an image encoder and a text encoder, and we use a simple contrastive embedding loss, it's InfoNCE, to basically encourage the model to assign a high similarity score to image and text pairs that are correct. And then we use all the negatives of incorrect pairings from the combinations in the batch as negatives. So that's the pre-training step. We're just training it to predict which image is paired with which text. And then what we do at test time is we create dataset classifiers from labeled text. So we might use a template like a photo of a blank, and then we can slot in all of the CIFAR 10 categories, plane, car, dog. And then we can use it for zero-shot prediction. So these are basically generating class embeddings from our text encoder. And then what we can do is we can run an image through our image encoder and then say, okay, which of these, a photo of plane, dog, car, cat, do we think, or does the system predict is most likely? And then we can use that for prediction. So that's kind of the setup, and it kind of fits into that pre-train on the internet, then evaluate on our standard data set setup. And so the question might be kind of like, okay, what are the details of training, and then how well can these systems do? And so we use 400 million image text pairs, batch size of 32K. We train for 32 epochs over this data set, and we use pretty standard machine, computer vision stuff here. AdamW, cosine learning rate decay. For architectures, we use either ResNets or VIT-based models for image encoders, and then we use these transformer-based text encoders that have kind of really powered a lot of natural language breakthroughs in the last few years. On the left is pseudocode, and on the right is kind of the reason we went with this setup is we found that it was much more compute efficient than some baselines or alternatives. So a transformer language model was kind of actually what the first almost year of this project was focused on, was training more GPT style models that were image captioners that took in an image and then tried to predict the text from it. And at least on this zero-shot classification on ImageNet, we found that they just weren't very compute efficient. A lot of this is because it's difficult to perform 1,000-way classification with a language model. You have to evaluate 1,000 different fprops and check the log probabilities of every label, and there's a lot of details there that just end up hurting you. Whereas something like this contrastive adjective looks much more like standard text classification, except of course the labels are dynamic. They're full sentences or phrases or even paragraphs, and there's a lot of richness there. They're not fixed categories. It's kind of open set, general, and we really hope to leverage that. And so what do we find? We see a lot of okay task generalization to existing data sets. So we're evaluating CLIP zero-shot here. Again, for all these data sets, we don't use any training data. We just say, is this a photo of, we get the class list for the data set, we maybe do some prompt engineering, and you can kind of see on the right quickly for a bunch of different existing data sets. We check a very broad spectrum of tasks here. I think in total, we looked at like 35 different data sets. And it can kind of do car classification, geolocalization, food, kinetics, so action recognition, videos even. And we see kind of a spectrum here. So in the left graph, we're comparing to a linear probe on top of ResNet 50 as kind of a maybe a weaker baseline, but a very canonical baseline. And this is, again, our zero-shot system with literally zero data. And we're competitive. We bat out average match performance. You can see there's some tasks we do better on, and some we do much, much worse on. So particularly things that are very domain specific, that like the kind of the supervision just maybe isn't there for CLIP, or it's a complex task. So things like classifying the distance in a photo of a car, like a self-driving data set, or satellite photo classification, or very domain-specific stuff like medical image classification. CLIP isn't. You don't want to use CLIP zero shot as a dermatologist or something like that. Is basically one of the findings there. And this is not too surprising. When we're training on general purpose data, we get kind of more general purpose capabilities like recognizing what country or types of food or pets, and less of like very domain-specific things. This is kind of the trade-off between generality and specificity, maybe restated. What's exciting, though, is we see that these zero-shot systems have much improved effective robustness over models that are trained or fine-tuned on ImageNet. And so, there's kind of this graph on the left. And what does effective robustness mean? Effective robustness is basically this concept where we can say how well does our system do on a given data set, such as ImageNet, and we might predict that its ImageNet performance would be predictive, especially for the same classes, of its performance on other distributions. So, if we had a truly robust system, what you see is what you get in terms of performance. If it does well on ImageNet, it should also do well on ImageNet v2, or, maybe drawings of photos from ImageNet, or, sketches or photos, ImageNet classes within your house. And in practice, one of the big findings has been that existing computer vision systems quickly break down in terms of their robustness. What we see is because zero-shot, CLIP is zero-shot, it's not leveraging supervision from a specific data set. It's much more generally pre-trained across this very wide and general distribution. And so we hope that, and it uses natural language to basically combine this all together into a single classifier for a given space. And so we hope that it makes it much more robust to all these different distribution shifts. And we kind of found this empirically, where we can close these robustness gaps by up to 75%, and get a lot closer to this kind of true or representative performance of the system, hopefully. Additionally, we kind of compare the zero-shot and supervised task specification. So getting back to that natural language as an interface question, the way we primarily communicate and specify tasks as people is through language. We tell someone, oh, you're going to perform this task, or we want to do X or Y. We don't always, for every single given task, give labeled examples. We rely on existing knowledge, existing understanding to have transfer and to invoke capabilities that are already known. And so, when we compare that to standard machine learning, which is always, or mostly example-based specification, we actually find this really interesting result, which is a zero-shot CLIP model can actually outperform few-shot linear probes for task. There's some follow-up work that kind of leverages hybrids and kind of shrinks this gap compared to the results we're showing here. But it's really showing that natural language can specify a task and kind of invoke and potentially better robustness and better specification than purely example-driven learning. So that's the left graph. And we see that on this task suite also that CLIP features are kind of more general. They outperform existing systems, anything that we had publicly available that we could benchmark against. And on the right, we kind of can see, kind of this specification framework and how that interacts with robustness. So few-shot classifiers, again, this is an effective robustness plot. So the x-axis is ImageNet performance and the y-axis is performance on distribution shifts. We see that, few-shot classifiers are natively more robust because they, you're almost hopefully learning, you don't have a lot of data to find spurious correlations or quirks of a specific distribution. Hopefully with only one example, whatever performance you get is actually closer to real generalization. And we see kind of the same thing, which is as we use more and more labeled data, actually, our effective robustness goes down and our gap compared to standard supervised systems shrinks. And zero-shot does significantly better as well. So a lot of this effective robustness is coming from the natural language, is coming from the zero-shot specification instead of more example-driven or distribution-specific specification of task. And then we kind of show how we can use natural language to actually improve performance on these effective robustness tasks. So, the standard way might be we adapt with the linear probe or things like that. And we can kind of see that, we improve our ImageNet performance on the x-axis quite a lot. But actually, like as kind of this prior plot showed, our effective robustness can even go down a bit. But if we instead use natural language to better specify the task, so in this case, some of the classes in these transfer data sets don't exactly map one-on-one to ImageNet classes, and prior work would bin over, the ImageNet classes that were most relevant. We can just use natural language to say, okay, you're actually looking for a scuba diver instead of, or a person instead of a scuba diver. And, an ImageNet model might have classified, pooled over like the 3-person category, scuba diver, baseball player, and I forget what the other one is. Maybe it's like figure skater or something. We can just say it's a photo of a person. So natural language is this extremely powerful way of specifying a task to a system. And we also see that kind of that generality looks like it shows up. So on the left, we kind of see efficiency plots where for kind of a given architecture, we have higher performance than existing systems. And on the right, we have kind of a distribution, like an effective robustness plot for transfer to downstream task. So we have our ImageNet axis on the on ImageNet score on the x-axis, and then we have our transfer score on all these different downstream data sets where we fit a linear probe. And we find that our ImageNet performance is much more predictive and much closer to kind of what you see is what you get than existing systems. There's also robustness via prompt engineering. So this is a little bit of the inside baseball of CLIP, but what we find is that, CLIP is trained on a very wide distribution of photos, and they have all sorts of formats and labels, and this can result in kind of some noise and some difficulty. And so what we found as we did our research was by ensembling over many different prompts, a good photo of a cat, a blurry photo of a cat, we can help kind of specify to the model all of these axes, hopefully that it might want to be invariant to and what is preserved across them, i.e. the object identity. And we actually saw that this could consistently improve performance by quite a lot, about 5 points overall if we spent some careful time kind of prompt engineering. Again, we always did this on validation data sets and then checked on tests, and it can be a significant efficiency gain. So that's, a lot of open research is kind of exploring how we best specify things to models via natural language now, instead of maybe more traditional, how do we best fit classifiers on feature spaces. And then we also have a nice study of the effectiveness of these zero-shot classifiers. So what we can ask is, on the left, is what is the data efficiency of these zero-shot systems? How many labeled examples do we need to match its performance with linear classifier? And it can range by quite a lot over systems. In some cases, you actually get like very little transfer. It's less than the performance of even a single example. In others, it actually is quite strong to do zero-shot. And on the right, we look at the correlation between linear probe performance and zero-shot performance. So we can kind of think of what we're studying here as like, how well is CLIP during its pre-training and therefore its zero-shot performance optimizing for a bunch of different tasks. So those tasks are all these classifications on all these downstream data sets. And a linear probe is kind of our heuristic for what we expect the system to do, because the zero-shot CLIP classifier is also a linear probe module, like L2 normalization, no biases or something like this. And what we find is there is a strong correlation here. So that's encouraging for the pre-training of CLIP to be optimizing also directly for transferring for downstream tasks. It'd be concerning if we found that these two were uncorrelated, because that would suggest that our pre-training setup isn't actually optimizing well for generalization or zero-shot transfer compared to like what we know the feature space underneath it could do. A final concern is we're training on a ton of data. So, a very natural suspicion might be, are we cheating? And so we built a data set detector for kind of detecting basically duplicate images. We ran this over our data set, and we kind of studied performance as a function of detected data overlap. And for most data sets, we find very little overlap. But another finding we have is that there are some data sets where there is significant detected overlap. However, in general, even though there is significant, can be overlap, the performance shift is not that large. And we kind of see this between, from pre-training, we don't have that big of a train test gap. And if you have 5% contamination and you do maybe 5% better there, you multiply those two factors together and you get a 0.25% accuracy change. So there's probably a little bit of overestimation of performance here, but in general, there's nothing that moves, as far as we can tell, more than single digit here, and only a few data sets that standard significance test would highlight as an issue. So that's kind of our talk about CLIP today. I think in the second half, we kind of just really talked about kind of results and kind of our early experiments here, but kind of, the core message, that I just want to communicate here is, we're really, with all the improvements in natural language over the last few years, finally able to, I think, unlock a lot of this native supervision that people have made for each other, and we're moving towards systems that can leverage and learn more naturalistically from that. And I think that's a super exciting opportunity for the field. And there's lots of other work going on here that I didn't even have time to discuss. And I think it's really promising, and it'll be exciting to see further developments in this space. Finally, I want to thank my joint co-author, first author, Jung Wook, who helped a ton and basically did all the evals, built out all these eval suites, and really made this work possible, and all of our other co-authors on this work. Thanks. At this point, we're opening up to, I guess, questions and discussion. Appreciate you spending the time. Excited to chat.
Hey, thank you for the talk. And unfortunately, Alec couldn't in the end make it to the questions. But feel free to reach out to him if you have any follow-up questions, and he'll probably be able to answer them directly with you. And also, advertisement for our panel later during the day at 3 o'clock. So if you have any general questions, that's probably also a good time to ask them to the panel, and we can discuss there some of a few questions. Maybe I unshare my screen at this point. And we are excited to have our next speaker. Cordelia, are you there? See.
I think maybe she hasn't arrived quite yet.
Okay, yeah, we're a bit early. So see, she had some. But she'll be there in about 5 minutes. I think we can take a short break for 5 minutes. I think her talk is scheduled for 12 or 5. Let's take a short 3-minute break, and then we'll be back. And hope the Cordelia will be there. Hey, Cordelia. Cordelia, can you hear me?
Hi.
Hi, great to have you. We said we'll start in about 3 minutes, but if you want, you can start sharing your screen, and we can see if that works.
Right.
No rush.
Just share the screen.
Other people find it
You
important.
turn actually on the video. Let me just turn on the video.
Sure. Your video was there? It's gone again.
Sorry?
Yeah, I think now we can see your screen, yes.
Yeah, maybe now can you see my camera?
Yes, we see your camera, yes.
Okay, and now it's all good?
Yeah, I think it's perfect.
Right. Okay, do you want to start on time, or do you want to start early?
Sorry, I was talking at the same time. Can you repeat?
I said, do you want to start now, or do you want to start in 2 minutes?
Yeah, let's wait 2 minutes, because I said we'll take a short break.
Okay, I'll just get a glass of water. I just had another talk before this one. So.
Yeah. Okay, I think we can get started. We are very excited to have Cordelia Schmidt with us today. I actually have to say, since I started my career like 10 years ago, I was always following her work and frequently using her work. So very excited to have you here. She's a research director at India and also has a joint position at Google, and has numerous awards, including 3 Test of Time awards, which I think is very impressive. And happy to hear from you today, Cordelia.
Yeah, just one sec. Actually, yeah, thank you for the very nice introduction. It's a pity actually to have to give the talk online again, but hopefully next time we can. Actually, I can give it in person. Can you see the slides?
Yes.
In full screen?
Yeah, I think they're in full screen.
Okay, fine. Right, so I'll talk about large-scale learning for multimodal videos today. There's a huge amount of videos available online and growing daily. There, for example, film archives such as BBC and INA. There's obviously YouTube, where we have 30,000 hours of video uploaded every hour, and there are 770 million surveillance cameras worldwide. One task is classification of activities such as birthday party and grooming an animal. And if you look at the videos, we can see that here we have the visual information, but we also have the audio information and the speech. Another example of automatic video understanding is text-to-video retrieval. Again, given the query, you want to retrieve the corresponding videos correctly. And again, to do so, it's important, or its advantages, to have multiple modalities and not just one. Similarly, if you want to have the complete description of a story, again, if we have multimodal information, we obtain better results. So if you want to precisely understand the video content, we should have access to all modalities simultaneously. For example, here we can see that the man is serving food to the woman, but only if we hear, "Is this Indian?" do we know that the man is serving Indian food to the woman. Another reason we use multimodal video representations is that this gives access to large-scale cross-modal supervision, for which we don't need any manual notation. For example, it has been recently shown that we can train on the how to 100 million dataset. I'll start by presenting our VideoBERT approach. VideoBERT learns from multimodal videos by taking into account visual video information and speech transcribed with ASR. For example, here we can see the frames, and here, but in the meantime, you're just kind of moving around your cakeboard. The BERT model learns the correspondence between video and speech. We learn from large-scale data, for example, cooking and instructional videos. The VideoBERT model takes as input text, as does the standard BERT model. It's a transformer-based model which takes into account input text obtained by ASR and learns by masking the text. And in addition, our VideoBERT model also takes as input video features encoded by 3D convolutional features for small chunks, 1.5-second chunks of video. So now we have a video clip, the corresponding text, and we feed the text into the transformer, and the video features, which are small snippets of the video encoded by 3D convolutional features. And for both video and vision, we use masked language modeling, so masked token modeling as in BERT. And to do so for the video representation, we'll rely on clustering. We can then train our model on 300,000 cooking videos, for which we have in many cases descriptions, so ASR, or what the speech, which describes actually what's happening in the video. So for example, here, keep rolling tight and squeeze the air out to its side. We obtain the text transcriptions by using automatic speech recognition, which gives us in many cases a relatively good description of the video content. We can then train our model on 300,000 such cooking videos, and we can then show that we can use the obtained model for zero-shot prediction. For example, for the 2 frames on the right, we can predict correctly the verb make and the noun pizza. If we measure more quantitatively the performance, we can show here the results on the UCOOK2 dataset. The top line on the left, in the left table, shows the results for a supervised approach. We obtain 46% accuracy for verbs and 30% accuracy for objects. If we now use our video BERT model, it has seen no supervision but is only trained from the weakly supervised or automatically supervised data, we get a comparable performance, better for the object and slightly worse for the verbs. So we can actually see that this video BERT model learns the video to language correspondence, and it's close to fully supervised accuracy. If you look at the table on the right, we can see that the pre-training size actually impacts the performance. We can see that by doubling the size or by tripling the size, we increase the performance significantly, and we can see that this improvement is not yet saturated. We can really see that these models learn from large-scale data. Now, if we want to go one step further and use these models also for other tasks such as vision question answering, we want to rely on cross-modal supervision. So here the goal is to obtain zero-shot performance for video question answering with cross-modal supervision. So the video question answering would be the question and the corresponding video. What type of animal do we see? And the answer would be, the correct answer would be fish. You can see that there's a fish in the video. And to train this approach, what we do is we generate a large-scale video question answering dataset automatically. So instead of taking training data for which we have the video, the questions, and the answer, we want to create it automatically. What we rely on here, we rely on existing manually annotated question answering text corpuses. So the Squad V1 corpus has 100,000 question answer pairs for paragraphs from Wikipedia articles. So we have the Wikipedia article and the extracted answer and the extracted question. And there are the transformers, they're transformer models which are trained for answer extraction. So first, we have the text corpus, we train a model to extract the answers, and then given the text corpus and the answer, the model extracts the question. And this is an existing data set, an existing trained question answer transformers, which we reuse here for our cross-modal training. So given this, what we do is we take our how to 1 million data set, we split it into chunks where each chunk corresponds to a sentence. And obviously the sentences are obtained by ASR. And so here what we have, we extract the sentence by using punctuation extraction with recurrent networks. Then once we have extracted the sentence, we align it with the video. This gives us a start and end time. And then we can take the extracted sentence, and for the extracted sentence, we can generate an answer and a question. So now what we have video clips with corresponding question answers. And if you look at a few examples of these generated question answer pairs. You can see here a video, then the ASR, add some of your favorite sprinkles, give it a mix, and then the generated questions, what can we add to the mix? And the generated answer is sprinkles. You can see that here we correctly generate a question and the corresponding answer. Another example, here we see the clip on the top, then the corresponding ASR. The sound is amazing on this piano. Generated question, what kind of instrument is the sound of? And the generated question, the generated answer is piano. So again, we can see that the generated pair is correct. And here, a failure case. For children, give one breath every 3 to 5 seconds. And the generated questions, how long does it take for a child to take a breath? 3 to 5 seconds. So here, basically, the question is incorrect and the context would be needed to generate the correct question answer. So here it's incorrect. And then once we have these generated questions and answers, we have a multimodal transformer to take as input the video and the questions, and then an answer. And then we use contrastive loss with positive and negative answers to train this model. This can deal with large-scale data. Here, 16,000 different answers, 16 million different answers, and it allows to train our model with an open vocabulary. If we now perform zero-shot vision question answering, we use no annotated examples for training and report results in state-of-the-art data sets for which we have annotations for the test data, we can see that our model outperforms a random model significantly. However, obviously the performance could be further improved, and this is like open research. If you look at the few zero-shot results, we can see here, what is the man cutting? And the correct answer is pi. Here, we have never seen any annotations, but just learned this from our completely unannotated corpus. And then if you would just use the text only model, it would be onions, right? Probably in the cooking data, thing which is mostly cut are onions, which is incorrect here. And we need the visual information to correctly predict what the man is cutting. Second example, what is the largest object at the right of the man? The answer of our model is wheelbarrow. And if you would use text only, it would be statue. This is kind of obvious because many people, they're next to a statue if they ask where they are. But this is not the case here. And here we use the video information to predict the answer correctly. And finally, misclassification. In what room does this video take place? And our answer is dining room, but the correct answer is kitchen. So basically, I guess the model has not correctly recognized that the person is cooking. And if you would use text only, it would be studio. So I guess most videos are visualized indoor scenes or in a studio. If we now look at the impact of the pre-training size, we can see that again, for zero-shot results, the performance goes up. If we use more training data, we can see that it starts to saturate. And basically, this means we might need more diverse data if we want to further scale up the approach. And then we also report results where we have a small amount of annotations and use our approach for pre-training. And we can then see that again, the amount of data which we use for pre-training impacts performance. And then interestingly, we can see depending on the VQA data set we use for evaluation, we get a larger improvement on the IVQA data set, which is in domain, which are videos of instructional videos which have been annotated by us. And the second example, MSVD QA, we can see that the improvement is less significant. So here, the pre-training plays a smaller role, and this actually shows that the data used for pre-training impacts the zero-shot performance, but then also the fine-tuning performance. So obviously, if the pre-training data set is closer to the fine-tuning one, its impact or its increase in performance is bigger. And then if we compare our results to the state of the art, we can see that it outperforms all the state of the art methods, also those who use How-To 1M for pre-training. And we can also see here that the difference between our approach with training and with pre-training without is significant. So here it's 5%, here it's 2%. And then here we compare, again, it's a couple of percent in performance increase. And the last part I've shown before how to use this cross-modal information for automatic zero-shot training. And then another question is obviously, how can we use these models jointly? So in the last part of my talk, I'll introduce the audio-video vision transformer. Transformers have shown excellent results for a number of tasks. For example, they have shown excellent results for image classification. So the vision transformer VIT has shown excellent results for static images, for image classification of static images. And here we extend this approach to videos. And in order to handle a large number of tokens, we explore more efficient factorized attention variants. We take as input, our approach takes as input a video, embeds them to tokens, and adds the position embedding. I'll show in a moment how we embed the videos to tokens here. Once we then have these tokens and position embedding, very similar to the VIT transformer, we feed these tokens into a transformer architecture. This means every token attends to all the other tokens in the sequence. We then have an MLP head and obtain the class probability for all of the classes. So first of all, how do we encode the videos? And then second, how can we make our approach more efficient such that it's not quadratic in the number of tokens? For input encoding, we use a two-blip embedding. So instead of extracting patches for a number of frames, which you could do by just uniformly sampling, we extract 3D spatial temporal doublets. So this is a patch in an image plus a temporal extent. As you can see here, so a patch and its temporal extent. And then we linearly project it into a token and then add the position encoding over the sequence. This captures the temporal information already in the tokenization stage. As I said before, it works better than uniform sampling. And then we can train a transformer to predict the classes. However, this is quadratic in the number of tokens. And so if you have a video, and in particular if the video is long, the number of tokens is much larger than it would be for images. So what we have done here, we have separated the encoders for spatial and temporal information. This reduces the complexity, requires less compute, and is less prone to overfitting. Furthermore, the spatial encoder is initialized from a pre-trained VIT model. So here what we have, again, we embed our tokens as doublets. We then have a spatial transformer for an image, and then a temporal encoder which models the information between the different images. This is obviously less complex as we factor out the complexity and take into account individual images and then combine them over time. If we look at a comparison of the different model variants, the first model is our full spatial temporal transformer. You can see that on Kinetics 400, we obtain an accuracy of 80, on Epic Kitchens an accuracy of 43. And then if we compare, we can see that we have the flops and the parameters. And then if we actually have the factorized encoder, we can see that the performance on EpiKitchen goes slightly down, on Kinetics 400 goes slightly down, and on EpiKitchen it remains constant or slightly better. This is due to the fact that EpiKitchen is very small, and so if you want to train a large-scale model, you're prone to overfitting. If you compare the runtime, you can see that the factorized encoder is actually much faster. We can then also compare to an average pooling baseline, and we can see that our factorized encoder outperforms it significantly with almost no increase in runtime. So we can see the spatial temporal model is better for large data sets. The factorized encoder is faster than the spatial temporal model, and it's better for small data sets. And all spatial temporal models outperform average pooling. And then here, if you compare the state of the art, you can see that our approach outperforms the state of the art. And then even more so, if we use huge transformer architectures and large-scale pre-training datasets. We can see this for Kinetics 400, and then similarly, same holds for Kinetics 600. And this is just taking modeling, designing a new architecture for modeling the video information. We can now also extend this to model the audio-visual information. So what we want is we want to extend our video transformer called Vivid to multimodal information by adding audio. So you can see here, we have the video, RGB fetches as input, and then we want to add audio spectrogram patches. So here we represent the audio by spectrogram patches, but it makes it possible to also apply a Vivid-based model to the audio patches. Now the question is, how do we combine these two modalities? The dominant standard paradigm is light fusion. People extract features, a separate encoder for video, another set of features with a separate encoder for audio, have a classifier, and then use late fusion to combine these two classifiers. And furthermore, in general, the architectures and the data sets and the evaluation benchmarks are different. One idea to extend this approach to a transformer would be to feed in tokenized RGB and spectrogram patches, and then have just a multimodal transformer on top of it, where we have self-attention between all tokens. So this would be a way of doing early fusion. We take all the tokens in and just have a transformer which takes as input all the tokens. However, this scales quadratically with the sequence length, and also video has a lot of redundancy, so we might not want to combine all the video patches with all the audio patches. So what we have done here, we have introduced the multimodal back bottleneck transformer, which introduces a small number of bottleneck tokens where there's only fully pairwise attention within a modality. So we would have pairwise attention inside the video modality, but then the attention between the video and audio tokens is only via the bottleneck tokens. So now we don't have the quadratic complexity anymore, but we just combine the video tokens with the bottleneck tokens and the audio tokens with the bottleneck tokens. So the bottleneck tokens are the bridge between the two modalities. Also shown recently that we can extend this approach to additional modalities. And next question, do we need all layers to be cross-modal? And so here, I've actually experimented with variants where we have the bottleneck fusion at all layers, or where we have them only starting from a specific layer, which we call bottleneck mid-fusion. And so the bottleneck mid-fusion allows earlier layers to specialize to unimodal patterns. And it's kind of a compromise between late fusion and early fusion, right? The mid-fusion doesn't take into account and combine all the input patches, but only combines them after they have learned some information. And now if we look at the performance, here we show the results for the audio set and for bottleneck tokens. We can see, so here what we measure is the fusion layer, so at which layer we fuse, and blue is the vanilla cross attention, and the red is the bottleneck attention. And you can see that if we fuse them at the end, performance is similar, but if we use as fusion layers, as fusion layer 8, we can see that actually the attention bottleneck method outperforms the vanilla cross attention. And vanilla cross attention, which chooses from layer 0, the results would be here. And we can see that actually the cost is much higher for the vanilla cross attention, where we have to compare all the patches. So if we fuse the information at layer 0, the cost is much, much higher than if we have the bottleneck attention. And we can see that in all cases, the bottleneck attention improves the performance over the vanilla cross attention, and it has significantly lower compute. And so we experimented on two different video classification tasks, action recognition and sound event classification. So in both cases, so for action recognition, we've seen before, people in general only report results for video information, but obviously you can also take into account the audio information. And similarly for sound event classification, such as audio set, people usually only use the sound, but we have shown that by adding the visual information, we can further improve the performance. So we can really see for these two different tasks of action or video classification, visual video classification and audio classification, both cases we gain by having this multimodal information. And if you look here, so the thing which you can see on the right is by using our multimodal bottleneck transformer, we obtain an improvement over late fusion for the audio set and for EpiKitchen. And we can also see that our approach outperforms state-of-the-art significantly. And if you look at the audio set, you can see if we use audio-only features, we obtain 44%, video-only features 32%. So we can really see that video information also is important here. So it's not only, as people have used previously, it's not only important to have the audio information, but the video information also has some additional information. And if you combine the two of them, you have a significant boost in performance. Can show really here that having these audiovisual features improves the performance with now no additional cost, basically. And similarly for EpiKitchens, again, we can see here the audio features performance for actions in particular is not that good. And here we have the results for the video features, but then we can see if we add the audio features to the video features, we do get an improvement in performance. And if we look at the attention heat maps, we can see on the left the middle frame for two different classes, baby cry and piano music. You can see the heat map, the attention heat map by when we use the vanilla fusion transformer. We can show the heat map for our multimodal bottleneck transformer. And we can actually see that the multimodal bottleneck transformer focuses on smaller regions and sound sources. So it seems to be that the correlation between the two sources is more tighter with the bottleneck transformer. In all cases, it's nice that the attention really focuses on the regions which are relevant for the sound. And so maybe the example here, which is yodeling, you can see that here there's quite a lot of heat maps, region in the heat map, and here it's much more localized on the mouth of the person. In conclusion, we have seen that weak supervised learning exploits the large amount of data available online. It relies on the correlation between multiple modalities, for example, video and language. And we have seen that it's important that models take into account spatial, temporal, and multimodal information. And future work is how we extend these approaches to interact with the world. And so here, just very briefly, two of our recent works, which are actually learning visual representations by interacting with the world. So here we have the episodic transformer for vision language navigation. So what we have is as input a sequence of instructions. And then what we want to do is we want to navigate around an environment and determine, given as input, the sequence instruction, the history of the visual informations, and then the action. We want to determine what the next action is. We've shown here in this paper that by having a transformer which takes into account the history of our previous observed actions, we can really see that it remembers and creates the link between the different places of what we have seen before. So here, go to the right of the fireplace, pick up another vase. So here we know that we should navigate back to the fireplace and pick up the vase. And so basically, if we have a transformer, attention mechanisms allow us to remember this. And we can show that if we use instead an LSTM, the loss or the forgetting is much faster. So it remembers less cleanly. And then the second approach here is leveraging the large amount of online data. So here, one of the things is that if we go from unseen environments to seen environments to unseen environments, in many cases the performance drops significantly. And so here, what we have done, we have collected additional houses from Airbnb data sets, and we can use those to increase our training data set, and we can show that this improves the performance on previously unseen environments. Thank you for your attention.
Thank you for the nice talk. Happy to take happy to open the microphone for questions. Anyone? Cordelia, are you still there?
Yes.
Okay. While we wait for questions, maybe I have a question. So I really like the large scale pre-training work and how that compares to previous supervised approaches. But I was wondering, how do you see that bias comes into those models? I mean, we know, of course, that models who are trained on supervised models are biased, but how do you think that compares to models on this sort of more unsupervised but larger scale data? Just general bias, but also there's concerning bias, including gender or race.
Yeah, I think this is like one of the open questions is how to deal with bias, right? So, I mean, if I had a reply, then yes, it would be very easy. But I think the question is, I guess, how do we detect the bias? And I guess to detect the bias, we have to kind of dig into the data, right? Because basically, if you just harvest the data and you have no control over the bias, or maybe you could have something like if you want to remove people or names, you could like exclude them, right? But if you want to exclude any general bias, you have to kind of dig into some statistics of the data, right? And I think this is also what I showed a bit, and what I said a bit. In some cases, the pre-training data really improves the performance, and in other doesn't, right? And this is also some domain gap within what we use for pre-training and what's used for testing. And I think this is something which we have to see, is how to actually have some measure or some statistics on the data and have some way of curating the data, right? Because otherwise we cannot get rid of the bias, or we can just use it and then have a very large set of additional training steps on top, or we have another protocol of debugging the bias. But I think it boils down to really understand what's in the data, right? And this is something, in my opinion, people haven't done enough, right? And it's kind of not clear how to do it, but I think this is the next thing where we really have to see is what's in the data, right? And for text, it's much easier because there, I mean, you can understand what's in there, right? You can read and you can have a quite good analysis and understanding of the semantics of the text. While for the video, I guess you would have to have some pre-processing which understands what the data is about. I think this is kind of my very high level answer, is that we need to get a grasp on the data, right? We cannot just say, oh, we take everything which is around. We have to understand what's in there.
Yeah, I think I agree. I think it's very challenging, especially because we are learning the representations. So we don't really know yet how to understand lots of the video. So yeah, definitely.
Yeah, but I guess one thing would be, for example, pseudo labeling, right? You could have some pre-trained models and then use those as pseudo. So I think there are some ways, right? Because there are some data corpuses which are annotated, right? And so we can maybe use them for bootstrapping and analysis. Right?
We have other questions.
I have,
Yeah,
I have,
Anya, I think.
yes. Hi, very nice talk. I
Hi.
have two questions to the work on Just Ask. So when you are generating these questions, right, sort of using the ASR descriptions directly, it seems that sometimes the questions may not be grammatical or, you know, not very fluent, or maybe kind of like false premise with respect to the video. So how important that issue is really, and so how important, you know, is to get the questions right? Did you have any analysis on that?
So we did actually a small scale analysis on I think it was 100 pairs to see how many, I mean, basically retroactively, right? How many are related to the video, how many are completely incorrect. And so actually surprisingly, they were not, in many cases, they were not completely incorrect, but then they were not related to the video, right? If you have a question which is completely not related to the video, then there's nothing you can really do with it. But I don't remember exactly numbers. I think 40% of the questions were really relevant, and then the rest was kind of split into incorrect ones grammatically. And then also obviously DS are sometimes also incorrect, right? Sometimes people just say random things and it doesn't make sense. And so I guess there you could imagine there's something actually I was thinking, but then it was quite hard. You could imagine to have a number of pre-cleaning steps, right? Pre-clean the ASR, have some way of generating the questions and seeing if there's some correlation with the video. But for now, it's automatic and it's about 40% correct, which is enough to train the model, right?
So I guess the question is, how much is enough? That's kind of the interesting point. How much effort should one even put into this cleaning? Because it seems that you could use it, you could only learn something very useful from these not perfect questions. That's kind of interesting. The second question is, I guess, the framing. So if you think about this as just a pre-training task, right? The way that you go about this is a kind of like fill in the blank, but not exactly. So the answers are sort of extracted from the ASR. So one may ask, why not just frame this exactly as the masked language, learning task, and just say, I'm going to be masking out these answers, from the transcript, and just aim to fill them out. Would that be equivalent, or is there something specifically about framing this as the question answering task, you think, that makes it work?
I guess the question answering lets you much easier, go to zero shot, right? Because then you can really have the question and the video and output the answer, and you can use this contrastive loss for the question answering. And obviously you could also have the model which is pre-trained, could have the model pre-trained on the ASR on the video, but then somehow and mask it out, but then the masking wouldn't be really a reply to a question, right? Then you would need to have some, it wouldn't do exactly the same thing, right? So you couldn't, maybe you can, but I think the pre-training would work. The pre-training would work actually in the paper. We have an experiment where we use the pre-training with the standard masking loss and the pre-training with the video question answering, and we can show that it works a bit better, but it's not like completely, like it also works, right? Pre-training and how to works also for the video question answering, but what doesn't work is the zero shot, right? I think this is the thing which I'm kind of excited about, is how to go to the zero shot. And this is also the thing where I kind of feel maybe for pre-training it's not that important, but if you want to go to real zero shot, then you have to clean better, right? Because otherwise, I think for pre-training, some kind of language plus vision, which kind of correspond, will be fine for pre-training, right? And then basically it's just like a data augmentation problem to do the fine tuning correctly. But if you want to go to zero shot, I think this is the thing which I'm kind of most interested in, because in the end of the day, you really want to have the zero shot, at least I want to have the zero shot capacity, and there it could be actually interesting, and maybe we should go back to this, is how to see how to clean it. And then if you measure zero shot, you could really have an improvement, right? For pre-training, you wouldn't, right? If you clean it and make it better. But it goes also towards the fairness, right? If you understand better what's in there, then, the zero shot performance will also go up, right? So the two things are maybe quite related.
Thank you, that makes sense.
Thank you. Any short, one more short question maybe, or? Okay, I think I don't see any further questions. So let's thank Cordelia again for coming and giving this exciting talk. And I think we'll have you again for the panel later on today. Yes, thanks so much.
Yeah, thank you. Bye.
Bye. And next up is the value challenge. And I think Lindsay is already here. If you unmute yourself and want to share your screen, we're excited to hear about this. Hi.
Hi, can you hear me?
Yes.
Okay, let me try share my screen. Can you guys see the slides?
Yes, we can see the slides and I can hear you. So thanks
Yeah.
for coming and presenting the value challenge. Take it away, Lindsay.
Okay, yeah. So hi everyone, this is Lindsay. I'm a researcher from Microsoft. Thank you for joining us today for the CLVO workshop, to listening to our great talks from invited speaker, challenge hosts, and the winners. For the next hour or so, let me take you for a tour to the new challenge we're just holding for this first time, video and language understanding evaluation, or shortest value. This is a joint work together with many of my collaborators from Microsoft, UNC Chapel Hill, UC Santa Cruz, UC Santa Barbara, and Tsinghua University. Yeah, so let's get started. So here's the outline of this session. I'll first give an introduction to value benchmark, followed by the overview of value challenge. And then we have our exciting winner announcement. And each of the winning teams will be giving about a 10-minute introduction to their winning approaches. So for the first part, I will introduce the value benchmark. So as you may hear from the previous invited talk, that the video community have been using language as a tool to probe into video understanding ability of multimodal AI systems. And it comes down to actually many grounded tasks with video and language input. And the most popular three perhaps are what I'm showing here. Text to video retrieval, that is to retrieve the most relevant video that corresponds to the text query. Video question answering, answer questions about the video content, and the video captioning, generate concise yet informative description about a video. And there are many data sets created for these three tasks. The past decade has witnessed the growing in video and language data sets. Until early 2019, the largest video language dataset is probably ActivityNet, with more than 600 hours of video data. So these datasets, what I just showed in the figure, are mostly built on single channel videos. In this case, the annotators or the models are presented with a sequence of video frames. And the popular data sets including Youku2, ActivityNet for retrieval and captioning, and MSRVTT, MSVD for video question answering. And existing video and the language models, especially the more recent video and language pre-trained models, are evaluated on their own choice of data. So on different tasks from different domains. So hence, it's really hard to make a comprehensive comparison among these different models. While a general video and language system should do well on diverse tasks, domains, and datasets. And on the other hand, in reality, most of the videos are multi-channel or multimodal in nature. In addition to video frames that provides appearance and motion information, there are often subtitles or ASR for the text modality and audio signals as well, which also contain rich information other than video. There are also datasets proposed on multi-channel videos, mostly focusing on two modalities, video frames and subtitles, like TVR, TVQA, TVC on the TV domain, and how to R, how to QA on instructional videos. Hero is a representative work from EMLP 2020 that could handle both multi-channel and single-channel video and the language downstream tasks. So for application scenarios in real life where videos are often multi-channel, we would expect a smart video and language system be able to leverage information from different modalities. And lastly, from the NLP community, we have seen publicly accessible large-scale multitask or even multilingual benchmarks help facilitate the advances in modeling of NLP models. So to this end, we are motivated to propose a value benchmark as a comprehensive testing bed for general video plus language understanding systems. And there are four main characteristics of value benchmark. First, we focus on multi-channel videos with both visual frames and subtitle or ASR for the task inputs. Second, videos in value are from diverse video domains, including user-generated content from YouTube and TV episodes or movie clips. And third, value benchmark assembles 11 datasets over 3 representative video and language tasks: video retrieval, video question answering, and video captioning. And lastly, we support a value leaderboard. And also we have just hosted and are hoping to hold value challenge every year to encourage the development of advanced video and language systems and to track the progress in video and language research. Oh, yeah, here are some example video clips from value. I don't think it's playing. Sorry about that. So the videos that are coming from diverse domains ranging from TV episodes and movie clips with different temporal dynamics, event shifts, and people interactions, to instructional videos and vlogs dominated by monologues with less human-centered scenes. And some other feature of videos in value, including the varying video length. We have videos from 10 seconds to 76 seconds. All the video data sets except for the text has a high multi-channel ratio. That is, the proportion of videos have subtitle channels. And value include 11 datasets across 3 popular video and language tasks. So this table here shows the datasets for each type of video and language tasks in value, its video source, and the evaluation metric. We use the average of recall at 1, 5, and 10 for retrieval tasks. And note that TVR and How2R, they not only need to retrieve the most relevant video from the corpus, but also need to predict the relevant span that are, so the time span that are most fit to the text query. So there is another additional metric is the temporal IOU. And then for QA tasks are evaluated with accuracy, and the CIDR is used to evaluate model performance on captioning tasks. Each dataset has its own train and validation and testing splits, and the testing annotations are hidden from the public for leaderboard evaluation purpose. And we have more detailed statistics for each dataset in our paper. I'll skip them for now. And in value benchmark, we use Hero as our baseline model architecture, as its strong performance on all 3 types of tasks on multi-channel videos. So a brief introduction to Hero. Hero is a hierarchical video and language model consisting of a cross-modal transformer for local temporal alignments between frames and subtitles, and the temporal transformer for global temporal context. Hero is designed to be pre-trained with 4 tasks: mask language modeling, mask frame modeling, video subtitle matching, and frame order modeling. And it has achieved competitive results on several multi-channel video and language tasks. Many of them are included in the value benchmark. And to fully understand the characteristics of value benchmark and to provide guidance for future works on value benchmark, we conduct detailed experiments and analysis to investigate first the impact of input channels and video subtitle fusion methods. Second, impact of video representations. Third, the transferability between tasks. And lastly, the benefit of multitask learning. Due to the time limit, I'll focus on deliver the main messages. So feel free to refer to the paper for more detailed discussions. And the first question we seek to answer is that, is video channel alone sufficient to achieve good performance? When leveraging both video and subtitle channels, the model achieves the highest meta average score, the average across 11 datasets and 3 task types, with the best performance also across all value tasks. Even for tasks that originally designed for single channel videos, for example, Youku 2 and for text, augmenting the inputs with subtitles is beneficial for model performance. So we can conclude that subtitle or ASR contains rich information that are helpful to solving the tasks. And secondly, what is the effective way to fuse video and subtitle embeddings? We test out several variants based on value. First, the 2-stream model, the subtitle pathway and the video pathway make predictions independently, and we aggregate the result at prediction level. And second, we simply concatenate the embeddings from subtitle and frame and feed this long sequence to the temporal transformer to generate predictions. Note that the temporal alignment between subtitle and frame are not used in this case. That is, the temporal transformer only knows the order of the subtitles or frames, but not the correspondence between subtitle sentences and frames. And the third instance utilizes the temporal alignment explicitly by adding the embeddings from the 2 modalities together. And then for the fourth instance, uses concatenation instead of summation to enforce the temporal alignment. And lastly, Hero adopts a cross-modal transformer to learn contextualized frame embeddings from temporally aligned subtitles and frames. And as the results show in this table, the best performance is achieved by Hero, suggests that early fusion of temporally aligned frames and the subtitles can help boost model performance. And next, we show how value tasks relate to each other by conducting transferability evaluation. So when transfer the model trained on one dataset to another, we often observe much worse performance. These results indicate that there are large differences between tasks in value benchmark due to the domain gaps, different video length, and different task formulations. And the last question we are interested in is, can we have one model to conquer them all? Here we explore several variants of multitask learning setting, all based on the Hero architecture. For example, single task training, multitask training by task type, and multitask training by domain. and all task training. And lastly, we try the all task training first and then fine tune on single task. Among them, all task training first, then fine tune on single task achieves the best performance. And we can also combine multitask fine tuning with the pre-training. We take advantage of pre-trained hero model and repeat experiments from line 2 to line 6 of this table. When compared with their counterparts without pre-training, we observe consistent performance improvement across all training settings considered. However, pre-training and multitask fine-tuning often do not complement each other. Hope now you have an understanding about what value benchmark is about. So with the value benchmark, we hosted our first value challenge this year. And next, I'll briefly talk about some of the statistics from this year's value challenge. In total, we have 4 challenge phases for value challenge. So the value phase evaluates task agnostic algorithms on all data sets and tasks in value. And retrieval phase focuses on 4 text to video retrieval tasks. QA phase focuses on 4 video question answering tasks. And then captioning phase evaluates on 3 video captioning tasks. And as I mentioned before, we have 3 types of tasks in value. So each task comes with their own evaluation metrics. This is a challenge to combine all different evaluation metrics for the following reasons. First, different evaluation metrics across different tasks may have different scales. For example, accuracy for QA task and CIDR for the captioning task. Accuracy often is from 0 to 100, and the CIDR on some data set can easily go over 100. And secondly, simply average the metrics may favor data sets with smaller size, for example, in retrieval tasks, or metrics with larger range, like CIDR in captioning tasks. Therefore, we introduce a new evaluation metric to rank models on our leaderboard and for the competition, mean rank, the average of model ranks over all tasks. This measure is similar to how we rank countries in Olympic Games, in the sense that the team who wins the most number 1 on different data sets or tasks wins the challenge phase. In the case that there's a tie, we break tie using the meta-average, basically averaging model performance over all data sets regardless of the metric scale. And we are honored to have 12 teams from more than 5 institutions in both academia and industry participating in this year's value challenge. During the challenge, we restricted the number of test submissions to be less than 5 to prevent overfitting to the testing splits. In total, we have received more than 45 submissions to our evaluation server. The breakdown of number of participating teams to each challenge phase is shown in this table. Note that a team is allowed to participate in multiple challenge phases. And let's announce the winners of this year's challenge. For both value phase and QA phase, we have the winning team as Team Kakao Brain, which achieved 5% absolute improvements across all value tasks and 1.6% absolute improvements across all QA tasks. For retrieval phase, the winner is Team Aiden Lee. They were able to achieve more than 5% absolute performance improvement over value baselines across all retrieval tasks. And lastly, for the captioning phase, we have the winner TKD AI, which achieved about 24% absolute performance improvement over value baseline across all captioning tasks. And next, we will have each of the winning team to present their winning approaches. Due to the time difference, we do not have them with us today, so I'll be playing their pre-recorded talks. And the first winner talk is from Team Kakao Brain, the winner of Value and QA phase. Let me play the video. Let me know if you can hear the sound.
Hi, my name is Minchul Shin from Team Kakao Brain. First of all, thanks for hosting such a nice competition.
Can you guys hear it?
And I'm very glad to make this winner.
Yeah, we can hear it.
We are the winning team for Value and QA phase, and the title of our presentation is a task-aware ensemble approach and the transfer learning with a visual concept. Before we begin, let me briefly summarize what the Value challenge is. Value is a newly introduced benchmark which has 3 macro tasks and 11 subtasks. And each subtasks are defined based on 6 kinds of data sets. The ultimate goal of this challenge is to train a task-agnostic foundation model which can be generalized well for any kinds of tasks without optimizing a model for a specific task. So in the retrieval task, when the query is given in the form of a text that describes a certain moment in the video, the model retrieves the exact moment in a long video with the exact time for the interval. In QA task, the query is given in the form of a question, and the expected result is an answer for this question, which is usually formulated as a simple classification problem. Last, in the captioning task, the model generates a caption that describes the target clip with the frames and the corresponding subtitles as an input. So in this competition, instead of raw videos, the participants are given 8 kinds of visual features that are extracted offline from different pre-trained models. This figure illustrates our entire training pipeline. Basically, we explore all the possible combinations of visual features and the fine-tuning strategies and other trivial hyperparameters to find the optimal training configurations for single models. Our base model is Hero, and we use the publicly available pre-trained checkpoint for fine-tuning. We did not explore the pre-training part because of the limited time of the competition. Given a Hero model initialized with the pre-trained checkpoint, our base approach is to fine-tune the model with all the subtasks, then fine-tune on the single target task. However, we also tried all the variations on this fine-tuning strategy. For example, we tried the fine-tuning on the single task only, or fine-tune the model on all the tasks without fine-tuning on the target task. And we also explored all the combinations of visual features at each fine-tuning stage. So in this case, because the pre-trained Hero model was trained on the ResNet slow fast, we fine-tune the model with the clip VIT plus a slow fast feature, then fine-tune on the single task with the mill NC feature. This is still another case. And interestingly, regarding the training features, fine-tuning with OL series features bring significant improvements, while the feature distribution is different from the one the model is originally trained on. So in this table, the model is the pre-trained Hero model is trained on ResNet slow fast feature. As you can see in this column, we can find that significant improvement for some subtasks when we fine-tune the model with the different visual features in this way. We also perform an extensive parameter search to find the optimal set of hyperparameters. For example, training features and batch size and gradient accumulation steps and the number of GPUs and so on. So based on this process, we managed to improve the single model performance in this way. So comparing to the baseline scores in value leaderboard, we managed to find a better optimization for a single model. So as you can see in the table, our single model performs better for most of the cases. The simplest form of our approach is to fine-tune the hero model on the single target task. And with a slight modification, we also try to fine-tune our model on all the subtasks in advance to benefit from the multitask learning. But drawback of this approach is that we cannot expect the potential benefits for this because the performance will be degraded if dataset domains are significantly different from each other. Last, we extract the visual concept from the frames, then add this information to the subtitles as a form of text. In this way, we provide our model rich and fine-grained visual information. For one object detected from a frame, we infer up to 2 corresponding attributes and combine them with the original subtitles with the special token SCP. So in this example, if the original subtitle was I like my dog, then we extract the visual concept, which is a girl, blonde, small, and a dog and a brown puppy. And the first word is object, and the latter part is the attribute corresponding to the object. This is another example. We used a VinVL model for this pre-processing, and as you can see in this figure, our model successfully detects the cabinet wood brown and woman smiling cooking, and we integrate all this information into with the original subtitles and use them as an input for Robota Tokenizer to get the sequence of input IDs. The visual concept gave us an improvement for 5 out of 11 subtasks, and it was especially helpful for QA tasks and works best for Vatex dataset domain. Next, we explain our ensemble strategy. For retrieval, we use hyperparameter tuning by Bayesian optimization technique to find the optimal weight for the weighted sum of individual model scores. The weights are randomly sampled and fed to tree-structured Parazen estimator algorithm based on the objective function. We use the mean recall for the objective. For QA task, we use a learning-based approach. We convert the problem to find the optimal weight into learning a single-layered, fully connected layer with no bias. In this formulation, training a single-layer linear layer is very fast, which means we can ensemble more single models in a short period of time. Last, we modified consensus tree ranking for the captioning. For each sentences the model predicted, we calculated the sentence similarities for each other, then picked the most general one for the final choice. In this way, we could effectively remove the outliers. This table summarizes the effectiveness of our ensemble strategies. Comparing to the single model, our ensemble score significantly improved. For example, in case of a Hautoir dataset, the the improvements was up to 39%. We apply our findings step by step for the submission and finally achieved our final score for the test. Here, let me briefly summarize our approach. So we start from the single model, and first we try to optimize the single model through the hyperparameter search, and we also extracted the visual concept to use it as auxiliary information. All these informations actually increase the model variance, which is a key factor for a successful model ensemble. Then we move to the model ensemble part. Then we apply 3 different ensemble strategies according to the macro task. Then the final score is calculated based on these ensemble scores. This is the end of presentation. Thank you for listening. Please feel free to ask any questions. Thank you.
Yeah, unfortunately, we are not able to host live QA for the winning talks today. If you have any questions about Team Kakao Brain's presentation, please contact them directly via email. Yeah.
Hi, my name is Min.
And the second winner talk is from Team Aiden Lee, the winner of retrieval phase.
Hello, my name is Aiden from 12 Labs, and I'm here to present our approach, Visarat, which placed first place on the video retrieval track of ICCB Value Challenge 2021. This work is done with the collaboration with Han-Seok and Min-jun from KAIST Graduate School of AI. Before I dive into our approach, I would like to thank the organizers of Value Challenge for this amazing challenge and the benchmark dataset. The video retrieval track of the Value Challenge is composed of 2 text-to-video tasks. The first one is the traditional video retrieval task, or VR task, where its objective is to find the best video that describes the given query within an extensive video database. The second one is a newer task, Video Corpus Moment Retrieval, or VCMR task, where its objective is to find the best video and also localize the moment or timestamp within the video. Value Benchmark is composed of 4 different domain-specific datasets. TV dataset is composed of TV episodes, such as Friends. How-to datasets is composed of instructional videos. YouCook datasets is composed of cooking videos. And Batex dataset is composed of open domain YouTube videos. TVR and How-to-R datasets are designed as a VCMR task, while YouCook and Batex datasets are designed as the traditional video retrieval tasks. The goal of the video retrieval track for both tasks is to get the average recall value as high as possible. In the end, the competition's winner is determined by the average rank of the model's performance on each dataset. Our motivation for our approach is the following: how to tackle the video corpus moment retrieval, or VCMR task, while maximizing the performance of the models trained on the video retrieval task. We recently observed a huge performance gap between the models optimized just for the video retrieval task and the models that are optimized for multitasks. Therefore, we created an assumption that the model maximized for the video retrieval task could ideally perform competitively in the VCMR task with an appropriate video segmentation technique. So we propose our approach, Visarat, which stands for Video Segment Retrieval, that jointly tackles VR and VCMR tasks with the model trained only on the VR task. During the training, for the VR task datasets, the Visarat model is given with the whole video and query to output a similarity score. For VCMR task datasets, on the other hand, there is one additional step. Before the videos are given to the model, the original videos are segmented into shorter clips based on the ground truth timestamp annotation. In other words, the model is trained on a segmented video caption pair instead of a raw video caption pairs. This structure allows the model trainable on the BCMR task datasets, just like the VR datasets, without modifying the underlying structure of the model during the training phase. During the inference stage, for the VR datasets, the model calculates the similarity scores between the given query and all the videos inside the video corpus. The final rank of the video is based on the outputted score. For VCMR task datasets, however, the model is given a pool of videos without any specific timestamp information to segment the videos as it did in the training phase. Therefore, we create a pool of heuristically segmented videos based on the timestamp statistics in the validation data. For example, the original video from the TVR dataset can be segmented into a 0 to 3 second video clip or a 29 to 59 seconds video clip. The specific numbers of lengths and strides for each dataset are calculated based on the timestamp distribution of the validation dataset. Now that we have a pool of segmented videos with the timestamp information, we give these segmented videos to the model to treat them as separate videos and use the timestamp information to calculate the temporal IOU. As presented, this simple heuristic segmentation technique allows us to jointly tackle VR and BCMR tasks using the model trained only on the VR task. Next, I would like to briefly introduce the model architecture of Viserat and present our results. Our model is composed of 4 different components. The first component is the frame-level visual encoding layer. The frame-level visual encoding layer is composed of 2 different types of clip models, the pre-computed clip feature and raw frame clip feature. The difference between the two is whether the clip model's weight is updated or not during the training. We element-wise sum the 2 clip features and use it as the final frame-level visual encoding. The second component is the video-level visual encoding layer. The video-level visual encoding is based on the transformer architecture and creates a temporal connection between the frame-level visual encodings. The third component is the visual subtitle fusion encoding layer. We notice significant performance differences between the model with the subtitle feature and the model without the subtitle feature. We obtain a single BERT-based subtitle embedding for the entire video and element-wise added to the video-level visual encoding. We use this summed embedding as the final representation of the video. The last component is the similarity estimation layer. We obtain the similarity score between the query embedding and the final video embedding using cosine distance. The query embedding is obtained through pre-trained CLIPS text model. Now we present the result of our single model compared to the hero model under the fine-tune only setting. Our model exceeds the baseline hero model on all 4 datasets with up to 263% relative performance gain in the How2R dataset. This clearly shows that our simple heuristic segmentation technique with the model trained only on the VR task can not only outperform in the traditional VR task, but also perform competitively in the BCMR tasks. Next, I would like to introduce our final submitted ensemble model and its result. Our ensemble model is a combination of our Viserat model and hero model. We use a simple weighted averaging technique to get the best performance for each dataset. Using this simple technique, our ensemble model achieves the new state-of-the-art performance on all 4 datasets. We noticed an average of 22.9% performance increase compared to our single model, showing that the 2 models complement beneficially to each other. Both of our models are up in the leaderboard. Our example model won the video retrieval track of Value Challenge with the mean rank of 1.75, placing the first place on How2R and Vatex dataset, the second place on the UCook dataset, and the third place on the TVR dataset. The future work includes a large-scale pre-training of the Visirat model on other external datasets, such as How200 million sets, and the incorporation of a separate reader model that extracts moments from the results of our Visirat model. If you're interested, you can read our paper up in the archive. Thanks for watching. If you have any questions, feel free to reach out. Thanks. Hello, my name is
Yeah, and we have our last winner talk from Team TKDAI, the winner of captioning phase.
Hello, everyone. My name is Tang Mingkang. I'm an AI researcher at Tsinghua University. The title I want to share today is Clip for Caption Plus, Multi-Clip for Video Caption. This work was completed together with my team members during my internship at Tencent. Our method ranks first in the leaderboard of TVC evaluation and Vatex video caption challenge. We won the championship on the video and language understanding evaluation competition in the caption task. This page shows the framework of our proposed method. First, we used the pre-trained model of Clip and Slowfast to extract video features from origin video frames. Second, we sampled the extracted frame features using TSN Symphony. Then, we embedded both video features and text for feature fusion. Finally, we trained several caption models and examined the output of these models for a final strong result. We use the pre-trained Clip and Slowfast as our video feature extractor. Clip was pre-trained on image text matching with 400 million image text pairs. Clip has two different image encoder architecture. For the first architecture, ResNet architecture, we choose ResNet 50 as our image encoder. For the second architecture, the Vision Transformers architecture, we choose VITB32 and VITB16 as the image encoder. We extracted clip-based video features at 10 FPS. Slowfast was well designed for video recognition. We chose Slowfast ResNet 50 as our feature extractor. We set a sliding time window to extract the Slowfast feature. The time length of the time window is 1.5 seconds, and it moves 0.3 seconds every step. After feature extraction, we sample the extracted frame features using TSN Symphony. During training, TSN Symphony divides all frame features into case threads and run next one frame feature in each thread. It can increase the simple randomness on the limited frame length. The TSN Symphony was not used in testing. We extracted keyphrase from all the phrases at equal intervals in testing. The visual video feature was embedded by the video feature embedding layer. We also use a video subtitle to enhance our model. The subtitle text was embedded by the text embedding layer. Finally, the text embedding and video embedding were concatenated as the external input. In order to make the model distinguish between these two embeddings, a special embedding layer, token type embedding layer, was added. First, we set the video label as 0. We set the text label as 1. And then the token type embedding layer was used to embed the token type label. After that, token type embeddings were added to the video embedding and the text embedding. All three embeddings has the same dimension as 1024. We conduct a two-stage training. In the first stage, we train the origin model. In the second stage, we use the best model from stage 1 to initialize the model and further train the model with self-critical. Self-critical can optimize slider directly and encourage the model to perform consistently in training and testing stages. We use the slider score as a reward in stage 2. Experimental result shows that self-critical significantly improved the slider score in stage 2. This page shows the word level in the MOS strategy. During the decoder stage, the caption model generates one word according to the softmax output and takes the word as the input for the next step. We average the softmax output of all models and choose the word with max probability in each step. The model selects the correct word with a larger probability after considering all the results of several models. It can reduce the bad influence of wrong words. This page shows the sentence level in the MOS strategy. We use a caption evaluation metric, such as slider, as the importance score of a generated caption. Considering the predicted captions of one video from n different models as TI, the importance score for caption SI can be calculated by assuming the rest of predicted captions as ground truth captions. We report the performance gain brought by each component. As shown in the table, each strategy contributed to the slider improvement, and the calculated facial video features and self-critical provided a significant improvement. The enhanced video feature allows the model to capture more information, and self-critical makes the model directly optimize the slider metric. We train more models for the ensemble. We reported the single model result and the ensemble result on the public test set and the private test set of TVC, UCOOC2, and BETIX datasets. As shown in the table, compared with the best result of a single model, our ensemble strategy has significantly improved the metrics on these three datasets, and our methods ranks first in the value computation. Thanks for listening.
Okay, that's the end of all winner talks. Here are some useful links to everything covered in today's value challenge talk. We have technical reports from all three. If you are interested in our value benchmark, please visit our website, and a more detailed introduction can be found in our paper. And thank you for listening. We hope to see you in our next value challenge next year.
Thank you, Linjie. Thanks, Linjie and the other winners for the great talks. And next, we will have Professor Mohit Bansal to talk about knowledgeable and spatial temporal vision and language. Seems like Mohit is here, but before playing the pre-recorded video, and let me first introduce Mohit Bansal a little bit, although we must be know him very well. Professor Mohit Bansal is the John Lewis Parker Associate Professor and the Director of Milgrer Lab in the Computer Science Department at UNC Chapel Hill. And prior to this, he was a research assistant professor at TTI Chicago, and he received his PhD from UC Berkeley. His research expertise is in statistics, natural language processing, and machine learning, with a particular focus on multimodal, grounded, and embodied semantics, human-like language generation, and question answering, dialogue, and interpretable and generalizable deep learning. So he
did lots of wonderful works in the vision and the language domain, and he is also a figure in this domain, and also someone who I admire very much. Okay, so and Mohit also won many best papers in variance computer vision and natural language processing venues. Okay, so for this talk, we will play the pre-recorded video first, but Mohit is also here, so you feel free to ask any questions in the chat, either in the chat or later in the live QA session. I'm sure Mohit will be very happy to answer them. Okay, let me share the screen.
Thanks for the invitation, and thanks everyone for attending. So I'll talk briefly about, I think I have around maybe 25 to 30 minutes. So I'll cover two brief topics today on some of our work in the last 3-4 years. So the first part will be video and language kind of tasks from different perspectives, and then the second one will be how to look at these large-scale pre-training models and language models, but with different aspects of multimodality in them. So yeah, so this is the first part, video-based dynamic spatial temporal context or knowledge. Here I will be basically looking at how to build joint video and language understanding tasks, where the models on these tasks need to perform complex cross-modal reasoning on this dynamic spatio-temporal information. So we'll start with something from 3-4 years ago on video and dialogue or video and language question answering, and then its spatial version, and then we look at retrieval tasks, multilingual retrieval, and a more recent task on future or next event prediction. Yeah, so this is TVQA from EMLP 2018, I think. So this was our attempt to build a large-scale compositional video and language data set. So the main criteria was that the questions in order to be answered should need information both from the video and the dialogue or subtitle text. And they also should provide both temporal and spatial localization information for the model to both be able to predict or learn from. So what I mean by compositionality is this is an example of how the data was collected. So it was requesting annotators to give us specifically these kinds of compositional questions. For example, what is Sheldon holding when he's talking to Howard about swords? So in this case, you can already see that the red part would be something where you have to look at the subtitle dialogue, right, and figure out which part of the video is Howard being talked to about swords by Sheldon. And then inside that time range, you have to go to the frames and visually look at what is Sheldon holding. And this there were also reverse and different kinds of combinations of this, right? I could say, what was Howard talking about when Leonard entered the door? So first you have to visually find the temporal grounding of when Leonard entered the door, and then inside those frames, you have to go and look at the dialogue and answer what was Sheldon talking about or Howard talking about. So, so this was basically collected on different kinds of TV show genres. So this was a good way for us to have things like sitcom, but medical and also crime genres. And there's a lot of daily rich sort of interpersonal activities involved in all these different scenarios. And the pie chart sort of, we also annotated the types of questions across these genres. So there were things like abstract questions, object, action, person-based, location-based, a few small 10% roughly on reasoning, and then also method or how style questions. And then the paper has, I mean, I'll not go into the details of each of these, but the paper also gives comparisons to all the previous useful work on video-based question answering. So in particular, TVQA checked sort of multiple checkpoints in terms of needing both text and video for the question source to reach the answer, also having timestamp annotations, also having longer questions and more amount of data, etc. And then the TVQA follow-up on this also ended up adding spatial bounding boxes inside the frames that contain the answer. So in particular, case, the model would also have to do spatial sort of first temporal grounding checkpoints which part of in terms of needing both video and video for the question source. But instead of just generating the answer or choosing the answer out of multiple choices, also having the model also had to questions and round the more amount of object in the frame. And so then this added an extra follow-up on this also responsibility on the models, right, where you could not just sort of have shortcuts inside in terms of multiple choice frames that contain the answer. So in particular, the model would also have to do essentially, right, where first you do multiple choice checkpoints part of the thing versus generating video for the question source, but instead of just generating the answer. So in this case, the extra responsibility for also showing the answer bounding box allows the models to be more faithful to the answer. Then the next step in this direction was TVR, which was text and video moment retrieval. So the TV sort of acronym I'm using both ways. I mean, it was for TV shows, but also T and V could be text and video. So the basic idea here is that now the output and input have changed. So in this case, you're not given a single clip and a question. You're first of all given thousands or millions of videos in a big video database and a flexible language query. So you have to both first find the video among the thousands or 100,000s of videos that contains the answer to that query, which is the clip. But then inside that video, you have to also find the timestamps. And again, this was one of its first compositional style video moment retrieval datasets, where a lot of the queries needed both information from the video and the subtitle, in the sense that talking on the phone is part of the video, whereas the red parts are from the dialogue subtitles. So this part of the slide I already explained. This is a video corpus moment retrieval VCMR task, where basically you're given a query and a full video corpus with thousands or 100,000s or tens of thousands of videos, and you have to retrieve the matched moment from the full corpus, which means that first you have to retrieve the ground truth video, which is called video retrieval task. And then inside that video, you have to do the moment retrieval, single video moment retrieval task. So again, there's some more details in the paper that I'll refer you to, but the idea was to be able to cover a lot of properties in this data set, which would be things like diverse genres, much bigger number of questions and videos, much bigger vocabulary size, having a reasonable average question length, but also things like needing both video and text in the query context, having timestamp annotations, also the question type being annotated like reasoning versus object detection versus other kinds of questions. And also the fact that these are standalone queries as opposed to some previous works having more just marking sentences inside a big context paragraph or span detection style queries. There's also some other properties that were interesting. So TVR, we have much relatively shorter moments to be discovered by the models as well as longer queries. And then also on average, it has more types of examples which need multiple actions and multiple people involved. So this this slide gives some examples of multiple people and multiple actions being involved in retrieving the query. And then I'll not go into the model details, but this XML model that we proposed for TVR was an interesting starting point, which was a idea where you first get all the clip and query similarity scores. And then when you look at this query clip similarity plot, then you can use an edge detector, a convolutional start end detector style model inspired from edge detectors previous work on being able to find the right edge detection of the start and the end of this similarity plot to do moment retrieval or moment detection. And then recently there's a multilingual version of this coming out at ACL where we have the query and the subtitles in multiple languages. And then there's a starting point model there, which basically promotes sharing parameters and also using multilingual neighbor constraints such that the joint model has fewer parameters but better performance than the monolingual models. So that's what this data set should be able to promote. And then the last example that I'll give for the video and language stream of tasks is something that's more in the direction of trying to predict the next event given a video and dialogue or video and language premise. So the idea here is that you're given a premise event as a video.
Oh yeah, oh maybe a shake.
So this is Mark Wiens, who I'm sort of giving free advertisement here because I follow him a lot, and we ended up collecting data from YouTube blogs and not just TV shows for this data set. And then some of our future data sets are bringing in a lot of news, disasters and protests, and also more real world events from news domains. But the idea here is that you're given this video premise event, not the premise summary. That's just something that we've collected, but the model will not have access to the textual premise summary. And then what the model needs to do is figure out which of these future events on the right side is more likely to happen next. So there's two options here. The green one is the right answer. And we also collected rationales for why one of these is the more likely event than the other, also so as to promote rationale or explanation generation tasks on this data set, and not just, again, choosing the multiple choice answer, which can have shortcuts. But even before using the rationales or making the model generate the rationales or choose the rationales, we tried to have the multiple choices be not that shortcutty in the way. Let me actually show you one more example first. Actually, I didn't explain this example. So in this one, the answer hopefully is clear why it's the B answer and not the A. And the reason is because there are hollowed out watermelon rinds sitting in front of the woman here. So she will pour out the watermelon juice in the rinds and not the cups. So there's some of these are very subtle next event predictions. This one is more from a crime genre example.
I got back to my apartment. That phone was on my doormat. It had a text on it.
And again, in the same theme of our previous works, the video here is always accompanied by video and dialogue text. So the even the next event prediction task, a lot of the examples can only be completed when you use information from both the video and the text in the dialogue, and not just the video alone. And in this case, there's two options. Beckett takes the phone and reads the text, or Beckett picks up the phone and hands it to Dean. So the first option is the correct one, and the rationale is that you don't usually just hand a piece of evidence to a suspect. So you can see how these need a lot of high-level common sense knowledge. And the way we made these options more adversarial is that we use the human and model in the loop adversarial data collection technique called Hamlet, which we did with Facebook in one of our previous papers called ANLI, adversarial NLI. And the idea here is that hopefully most of you are already probably familiar with this, but I'll give a brief summary. The idea is that you want to collect more challenging data, in this case, the multiple choices for the next event, in a way that the annotators, if they write some very easy options that are that have some obvious biases, like someone slapped someone, or they spoke, they said nothing, right? So things that might be obvious that these are definitely not the next likely events. We don't want such easy examples. So what we do is annotators are supposed to write these tricky examples in a way that it can fool a strong baseline model, for example, GPT or Roberta. So they were, when they would write these A and B examples for us, and if a Roberta or GPT style model could already figure out the right answer, we would, with a certain amount of probability, not always, because there has to be a balance. We can't really force them to always give us the most tricky, hardest example. But with a certain probability, we would go back to the annotator and say, hey, can you give us a more tricky example such that this baseline model cannot solve it? And there's multiple rounds of this usually, where then you collect that data and you retrain your model, make the model stronger, and then the Turkers have to give us data for fooling the stronger model. So this is just some statistics on this data set. There's around 30K examples from 10,000 TV show and YouTube blog video clips. And then again, covering different genres: sitcom, medical, crime, travel, food, family, daily. And you can see how each of these covers a pretty wide and different range of actions and verbs. And then in terms of the starting point model, we had a pretty reasonable, strong starting point for the community where it obviously had the usual video feature encoding and all the dialogue and future event encoders, but also some common sense knowledge from atomic style common sense knowledge bases, which are good at predicting next possible events. So the current gap is around models can, with all the modalities, can do around 67 versus 90 to 91 for humans. And some of the recent models that have tried this data set are probably still around 68. So I think that's where maybe some more interesting changes in the common sense knowledge graph side and other things could help here. And then recently, just I guess yesterday, to wrap all this up in some sense for the community, we also did a collaborative effort with Microsoft and Eric also here and several people led by Linji and Jay from UNC, where we've sort of created this value. It's modeled after Glue, but in this case, it's video and language understanding evaluation, where this is around 11 data sets across video question answering, video retrieval, and video captioning. And the idea is that it promotes the community to build general or multitask or transferable video and language models that can do well across all these 11 tasks, and also hopefully generalize and transfer across different types of video and language tasks. So this is live now, and then there's a challenge at ICCV also. Okay, and then the second part for the talk is more from the side of language models and then vision and language pre-training. So here I'll briefly cover a general theme of how do we enhance large-scale pre-trained language models with different methods and types of visual grounding so as to have different kinds of effects, improved language understanding or improved language generation or improved multimodal/embodied tasks. So I cover things like LexMERT and then also some video versions of it, a generative version, a vision to language directional version, and then a maybe cute example on using things end-to-end for a robotic task. So again, like Ray said in his talk, I think this audience is very sort of well-versed with this literature probably, so I'll keep it brief, but everyone has been using BERT. So around 2.5 years ago at this point, we, along with others like Wilbert, we developed LexMERT, where the idea was that instead of doing pre-training from the idea of having the model predict missing or masked tokens in the text, we should also have the vision side of it interacting jointly for multimodal tasks. So the top part of this figure would, instead of just having the text at the bottom, would also have an image where you could do region or positional feature masking for the visual side to get an object relation encoder in addition to the language encoder. And then you would have a cross-modality encoder, which would then be pre-trained on 5-6 different kinds of multimodal or cross-modal pre-training tasks. For example, text and image matching, or text and image question answering, or cross-modal language model masking, and also things like feature regression or label classification version of image classification. So basically, this was a good example of how to use BERT style models for different kinds of multimodal applications. So I'll skip most of this, but back then this got pretty big gains on things like NLVR2 and VQA. And this one was one of my favorites, where this is the WizWiz VQA challenge, where the images are from people who have visual disability. So this is extremely sort of real world images in the sense that, and also because of the visual disability, the objects are several times out of the frame or blurred or only half the image. And so this is originally a crowdsourcing task where the person would take an image and ask a question to get help about their daily activities. But then what if models can help them with certain amount of confidence? So in this case, LexMERT was able to generalize to these kinds of images. And then we have a couple of video extensions of this. So probably not enough time to go into details, but I'm happy to discuss this offline or in the panel. But the idea here is that for video and language pre-training, you would basically have things like video, like the pre-training task would change, right? So you would shuffle the video frames and make the model reorder those, or you would have video and subtitle or ASR caption matching, and then also some other pre-training tasks. So we had two examples of this in the recent conferences. So one was December, where the idea is it's a short form for dense captioning, and also there's a constrained attention loss to basically do two things. One is that the dense captions help you get more grounding regional information, and this becomes as part of the masked language modeling pre-training task in addition to the video text matching. And you also have a constrained attention task here, where the idea is that these ASR captions are usually very misaligned with the timestamps of the video. So can we help a little bit shift and align this focus, where we give the model the captions, not just the one that matches the timestamp of the video, but also the surrounding ones, and we make it focus on the one that exactly aligns to it and give it less focus on the ones that are not aligned to it. So this is basically an easy way to be able to try to shift and align some of the ASR captions better. And then Clipboard is another angle where this uses sparsity for video and language pre-training, where the idea is that most of the video and language pre-training models become very memory and compute intensive if you do end-to-end learning. So the video features are usually fixed and not fine-tuned jointly with the end tasks, and sometimes the domain becomes different or the feature spaces become different. So by using sparsity and only sampling a small set of frames for a clip and then using multiple clips to densely fuse them together, this was a work that showed how you could do end-to-end video and language fine-tuning and get comparable or better performance with much better compute intense models for different kinds of video and language tasks. And then the second last example here is now going into the idea of more unified models. So as I've already shown you probably in my own 3 or 4 last slides, most of these multimodal pre-trained models start becoming very task specific. So across the literature, if you see the hundreds or 200 such papers that have come out in the last 2 or 3 years, you'll probably see that if they are, there are some models that will have a multiple choice VQA style architecture. Some will have a more visual grounding architecture for referring expressions. Some will have a more image captioning style decoder. So the idea of this recent paper that's coming up at ICML, which we called VLT5, as the title says, the idea is unifying vision and language tasks via text generation. So what we did was we basically treated all of these diverse, discriminative, and generative tasks as conditional multimodal text generation. So I think this bottom left side summarizes it maybe for the scope of this talk, that you would have a task prefix here, and then you would have the task text input here, and then the task vision input here. And then the decoder would be an autoregressive text decoder. So examples here would be, if you're doing multimodal language modeling, then the task would be, the task head is called span prediction, and then a dash is dash over fire hydrant, and the decoder has to generate man and jumping. If it's VQA, the task prefix says VQA. What is the man jumping over is the text input, and then obviously the answer in this case is text. But if it's visual grounding or referring expression comprehension, then you would have the task prefix visual grounding, the input referring expression, and then the bounding box number 3 would also be generated as a textual output. And then same for image text matching. That's the task prefix, that's the text input, and then you can have false or true as a text generation output. And so there were 2 advantages of this model. First of all, it was basically able to jointly multitask, train all these 7 or 8 tasks with just one set of parameters. And then the other advantage we showed is that for things like rare category visual question answering answers, this model can generate rare and unseen answers more easily because it's a generative model as opposed to a fixed vocabulary discriminative model. And then this is the last piece where we, instead of using multimodal, cross-modal BERT style models for multimodal tasks, here the idea was more that can we use visual mapping inside BERT to be able to ground it more to what the text in the given task would align to. So the idea is that in BERT, if you are doing the general pre-training task of masking some text and then trying to fill in the blanks, in addition to that, what if BERT, the BERT pre-training task also needs the tokens to map the text to their corresponding visual mappings? So there were two challenges here. One is that, first of all, such visual mappings from text to images, and this was pre-clip era, and in that case, there is MS COCO, right, as the smaller vocabulary and smaller sentence length kind of multimodal data sets. But BERT would rather be trained on things like Wikipedia, which is much more vocabulary, much longer sentences, and aligns to the kinds of language that BERT would be used for in natural language understanding tasks. So that was the first step that we did here, where basically you need to train a vocanizer on MS COCO style data, and then you generate vocans, right, these visual mappings for all of Wikipedia to be able to get a lot more data to pre-train BERT on, right, for this pre-training task of text to vision mapping. And then the second thing that How did was that even when you do Wikipedia, there's very small amount of words that are directly visualizable. So in order to get more words to have vocans, you would also do this mapping contextually, where hence certain words that are not directly mappable to images, but would get their vocans because of the context that they are trained on. So some of the surrounding words would also get vocans because of the contextualization. Okay, so I think I'll finish this here with the sort of simple, cute example I was mentioning. So this is an ICRA 2020 paper where we basically, this was not about a fancy sort of pre-trained multimodal language model. This was more in the other way around, where we said, can we have an end-to-end task where you start all the way from a microphone on a Baxter and you want to do the full end-to-end motion planning of finishing the task demonstration? And the idea was that, can simple language model-based common sense help us complete these incomplete instructions? So the whole point was how to handle incomplete ambiguous instructions. So in this case, if the example is pour me some water, and then there's an environment in front of the robot, which will have several objects. And the idea here would be that you need to understand the language and observe the environment and figure out from where to pour the water and to where to pour it, right? And then eventually, when you infer this through some sort of common sense box, and you figure out it's from bottle to cup and not from plate to scissor, you then conduct the action through motion planning. So the simple common sense reasoning that we did here was that after the microphone, speech recognition and all that, you can do something like predicate argument parsing here for the incomplete instruction, and you get this frame, right? And you know which roles are incomplete. So in this case, the initial location and the destination. And so what you will do is you then have this RGBD image from the Kinect, and then all the environmental objects that are in your environment object list. And then this box, pretty much what it'll do is it'll fill this frame and its incomplete roles with the environment object list and generate sentences from it. So it'll generate sentences using a language model for things like pour me some water from the bottle to the bowl, pour me some water from the plate to the scissors, and so on. And then it's very simple. You can basically use the perplexity of the language model to figure out what would be the most common way in a large corpus to complete the sentence. So that's pretty much what it does. You basically have these incomplete frames, you complete them, you do surface realization to generate sentences, and then you can use the language model to decide the ranking. And then there's some demos that I'll probably not have time for. And then I'll maybe end with some concluding thoughts and just some maybe fodder for the panel and just things to leave you with, which we haven't covered so far, right? And what are some of the next steps? So I think from the first part of the talk, I would say two important things that we need to think about are long distance understanding in videos, right? So it will be extremely challenging for current models to be able to answer things like, why did Ross and Rachel break up, right? Because it needs understanding not just across like certain clips with gaps. Like it's not just multi-moment, multi-hop moment retrieval, but it's also across episodes, right? And across many, many videos. Again, things like the second bullet is something where I mean, if new video and unseen information is coming in, how do we do continual learning of this information, adapt our vocabulary to it from the new videos that are coming in? And then for the second part of the talk, some of the questions would be to brainstorm about strengths versus limitations of just everything being large scale BERT, like SMERT style pre-training. What about structured and modular knowledge versus large scale pre-training? And then for grounding, obviously, we need to go beyond just language and vision. And then the last one would be that the ambiguities for robotic instructions, when we sort of imagine real world ambiguities, these are much longer and there's a lot of scope for interaction and clarifications, which obviously there's some work on. So this is what are some of my concluding thoughts, and thanks again. And obviously thanks to the students who did all the work. Thanks.
Okay, thanks, Mohit. All right, Mohit is here. Okay, and hi, how are you doing?
Yeah, so some of the things were in past tense, obviously. So, but the value challenge obviously happened 30 minutes ago, as opposed to in the future. So, but
yeah, and your hair got longer.
My hair got much longer. But yeah, I'm happy to answer. I mean, there's also a little bit of follow-ups that have happened since then. So just maybe for some quick context. So the Vocanization work that does basically improvement of text-only tasks using visual mappings. There's a new NeurIPS paper coming up called Vidlin KD, which is more of like the video version of it. How can you distill knowledge from videos to improve text tasks? And there we show much more detail of like tasks that need physical common sense, or so Pika or glue diagnostics, and also temporal common sense like Tracy. So it's a little bit more detail of what kinds of knowledge does the Vocanization style visual mapping bring in for text-only tasks. Yeah, Anna, please go ahead.
Hi, Mohit. Great talk again. I was wondering when you mentioned about like long range QA remaining a big issue. I had a kind of a tangential question, I guess. So recently, when reviewing the history of like how video QA has evolved, beginning from movie QA and until recently, we noticed that language-only models have been and remain extremely competitive. So we are still not really leveraging a lot of video information when it comes to, especially, more high-level questions. Do you see any progress in that regard? Like if you actually agree that that's still the case?
Yeah, no, that's definitely still the case, because in even in all the sort of data sets that I was presenting, basically we always try to do human studies of how much is both video and text needed to answer the questions. And that always was much higher than what the models were doing. So humans would tell us that a lot of the data needs videos to be able to find the answer. But then video plus language models are still only maybe a couple of percent points better than language only models. So I mean, so there's two kinds of progresses that maybe we are talking about here, right? One is low-level video features and just better maybe flow and better stereo and all kinds of multi-channel features being brought into the video understanding side. But the other progress that's important is to be able to have these features understand long distance reasoning. And so that's where different and new data sets need to come in, which are forcing models to not take shortcuts for long distance answers. So I mean, a lot of that happens, for example, in NLP, right, where there's a lot of multi-hop question answering data sets and a lot of work on showing how models can still take like shortcuts. So then how can we make that adversarial and force them to not be able to take shortcuts? So maybe some of that. So yeah, so I guess my shorter version of the answer is I think we need both better video level, like low level and multi-channel features, but also we need more sort of long distance forceful supervision for these models these features to learn from.
Thank you.
Mohammed, you have a question?
Hi, Mohit.
Hi.
I do have a question. How much do you think that the progress in video and language is connected to the vision and language grounding, and how much do you think that could be related to end-to-end learning? Because it seems to be a challenging or not so practical to train video and language model. And I think most models just extract features and then learn on top of that. So I wonder what are your thoughts on that? And yeah.
So are you actually, could you rephrase the question maybe once more? So what are the two
I
aspects?
just mean that to my understanding, video and language model, when the pre-training they do the pre-training. For example, VideoBird extract first features from the video, and then and also same thing. Maybe text is live. There's no need for that, and then train a multimodal transformer based on that to try to ground the language to vision. Maybe some of the room where we can improve this video language modeling relates to the ability of words to get to locations in the videos, and maybe this is kind of lacking because we don't have end-to-end video and language models. Like
so I think that's what I was. So I think that's what I was partially telling in the previous question, that in some sense, I mean. So some of these video and language, I mean, there are more advanced versions now, right? I mean, we're like SlowFast and SwingFormer. I mean, there is a lot of good follow-up work on trying to do more advanced video pre-training. We also have a recent work called WIMPAC, where basically we do sort of masked modeling inside videos, and then also do contrastive learning and show that it can specifically do better on temporally heavy tasks and not just spatially heavy tasks. So I think maybe that's what you're getting at, that the goal is on how to end-to-end pre-train these video and language models so that they are forced to do better on temporally heavy tasks. That's what I was mentioning to Anna, that it can't just be features, but also supervision. I mean, if we, for example, pre-train these video and language pre-training models on tasks that need very long distance retrievals, and then combining information from very long distance retrieved clips to be able to come to the answer, right? Then it's sort of easier for the model to make sure that it's able to understand long distance events. But for that, we also need better data.
Thanks, Mohit.
Thanks.
Thanks, Mohit. Are there any other questions from the audience?
Thanks, everyone.
Okay, so maybe we can conclude Mohit's wonderful talk here and let him go. And also next, we will take a short break. You can call it a coffee break, lunch break, or snack break. And then we will come back at 3 p.m. in EST. And then there will be a panel discussion with some of those invited speakers and the organizers, and they followed with a poster highlight. Thank you, everyone.
Welcome back. We are about to kick off our panel discussion, but I think we'll be waiting a couple more minutes until folks can come back, and our speakers in particular. And I wanted to encourage also the organizers to, if you're still around, have your video on, have some semblance of a live conversation between real people. Okay, somebody turned on the YouTube streaming and I can hear myself. That's never a good thing. Could somebody check that they are not? Okay, it's gone. Whew. No, I can still hear it. You know what? It was actually me. I don't know if you could actually hear it. Amazing live streaming feature. Okay, so I see Marcus, I see Andrew. Mohammed is still around, although it's very late. I see Lisa, I don't see Brian. We know that Cordelia will be a couple minutes late. So I think we'll wait a bit more. How are you, Lisa? Let's start with the with the informal part.
Fine. It's just had dinner, so it's dinner time here. How's that? It looks like you're not in California, but it looks sunny as if you were in California, so that's good with your background.
It is.
Oh, very nice.
Yeah. Just,
where is that?
This is the Berkeley Tower.
Okay.
In spring, okay, in spring. So we have this blossoming, I guess, cherry trees there, which blossom. Yeah, but we are in California. We just had lunch. Things are great. So while we are still waiting, hopefully for more speakers to join us, just a few comments. So we have prepared some questions for our speakers and just for general discussion. We might actually even open the floor for people to weigh in on, on these topics. But you are very welcome to post questions. We actually do hope that it will be not just our questions, very biased, obviously, but really more general audience.
Am I the only panelist here right now?
You are. That is correct. So we just heard from Mohit that he unfortunately cannot make it, and we already knew that Alec wasn't able to make it. So we are hoping for Brian and Cordelia to join. I think
if not, I'm happy to share my opinion on language innovation.
on all the topics, of course. So let me see if yeah, I don't think that we heard back from them that they are not making it. So I mean, I expect that they're just running late. Also, a general question to everyone. We are talking the time zones. Is it EST or EDT right now? Because people are confused about whether we are in EST or in EDT. Is it actually EDT? Anybody on the East Coast?
the time zone, which is, I think it's just the standard East Coast time, summertime. So it's Eastern summertime. It's still summertime in the US. So
I think, okay.
Maybe I can start with a question for Lisa. Maybe I missed it during the talk, but did you look at like increasing number of data points from the same data set? And do you think this will sort of, the findings you had will sort of stay constant if you do like 100x or 1000x, like a scale maybe CLIP was trained on, or even larger?
Yeah, that's a good question. So one thing that was hard with the evaluation that we did is we had all of these different data sets that we trained on, and then we looked at what the results were, and then we tried to say, well, given these results, given what we know about the data sets, what can we say? And so one thing that was clear is that it's not just about size, and that you can take a data set like MS COCO, which is much smaller than conceptual captions, and do pretty well. But we didn't do something more controlled, like what if we took conceptual captions and trained on 10, 30, 40% of the data? They do have results on that in Vilbert, where they play around with the percentage of data they play on with conceptual captions. And yeah, you see that the results get better as you increase the data. I think it would be interesting to sort of brainstorm cleaner ways to think about how you could. So for example, one of our hypotheses was language similarity to the downstream task. And there might be a cleaner way to play around with that and try and see if you could get a better intuition. Like, so as I said, what we did is we had all these data sets, and we could say after we had looked at our results, well, these data sets are more similar. Another one is data set noise. So for example, we kind of hypothesized the data set noise mattered, and maybe we could do something a little bit more systematic to get a good feeling how all three of those things kind of interact and play together. Yeah. Did that answer the question? Yeah.
yeah. I guess that's I think sort of an artifact of larger data set sizes potentially, I mean, not necessarily, but would be that they're more diverse eventually.
Mm-hmm.
I mean, at least that what CLIP is partially claiming, that the data set size helps them to do well on a variety of tasks. Albeit not all tasks, of course, because I mean, everything has limitations. But they at least showed that compared to what has done previously, there was sort of a more variety possible, maybe.
Yeah. Yeah, so I guess like the thing that's interesting about CLIP, and it's too bad that Alec couldn't make this because he could probably tell us a lot more details about CLIP than I can. Like the thing that's interesting about CLIP, I think, is that it's a very simple architecture, but it does very well. And so there, I think it's really just, it's eating up a ton of data. And I am curious to know if there's something in like, yeah, I'm curious to sort of know, like, you have this really big, you have all of this data that you're learning from, but you have this simple architecture. Is there something that you can have, maybe a smaller data set that you can understand a little bit better, but still do as well? I don't know. That would be interesting to get a feel for.
Yeah.
So there are some researchers. Sorry. Yeah.
You can go ahead.
Some researchers at UW have actually essentially replicated CLIP, right, on a smaller, I believe, on a subset of this large data set. What's it called? Ooh,
JFT.
What's the name? Right. So on a noise, I think on the cleaned up section of the data set, which the CLIP authors have kind of curated, and I think the general goal was to see whether the similar trends overall hold, but naturally doesn't reach anywhere near the performance that CLIP has, right? So we're talking like a fraction of performance, but we can still study some trends in general, like robustness and other properties, which in general seems to like hold still for these even smaller data sets.
Very cool. Is that something that is published somewhere, or is that something I haven't seen that work?
Yes. There is a GitHub repo, and I believe now it's also on archive. Yeah, and try to look it up later. So I think this probably goes toward the same question that Andrew, you had, right, about some of these interplay between the data scale and the simplicity of the architecture. Is there anything else you want to add or ask?
Well, I think importantly, I wrote that question before Lisa's talk, and then Lisa answered most of it in the talk. But the original question I had for the panel, Lisa, was just about whether data scale is the most important thing rather than architecture design, seeing as you say, these very simple like dual encoder architectures like CLIP and Align are getting such high performance. But you had a few slides dedicated to this with your sort of size of the data on the x-axis and performance on the y-axis. I guess what I'm interested in is, from your talk, the conclusion seemed to be that if you were to scale up a cross-attention architecture to the size of data set that CLIP was, I remember you said in your talk that there's issues with scaling, I guess just because of complexity of training like this, because the cross-attention architectures are so much more costly. I'm really interested in your intuition for what is preventing a cross-attention architecture being scaled up to that data set, and where would the data point be on that graph of one of the architectures that you were playing with on a CLIP-sized data set?
Yeah, so I guess you would hope that it would be, better. You would hope that if you had the better architecture with more data, it would be even better. To give sort of like the specific boring details of why it's hard, or why we had trouble scaling up the multimodal transformer models, is that with the dual encoder architecture, well, this is maybe more about like this. So with like these contrastive style losses, with the dual encoder architecture, you can extract lots of image features and just cache them somewhere, and you can cache lots of text features and cache them. And with the multimodal transformer models, because the text and the language are like talking to each other very early on in the network, you can't do any of the caching that you can do with the dual encoder architectures. So that makes them a bit slower, both in terms of training and then also like in terms of inference. So that was sort of the issue that we were having when we were training the models. I don't know that anybody has, I don't think OpenAI didn't release the CLIP data set, so I guess it was part of JFT, so maybe, anyways, but I haven't actually looked at the data set, so I don't have a good handle for how noisy it is. I do wonder if something happens where, because the dual encoder architecture is very simple, like maybe it actually does better with noisy data sets. So that would be one thing that I'd be kind of curious to explore.
Yeah, there were, similarly on that note, there was that other paper from DeepMind as well, I think called Thinking Fast and Slow, where they sort of tried to do a trade-off between the sort of very expensive cross-attention by distilling the cross-attention architecture, I guess, into a dual encoder, if I remember correctly, to try and get some of this trade-off.
Yeah, that's exactly what they did. So I was not on that paper, but I did a read through for them, and that's the general gist is like you can have the simple architecture really quickly, and then you can use the more intense architecture to try and get the better results.
Yeah, I guess speaking of just the last point on this data point of where the cross attention would be if you trained on such a big data set, I guess my question earlier was sort of cynically directed at maybe there's a lot of data set leakage into these training sets, and perhaps that would mean that performance would kind of saturate independent of the architecture, because the main benefit you're getting is this massive data set leakage.
Yeah, so I know when I was watching Alex talk, I know that he talked a little bit about that. And again, it's a shame he's not here, because I feel like he'd probably be able to say more about it than me. But yeah, I think that's an interesting point. And yeah, as I said in my talk, like I feel like we did put controls in to make sure that we didn't have like any obvious data set leakage. But if you have two images on the web that are very similar to each other, like they're the same image, just one is at a different URL, then the kinds of checks we had wouldn't catch it. So something a little bit more sophisticated would be better.
Yeah, and I think it's important to say, I think the CLIP paper did include some analysis on a data set leakage as well. So there's, they seemed very covered there.
Great, so we can probably keep rolling. So there was an interesting point that was brought up in your talk and also in others about some of the kind of robustness issues in many of the SOTA models, right? We sometimes see them fail on some really simple cases. Sometimes we have these more like natural adversarial examples. Like there was a very cool finding when they attached this iPod on the Apple, and then CLIP model thinks it's an iPod now and not an Apple, which is kind of playing into the strengths and weakness of that model, right? That it can read basically, and so it can be confused by these type of things. But what you specifically pointed out, like verbs or some more fine-grained distinctions, would really be challenging. And it seems that this is really a major issue. As soon as we go out of the academic setting, we will gonna run into all these problems, right? Which gonna probably limit the applications for these things. So general question to Lisa and everyone who wants to weigh in, how do we go about these robustness issues and what is actually going on? And hi, Cordelia.
Hi, I have another talk.
Welcome back.
Just ended now, so that's why I'm late.
Thanks for joining.
Do you want us just to repeat the question again?
Yeah, we are talking about the robustness issues in recent vision and language. I guess not only vision and language, right? This really is a general problem. That there are these natural adversarial examples, that there are also just hard examples, like some people say contrastive sets, or like, examples close to the decision boundary where many models fail. And how do we get into sort of a more realistic assessment of what these models can and cannot do, right? And when they will fail, which will be obviously, which will have implications to deployment of these models. Yeah, any general thoughts or comments? Maybe more specifically, like one example that Lisa had was recognizing verbs, maybe sometimes more challenging than recognizing nouns. Like we see these weakness modes. Yeah.
Yeah, I can attempt to maybe answer with some thoughts. So I feel like one thing that's tricky is that these are all sort of different kinds of failure points. So with verbs, I feel like part of the problem is that well, I don't know, maybe we can argue about this if people disagree with me on this, but I feel like in the language and vision space, even though we say that we're working on language and vision, I feel like we're very noun focused. So we talk a lot about object recognition. Like part of my PhD thesis was on novel object captioning, like a lot of nouns and a lot of objects. And I feel like we don't always think about these other parts of speech, like attributes and verbs, as much as we think about nouns. So I feel like that is kind of a specific failure mode that we have with these kinds of models. But to your other point about like, yeah, and then there's other kinds of robustness issues. And one thing that strikes me is interesting about language and vision in contrast to something like language only models is that in language only models, it's easy to come up with kind of counterfactual examples. So it's easy to try, like, because you can change words, right? So you can go from one sentence to another sentence and change a word and see how that impacts your results. Whereas that's something that seems a lot harder to do in computer vision. And that's not really a good idea of what to do next, but just sort of a thought process in that, like I'm thinking back in, I think it was ACL 2020, the best paper was this paper called Checklists. And the idea was that we're going to write out certain kinds of things that we expect from our models. So if I have a sentiment model, sentiment classifier, and I have the sentence, I'm going to fly to Dallas, and the sentence, I'm going to fly to New York, like both of those sentences we might expect those to have similar sentiment because, somebody's about to go fly to Dallas or New York, like that's exciting, right? But instead what you see is that, changes that shouldn't really change the sentiment. And you can kind of create these tests in a really systematic way because natural language is nice and discrete. With computer vision, I'm not exactly sure how we're going to do that. So like with a data set that we had created for SVO probes, we searched for examples that fit particular criteria. And that was sort of the best we could do. So yeah, it's not really a solution, but just sort of some thoughts about how it's tricky to make sure our models are robust when we're working with images and video.
Yeah, I have maybe one thought. I was thinking maybe the fact that we have been working for, at least for images, for a long time with nouns makes it much more trickier to scale to verbs, right? And we actually, I was just thinking for our work with Epic Kitchen, we actually saw that the verb classification works better than the noun classification. And I think this is because our features are tailored to video, right? So we're kind of hitting the exact opposite drawback that basically we have these features which we have developed for video, and now, yes, it works well for verbs, but it doesn't work so well for nouns. So I think basically somehow our architectures are still very tailored to a specific task, right? And adjectives, nobody has thought about adjectives in a long time, right? So it's kind of very, we're happy if you can solve for verbs and nouns, and I think this is kind of also part of the problem. And obviously what we would want is some generic architecture where we don't design something for each category and then, oh yes, but then we have another one, it doesn't work. But I think that's kind of my vanilla explanation.
It's interesting So you're making this contrast that in video, maybe we are not doing too badly on the verbs actually, but maybe not too good on the nouns. But I wonder if we actually have enough insight into these really like kind of hard, borderline, contrastive scenarios on video with verbs even, to say that, you know, small, subtle, like if you have a video and language task and we are gonna go and say, does the person perhaps hug this other person or are they wrestling? And so even this nuance could be challenging, I think, in the video context. You know, if the models are only forced to distinguish between pretty coarse language labels, have you had any experience, observations sort of on that regard, sort of in this more challenging, maybe hard negatives?
Yeah, I think I would say for videos, the other problem is that the data sets are limited, right? So in order to be able to give you an answer, I need a data set with hugging and wrestling. Otherwise, I can speculate and say things, but basically for now, it's still, the video data sets are still much smaller and much more like in their infancy stadium than the image data set, right? So image data sets, there are loads of them, but nobody has, I mean, there are a few fine-grained data sets, but then nobody has really thought about, I mean, people are already happy if they can train something, and kinetics is like the biggest one. And I guess there maybe, I don't know exactly, nobody really looks at the actions, I must say. It's a bit of a shame, but I guess there may be some of the actions which are close where we could actually see and measure what you're just saying, right? So I don't know. I mean, I don't know. I haven't looked at it at all, but it's a good comment, right? To see when people do start to do this contrastive learning now also for video, so maybe learn from video plus text and things like that. So I think people are just getting there, and then once they're there, maybe we can see. I guess it wouldn't be a problem, right? Because if the features intrinsically and the training objectives, you can make them very close. And that's basically also what I'm saying, probably between the verbs and nouns, you can optimize for the task at hand, right? And then you could probably also optimize for this in the same way as for images, but then maybe something else gets lost, right? So this is more the question, right?
Maybe, I mean, robustness, I think is on the one hand sort of this fine-grained aspect, but I think it also relates for me at least to the aspect which Brian partially mentioned is the case that the model maybe needs to detect if the model can actually solve the task, so that the model is sort of somewhat self-aware about what it's doing, both in the sense of prediction and in the sense of what kind of tasks it can do or cannot do. And then being able to say, well, actually, this is out of my ability, either because I can't do the task or can't do this specific aspect of the task because the video or the language is too hard for me. Yeah, I think that's sort of the other interesting aspect of this robustness.
I wonder if part of the robustness can come back to, so Cordelia, just before you arrived, we were having this discussion of dual encoder versus cross-attention architecture. And I wonder if some of the robustness issues with these big dual encoders could be solved with cross-attention architectures. It seems like the dual encoder and the sort of inherent global pooling that happens in the end, this sort of fine-grained spatial layout information that you would need to be robust to the difference between sort of man in train versus man on train. It seems like those sort of spatial specificities are very reliant on a architecture with earlier fusion than simply late fusion of a global embedding. So maybe the cross-attention architectures could be more robust in that sense.
Why are you saying this? Because the cross-attention between the objects would come up in later, or because everything is based on cross-attention, or I don't know. I don't.
So what I'm thinking is, let's say if we're thinking about robustness between two different sentences and an image, and the sentence is a man in a train and a man on the train. It seems as though for a model to be robust to that sort of fine-grained difference, it needs to find these spatial correspondences between the different words in the sentence and the regions in the image, such that it could tell the difference between man in a train and man on a train, as one would have the sort of, you know, the man on top of the train, you can tell by the spatial layout. I'm sort of making a point that maybe the global pooling at the end of these image and textual encoders for the dual encoder networks sort of loses a lot of the spatial information that you would need to be able to distinguish between these sort of fine-grained differences in text. This is quite a I'd be interested if you guys agree.
Why do you say cross attention would be better, or what do you mean by cross attention to start with? I mean,
so firstly, by cross attention, I guess I just mean the architecture that wouldn't be the dual encoder. There's a sort of earlier fusion when you're. Maybe I can pass over to Lisa for a description of what the cross attention architecture would mean here.
Sure. Yeah. I mean, I guess anything in the Vilbert family of models, where you have the language modality and if you're feeding everything into some sort of a transformer, and the language modality attends to the image modality and vice versa. I did want to just this is at the expense of kind of changing the subject a little bit too much. I was going to say that I actually wonder with the dual encoder architectures, if you're training with a contrastive loss, I wonder if the loss function is actually going to make it hard to do these kinds of tasks where you can say an object is, or the image matches the sentence or not, because in the contrastive loss, you're doing a comparative thing all the time, where you have your positive image and you want your positive image to have a better score than your negative image, but you're not normalizing anything such that you say that your positive image has a score above X and your negative images have a score below X. You're doing this comparative thing. So the model might learn that man in car or man in train versus man out of train, because those both include a man and a train, you would expect it to have a high score, but the score itself is meaningless unless it's contextualized within another example, if that makes sense. But yeah, I'm curious to hear about what Cordelia has to say about all of this. But yeah, that's the thought that I had.
So basically what you're saying as a dual encoder, you mean that's kind of the contrastive loss. You have a feature for the video or image and then a feature for the text, and then you make them close. And basically, given that in and on is very close, you would expect that somehow the content gets lost, right? So basically that's the idea, is that basically in the end it's some pooling, or even if it's not a pooling, the CLS token is also doing some pooling, right? That's what you're saying. Okay, now I'll get your point. So basically, yes, agreed. So basically, if you have the image and you match even the image regions and you match them with the CLS token, somehow it will just highlight everything up, right? And the fine-grained information is lost. That's what you're saying. Yes, I agree with this fully. And so in order to have something better, I mean, you could feed both streams into a transformer, but that's also not the end of the story, right? Because you get some kind of attention maps, we got these attention maps when you have images or videos and audio, but that's also probably not enough to make the difference between on and in a train, right? And if you think of this, it's a good question. Man, in a train, on a train, you would need to single out the in and on and connect the in and out on with some features in the image, right? To be able to say this doesn't correspond, and now I just say it's not on, it's in, right? So that's kind of what you're saying, right? And then obviously your training objectives needs to be also somehow adapted and then focused on the adjectives.
Yeah, I mean oh, sorry.
Yeah, go ahead. Sorry, that was done.
I'm actually wondering if this is so much a problem. I mean, I think there's another question if the representation is fine-grained enough. And maybe the other question is if the computation needs to be conditional. So if the video or visual side representation computation needs to be conditional on the language side, because it's just there's too many variants what could be extracted out of the video. Well, we could represent probably everything. Maybe it needs really to be conditioned on the language side, like in question answering, but like a query can also be a conditional, right? And then, but then it's there's also a counter argument. I think it's not clear to me that this makes it all robust more. I think it maybe gives it more computational power, but it's not clear to make it more robust, especially with transformers, because they have this distributed computation. They're very difficult to understand what is happening. We tried to analyze them, and I think many people tried, but it was always very difficult to sort of understand where the computation actually happens, because it can really happen in a distributed fashion, and at different places and different channels in the network. So it's not so clear that this reduces, really increases robustness. I think it increases the power of the model, but not necessarily sort of the robustness.
Maybe it's a good place to, oh, sorry. Yeah, let's finish this round and then move on.
Yeah, go ahead, go ahead.
I wanted to say maybe the question I had next would kind of really relate to all of that. Like, to what extent do you believe the recent transformer models actually do inherently ground concepts in images and video? And to what extent there is the usual story happening with perhaps memorizing data set shortcuts and whatnot? So I think this question is kind of strongly, and I think to Marcus's point, perhaps, you know, there is one intuition that better grounding may lead to better robustness. So perhaps if we, you know, if we encourage the grounding, we may in the end have the robustness as a benefit.
Yeah, I think the question is, how do we do the grounding? Is because basically just hoping you feed everything into a transformer and it grounds itself is probably not going to work, right? This is kind of the first thing, and you can show that there's some grounding going on, but I mean, otherwise people would already have seen it, right? It's not grounding. It's kind of, you can have this attention heat maps and it shows a bit up, but I think to do grounding, we need to do something additional during training or have some other models, right? I guess that's kind of.
Yeah, I think the whole inspiration for the line of work I presented today was reading some of the multimodal transformer papers and feeling like there were some assertions about learning universal groundings and that sort of thing that I wasn't 100% sure about. So I decided to go investigate for myself. So yeah, I think I think I agree with what has just been said. Like clearly they're learning something because they can do well on these retrieval tasks, and it's not like they're doing performing at chance on these language and vision tasks that we're testing them on. But it's tricky to say that that really means that they're really good at grounding things. I feel like there's a bit more work to go into. We feel really confident in that. And then yeah, and I feel like even grounding itself is a bit of an ambiguous phrase sometimes. So if we're just thinking about the ability to map different parts of language into which region that corresponds into the image, like perhaps for some words the models do an okay job, but I'm not quite convinced that they're universal grounding tools yet. So we'll see.
So we could start like a new direction in our discussion and talk more about video, because I feel like we spend a lot of time about, you know, talking about image and language, but video always gets underloved a little. So there is several questions, and I feel like we could maybe discuss them in parallel, but let me just present the layout. Sort of one question is, why are we still lagging in terms of video and language understanding as opposed to image and language? Do you see that perhaps transformer architecture is finally offering a path where maybe this could be, this gap may be closed, because we are seeing some very promising designs now in video transformers? But then also just generally, like, should we be doing images and video jointly? Should we look into pre-training on both image and video? And another one was, how do we make end-to-end video and language pre-training and modeling just more feasible computationally? And so I think like these three directions, feel free to choose and go in which one you kind of feel. And I can also repeat the 3 points again.
Maybe it was too much. Maybe you should focus on one.
Yeah, maybe you should just pick one and then propose it, because otherwise it's like.
I feel like they're entangled, but okay. So let's just talk about the gap between then the video and the image, and what are your thoughts on transformer models, or any other thoughts that you have about this gap that remains there?
Do you mean the gap in performance between videos and images, or the gap in?
Yeah, I think for the most part, we see, I think, a lot more compelling results and progress in sort of vision and language when it comes to images, but not as much in video. And sort of, I mean, there's clearly some lagging behind in data sets, like you mentioned, data set size is clearly one aspect, but also in terms of modeling, it just seems like maybe we didn't have an architecture that was really suited for temporal reasoning, for contextualized reasoning. So perhaps one intuition is that maybe transformers, like video transformers, are offering a path to maybe bridge that gap.
Because there are some video language modeling efforts around, right? So I'm not sure why you're saying images is much more advanced with respect to the models.
I think we still see, like when we just compare qualitatively results on image tasks and video tasks, I believe we do see some gap, like just metrics. But also, I think we oftentimes see that in the video tasks themselves are not going as far as to make, as to actually contribute to video understanding. So often the tasks themselves are still very much like driven by the progress that happens in the image and language. And so video kind of reflects that, but still doesn't really make that next step. So we've seen today, for example, Andrew talked about the new challenges and others, like maybe going towards more longer range reasoning, which sort of also remains still pretty limited, right? Like perhaps we are slowly catching up, but it's still, I think, 1-2 steps behind.
Yeah, for me, like the data set problem is really a big problem, right? We have been wanting to work on this more longer range video problems for a long time, and then you go to the data sets and they're all like 3-5 seconds long, and the longer ones are bad. So then basically you need to collect your own data sets, and the same thing for spatial temporal localization. I mean, we collected the AVA data set, and I would say there's still a lot of problems with it. And like now, basically, I think it's just more complex, right? The whole thing is much more complex to collect the data. I would say for me, it's not so much the modeling. I think the modeling have a pretty good grasp, but then all the data set issues are really, really very big, right? And I guess also the compute, right? Because you have this huge data sets, and you don't have them, but even if you had them, nobody could really compute on them. And so basically that's kind of slowing down the progress also a lot. And even images, I mean, even if you think of like annotations and everything, there's like a lot more annotations. I mean, you have the open image data set, you have contextual captions, you have a lot of data sets which are quite well annotated, while for videos, I mean, we're really not there yet, right? So I guess that's, and then maybe if you had the video data sets, then the modeling would follow, or then you could really develop models. But right now, without data sets, I mean, there's things which we can just not do, or we need to do it. We need to scale it up in a very weakly supervised way, which makes it even harder. If it's possible, but we have to really maybe think of, we don't want to do things anymore supervisedly. We have to do it completely unsupervisedly, or where can you get the data in some unsupervised way? Kind of, I think that's for me, that's kind of the drawback.
Would you wanna throw a number out there, like how large should data set be, so that we could start talking about video and language? Like what scale do you think will be sufficient? As you said, the modeling will follow.
Oh, I don't know if it's the scale or the type of annotations. I guess, for example, I mean, like objects. I mean, there's, for example, Epic Kitchens. That's kind of something where we're kind of going to look into more detail, where we have the hands, the object, the action. So you can maybe have a more, maybe this is quite restricted, but for this very fine grained scenario, have quite a lot of annotations. And maybe that's more, it's not so much the quantity. I think quantity pre-training we can do, but more like the quality. And then also, I guess, Epic Kitchen would be something where we could really measure what you asked about, this fine grained, like, are we making a difference between cutting a tomato, cutting a cucumber, cutting a banana? How do we actually set it up? What are the problems? I think this is maybe something where the annotations are good enough that we can really make progress, or at least, I mean, yeah, there's still a few problems because data set is too small, but I think these things we can actually handle, like with regularization and pre-training. I think this is handleable. Maybe this is like one thing to start, or look at similar categories, say in kinetics, and then see why they're confused, or if they're confused, right? It's also something people haven't actually looked at that much. So I think, and then maybe going towards automatic collection, right? That you kind of see, like for the how to 1 million data set, for example, people, they use the labels, but then maybe kind of think of ways of cleaning it up more, I guess. But all these things are super large scale, like even at the Google scale, it's like large scale, right? And so I'm kind of thinking this really holds back somehow the progress that you cannot just experiment so easily. And that it's really always some major effort, right? And you have to really make sure that you're compute efficient and right, because the video is like, if you compare for 1 hour of video, I don't know, it's comparable to all whatever image data set which is around if you compute things on every frame, right? So, and I think that's also a big problem, right?
Maybe it's quite an. Oh, sorry, Cordy, did I interrupt you? Go on.
No, I'm done. Thank you.
Oh, I was going to say maybe quite an obvious point. It seems like a problem you don't need to deal with image caption data sets is the sort of correspondence, well, somewhat is the correspondence between the caption and the images. I know there will still be a lot of noise, but it seems like a huge problem that you introduce when the captions may not be aligned temporally with the frame that they are originally paired with. And so there's a ton of work on the how to 100 million data set of trying to solve an alignment task there. And maybe that's the sort of inherent noise that is present in all video caption data sets that provides more of a hurdle than for image caption.
Yeah, I don't know, the alignment is maybe not the toughest problem, but it's just the problems probably just add up, right? I guess that's really what's.
Will we see clip for video and language soon? That's what I'm asking myself.
There's probably already an archive out there.
Yeah, there's some attempts, right?
Yeah, there are loads. Yeah.
But
I guess this, again,
the scale is the real issue.
I think there was a video clip paper that came out of FAIR not too long ago, maybe a few weeks ago. So called Video Clip.
So
yeah, I don't know, I haven't seen the paper. What are the results? Are they clip for clip, right? Where they use clip as initialization and then scale it up for video to text retrieval. It's clip for clip and clip for clip.
There are loads. So there's sort of clip for clip, and there are some that do some sort of transformer pooling of the clip features. But this paper Video Clip was actually directed on the how to 100 million data set. I don't know the results off the top of my head, Cordelia. I'll find the paper and I'll put it in the chat.
There was a funny confusion. One of the earlier papers, I think maybe it was actually from Mohit, was the title also like video clip, actually didn't use clip. And it was just like a video clip literally used as the word clip. And I think it was clipboard actually. And then everybody was like, whoa, how did they have a paper with clip before clip even happened?
Yeah.
So now it's very confusing to see lots of papers with clip in the title and then clipboard, which doesn't use clip.
Yeah, right. And you have to look also what are the details, right? And what is, again,
sometimes you have to read the paper.
This large scale pre-training, but I guess you could do it for videos, right? It's more, maybe more the data also, which is not as good as for images. I don't know, to be seen, right? Actually, it's an interesting question to see if it's the data or the training, because otherwise it's kind of straightforward to scale up, right? I mean, there's nothing which prevents you to scaling clip up to videos from a methodological point of view.
Mohammed, you had a question? I think we interrupted you.
Yes, so I think we have seen in video development in the video convolutional encoders for videos. We have seen development in addressing problems like spatial redundancy. Like I think one example is octave convolutions, among others. But in the context of transformers, how do you think we shall like address this issue of spatial temporal redundancy in connection to language? How to make, maybe if we have a grid of words, W times H times W times T, where T is time dimension, how do we model that more efficiently with sentences so that we have more grounded video language models?
I think that's a good question. I don't have a great answer for it, so I don't know if I can answer that. Yeah, I also have not worked with video for a long time, so yeah, I feel like perhaps defer to Cordelia on video things. But yeah, I feel like that kind of is the sort of the issue, right? We already have like the multimodal transformers in comparison to the dual encoder architectures are already a lot more compute heavy. Now we're going to take video, which is more compute heavy, and that can be quite tricky. Yeah.
I guess compute is a large issue, right? I mean,
so one thing I'm curious about from people who work with video, it feels like there are some things that we can learn fairly well from images, like we can learn like object names and that sort of thing fairly well from images. And it seems like maybe we shouldn't try and learn that when we're learning with video. Maybe we should try and say, okay, with the images we can learn this set of things, and let's not waste time relearning how to do that with video. And I feel like people have already done that. Like I am remembering some of your older papers, Anya, where you had the video description and you did things like, I think you did things like object detection and that kind of stuff in the video processing. So I think people have already done that, but I'm just curious to know, like, do we really need to have an end-to-end video language model to be happy? Or if we had a model where we borrowed heavily from image and language first, would that also be satisfying, and would that work, and would that help?
I don't know. I think my take would be that for doing video understanding, we need clearly lots of different capabilities, right? And sort of static image representation is definitely one of those skills. Like if you think about some of the works on this like mixture of experts, right? Where there is like a 2D expert, a 3D expert, maybe some additional expert like OCR expert and whatnot, you could clearly see that 2D representation, that powerful, something like Clip, could be a powerful expert, right? But then you would still need a 3D expert to add additional skills about understanding actions, which I think Clip, for example, would be lacking, or other 2D models will be lacking. So I'm sort of, I kind of tend to believe into these experts that might, each, like you said, there's no real need to replicate that effort in video, as we already could leverage the powerful 2D representation. Cordelia, are you talking? I think you're muted.
Yes, sorry, I had some issues. I tried to open the archive paper in parallel to the Zoom meeting and it just crashed. Yeah, I was saying this is actually what we're doing, right? For all these vivid features, we're already pre-training, we're already using the image features as input, right? It's either trained on ImageNet, or the largest model was actually trained on JFT, which is this large scale Google internal data set. So I think this is clearly something, maybe this is actually what you're saying is actually the way forward, that we kind of rely more on everything we have from images as initialization to kind of get us unstuck, right? And that we don't claim we need to pre-train everything from scratch, but that we can actually reuse what has been done and then just build up on it. Maybe not even, it doesn't need to be necessarily an expert, right? You can just say, what we initialized our models with the image features, and then basically we just build up on top of this. And this is actually maybe what you're also saying, use Clip or whatever for video Clip, or use some object detectors to pre-detect regions or something like this. And this might be, and this probably this needs to be done in an end-to-end trainable way, right? That you kind of have, you don't fix things too early on, but you kind of inject the knowledge and then continue training. I think that's kind of what I would say, right? And from what we have seen, that's something which works.
Do you have additional comments to video? And then otherwise we could move on and spend the remaining time discussing some other interesting or philosophical questions. Right. So I guess one one interesting thing we see these days, there is lots of new tasks showing up in the vision and language field. You probably have seen a number of data sets on, on common sense reasoning, visual common sense. A lot of that is coming from Yejin Choi, actually, and others in the field. Do you believe that we are actually, as a field, quite kind of ripe and ready to go for these tasks and start really pushing for these common sense tasks? Or do you think that maybe these models are really not quite capable of actually exhibiting the common sense reasoning skills?
I can try and answer. So I haven't actually looked at the common sense data sets too much beyond just like reading the papers. I haven't played around with them. So I should preface my response with that. And I guess I kind of feel like the way that research sort of happens a lot of times is you have a data set or you have a data set that's proposed, people start thinking about the task. And then what happens is people find all the problems with the data set and the task as you posed it. But it's not that the original task was bad or not worthwhile, because you wouldn't have thought about all of those issues until you started working on it. So for example, I think VQA is a great example of this, right? So VQA data set was released in like 2015, right? And then people started working on it. They realized all of these issues with it. VQA version 2 was released. Aishwarya has her compositional VQA. I can't remember the exact name, but this other kind of brand of VQA. So I think if there's a hard task and somebody creates a data set and we start tackling it, like at the very least, what we're going to learn, we might at the very end, like the worst that happens is we get to the answer to your question, Anya, like, is this reasonable at all? And it's possible that we spend some time on it and realize that, you know what, actually, we're so far behind, we need to work on some other things. So I feel like kind of a cop-out in terms of an answer. We'll gain something useless, we'll gain something useful no matter what. So perhaps it's okay if we're not quite ready yet.
We'll add it. We'll add it to the recording. I'm just kidding.
I mean, maybe the other aspect is also that even if our current models are not ready, that doesn't mean that that's not an inspiration point for people to think about how to model those tasks. Right? I mean, I think new data set, new challenges help people to come up with new models, new ways to think about it. And yeah, I mean, for example, when ImageNet started, it was models weren't really ready for it in many senses that didn't really work at all, but it led to like a big advancement later on.
Yeah, and I guess the common sense reasoning data sets are interesting, but the question is, what do we really learn from them, right? And for VQA, it's also not clear how much we learned, right? It's kind of a nice task, it's interesting, but then is it really, I don't know, did it really move forward that much? I mean, the models are quite similar, they're kind of variant. So I guess the question is, I mean, it would be worth it if we really learned something completely new, right? Or at least like transformative, but that's kind of maybe not the case, right?
I think maybe an example of what may be viewed as a successful demonstration of common sense is what we see in some of the GPT-powered like blocks, when people basically use GPT, right, and managed to fool an entire forum or community to think that this was actually a real person communicating and sharing opinions and commenting, and sharing experiences and basically prompting others to share, which really showed the power of some of these large-scale models to believe that these are, they definitely passed the Turing test in there. But I guess maybe when it comes to multimodal settings, it's still very easy to poke at them and they break. And sort of like, I guess we could easily find those brittle points, because the grounding, again, I think is one of the issues that needs more work.
Yeah, so I guess I hear that you're always saying that we need more grounding, right? And this is probably very true.
That's just me. Maybe one last question. I guess we are approaching the end of the hour, and I have to pick a really great question for you. Let me see what we have here. Maybe what kinds of works would you love to see more in the field? What is missing? What is underrepresented? Where would you, if you had a choice, where the field should be moving? Do you have some several maybe pointers?
You mean with respect to vision and language, I guess, right? That's kind of...
Sure, yeah, as we are vision and language workshop today. If you want to really, if you're passionate about other things.
It is the grounding, actually. No, I think for me, it's the grounding, right? I mean, I think for me, it's also the thing which is missing, that we kind of don't have a good understanding of the objects or the relations, right? I mean, every time I worked on relations in the past, it's also always very tedious and like frustrating and like feels like incremental and not something where you can really say, oh, I made progress. Like not like whatever you have a new feature, it works, and always like it works for a few cases and then it crashes. And I guess this in the train and on the train is actually a good example. And maybe these things we should go back more and rethink. I mean, maybe rethinking these relations, but again, there's these data sets, they were also quite buggy and quite bad. So I mean, but I think this might be something, grounding with relations might be something, and then going more towards objects. I think this would be, for me, this is maybe something where people don't look at enough, and maybe they don't do it because like you always have to beat the numbers on the benchmarks, and if you do something maybe along these lines, it's really hard. I mean, like say for VQA, if you have the objects grounded, performance might drop and then nobody will like your approach, right? So that's maybe one thing where we could actually see more of, I don't know, maybe as an idea.
Yeah, I think I'll have sort of a similar answer from what you're saying at the end there. I guess probably unsurprising to people that saw the talk I gave, I really like things that are looking at trying to understand what exactly it is that's making our models work and why our models are working. And it's always good to have a benchmark to make sure you're making real progress, but then digging in and understanding why is it that you're actually doing better on the benchmark. Like what is it exactly that the model has learned that makes your model better than another model? Like those kinds of questions, and thinking with that kind of like an analytical sort of hat on, trying to really dig into what's happening, I feel like is a good way to make sure you're actually making real progress and not just exploiting some spurious correlation in your bad relation data set or whatever data set it is that you're working with.
Mm-hmm.
Not to open a can of worms, but just a comment to that. I think our community is way more receptive to new architectures than to analysis papers, which is unfortunate. And when I see analysis papers, I often hear people say, well, so what's your solution to all the problems in the world? Yes.
Yeah, and then people come up with an architecture, the gate is 2% and everybody's happy, right? It's kind of, I mean, this is kind of what he's saying, and it's also not that great, right? Because it's not that much of a difference. So yeah, I agree.
That's why we have to make sure at the workshop panel we advocate for this. So next time when people are reviewing papers, they're thinking a little bit more about it.
Yeah, no, there has to be some cultural shift, I guess, beyond just computer vision in general, to not reject papers just because of novelty, and not to accept papers just because of novel architectures, but to kind of look at the bigger picture, what moves the field actually forward.
Mm-hmm. Yeah, I'll have both types of papers, right? I mean, it's not about rejecting one, but it's more like being a bit more tolerant towards things which are maybe more innovative. But it's hard, right? Because it's always very hard to understand what's the best way forward. But
do we have any final comments? Andrew, please.
Oh, I was just going to say there was an interesting post from SIGGRAPH to its reviewers, I think, which said that you should be reviewing papers mainly based upon what will prompt more future work as your main point of as your main metric rather than percentage points novelty. I thought that was quite a nice way of unifying a lot of things.
I don't see questions in the chat. Did I miss any? I don't think so. And I don't see questions in the live stream. And with that, I think we'll probably be wrapping up. And thanks so much for joining. We had a somewhat limited panel today because many speakers unfortunately couldn't make it to the panel. So we're very grateful to Lisa and Cordelia for making it. Thank you so much. I think it was really fun conversation. And hopefully in person next time. Thank you.
Hope to see you sometime in person, right?
Thank you for moderating, Anya.
Bye.
Sure. Bye. And everybody else will be switching gears, I believe, to the spotlights shortly. Oops, I accidentally muted. So the plan is that we'll be playing these 2-minute spotlights. And after that, hopefully we have the authors actually present in the meeting so we could have some live Q&A session. And after that, we have the poster session in Gatherly, which I hope that most of you or all of you have already seen that you can access from the virtual ICCV website. So there is a Gatherly link in there. So we'll move there once the live, so this part of the event is over. And so, okay, I see some chat comments. Okay. All right. So let me know. Okay, so I guess I should probably check that I'm sharing my audio. Let me reset this and make sure I share sound. Now let's give this a test first.
Thank you for watching this video. My name is Taijin.
Any confirmation that people can hear? Yes,
yep.
Nodding. Okay, I think this thing is a bit finicky, so I have to restart.
Thank you for watching this video. My name is Taijin Shimura, a PhD student at Kyoto University. Today, we would like to show our work entitled Egocentric Biochemical Video and Language Dataset. Science is facing the reproducibility crisis. More than 80% of researchers said that they cannot reproduce other experiments in the biochemical domain. Vision and language techniques break through this problem. For example, if we build an alignment model, researchers can learn how to achieve the experiments by watching an automatically created alignment of experimental video and protocol instructions. To achieve this, we created biochemical video and language dataset, which consists of 16 experimental videos from 4 protocols: PCR, DNA extraction, mini-prep, and making anoscale. We manually created alignment between events in the video and instruction in the protocols. In experiment, we employ 2 state-of-the-art video and language models. It is infeasible to train a D model from scratch due to the limited dataset size. Therefore, we propose a zero-shot aligner using the pre-trained models. This zero-shot aligner outputs the best alignment using the dynamic programming. In experiment, we compute mean IOU for evaluating alignment. We use uniform baseline for experiment. Results show that there is large room for performance improvement. We can observe that the predicted events are largely different from the ground truth events. Our contribution are create a novel biochemical video and language set and conduct alignment experiments on zero-shot settings. Our future work is to increase the dataset size for trying machine learning methods and do experiment on the few shot settings. Thank you for watching this video.
Today I'm going to present our new work, CIGLI, Conditional Image Generation from Language and Image. This is a joint work with Lynette, Jared, and Hao from Carnegie Mellon University. First, the motivation of this work. The classic text-to-image generation is very simple, as shown in the right part of the slide. Given the text input, we want to generate the image, but it has some limitations. For example, the source of information is limited to the text. But is it possible that we can define a problem such that the model requires both text and image to accomplish the task? In our paper, we define the problem such that given a text prompt and an image, the system is asked to generate the second image, as shown in the bottom part of this slide. There are 4 examples, 2 showing the correct examples and another 2 showing the examples that are not valid. We construct the dataset from the NLVR2 dataset, which is a visual reasoning dataset between 2 images and 1 text prompt. And then we further filter out the dataset. So the baseline model is first converts the image to the caption using the image captioning model, and then concatenate the 2 sentences and convert the task to text-to-image generation. And in our task, our model is shown in the bottom part of this slide. We did both the automatic evaluation and the human evaluation, and the results showing that our model outperforms baseline models in both automatic evaluation and also the human evaluation.
Hello, I'm UNN. This talk is about the paper Semi-Autoregressive Transformer for Image Captioning. As we know, the autoregressive image captioning model, AIC, generates a caption word by word. Though the generated captions are of high quality, the speed of inference is slow. In contrast, the non-autoregressive image captioning model, NAIC, outputs all words in parallel. Though the speed of inference is fast, the quality of generated captions is inferior. The introduced semi-autoregressive image captioning model, SAIC, falls in between, which keeps the autoregressive property in global but outputs words parallelly in local. It makes a good trade-off between speed and quality of generated captions. This is the illustration of transformer-based semi-autoregressive image captioning model, SATIC, which composes of an encoder and a decoder. Based on the original transformer architecture, there are only a few modifications needed to implement SATIC, such as replacing the original lower triangular matrix mask with a relaxed one. Here we list 2 merits of the SATIC model. First, based on transformer, there are only a few modifications needed to implement SATIC. Second, SATIC can directly inherit the mature training paradigm of autoregressive captioning models and get the speed-up benefit of non-autoregressive captioning models. This page shows part experimental results. The upper unit is autoregressive models, the middle unit is non-autoregressive models, and the bottom unit is partially non-autoregressive models. The PNAIC is a similar work. Though it can also achieve a good trade-off between quality and speed, the training of this model is somewhat tricky because it must need to incorporate curriculum learning-based training tasks of group length prediction and invalid group deletion. In contrast, our SATIC can achieve a good trade-off between quality and speed with an easier training paradigm. For more ablation studies, please refer to the following paper. Our code is available at GitHub. Thanks for your time.
Hello, my name is Zixu Wang. I'm going to present our paper, Latent Variable Models for Visual Question Answering. In this paper, we propose latent variable models for VQA, where vector information, captions, and answer categories are incorporated as latent variables. First, we extract the caption features by a caption encoder. We employ a continuous latent distribution to be the caption representations, which is modeled as a variational distribution. We then build a generative distribution conditioning on image and question pairs. Then the KL divergence between the generative and variational distribution is minimized during training. During testing, we use the generative distribution, which is conditioned on image and questions only for answer prediction, where the generative distribution has been regularized by the variational distribution containing captions information.
We then trained an answer category classifier using image question pairs as the input, given the ground truth answer category labels as the target. We then used the predicted category distribution to modify the answer distribution through element-wise production to get more precise answer distribution. The results in Table 1 show that our latent variable model outperforms two strong baseline models, bottom-up top-down model, the strong baseline model for VQA, and another VL-BERT, a pre-trained visual language framework evaluated on VQA. In Table 2, our ablation study investigates the effect of each component, the caption and answer category. Our model can get reasonable improvements with captions or answer categories. The improvement of combined strategy indicates that the benefits from the two latent variables are complementary. Thank you for listening.
Hi everyone, I will present the poster What You Say Is Not What You Do, Studying Visual Linguistic Models for TV Series Summarization. The context. General visual linguistic pre-trained models are said to be task agnostic, but they are created for and tested on tasks where the information between language and vision is redundant. The text reflects what is going on visually. We can see that in the two examples below, from COCO captions and conceptual captions, two widely used pre-training datasets. The problem is, for a variety of tasks, such as TV series summarization, the dialogue does not say what is happening visually, and vice versa, but both information are essential to the task. In the example below, we can see that the important information is sometimes in the image, a person lying on the ground, sometimes in the dialogue, someone admitting what they did, or a combination of both. So, for such a task, where the two modalities convey complementarity aspect of meaning, can we use general visual linguistic pre-trained models, and how? To answer this question, we designed a study. We have screenplays that contain both scenic information and dialogue, which are respectively paired and unpaired with visual content. The goal is to compare pre-training strategies for both types of inputs. In text inputs, we have three configurations: dialogue, scenic information, and all text. For the pre-training strategies, we have no pre-training, COCO captions, conceptual captions, or multimodal IMDb, a dataset with synopsis and poster images. For models, we used VisualBERT and VL-BERT. Our results suggest that it is possible to obtain results that are close to the state of the art with a general model. The dialogue text can benefit from visual linguistic architectures and from non-aligned pre-training. Thanks for your attention, and I hope to see you at the poster session.
Hi everyone, I'm Yusuke Hirota from Osaka University. VQA is a task to answer questions about an image's visual content. For the image representation for VQA, deep visual features extracted by object recognition models have been used as a de facto standard. However, the deep visual features may present some limitations to capture the rich semantic content from a picture. Within this context, we think descriptive text may be a good alternative for image representation. So, in this work, we explore the effectiveness of textual representation of images. Specifically, we conduct VQA experiments by representing images using text instead of deep visual features. The image descriptions are the combination of COCO captions and localized narratives. For the VQA model, we use transformer language model. Besides, with the success of data augmentation for VQA, we investigate the use of data augmentation for descriptions. We adopt data augmentation techniques for VQA to a language-only input setting. We also apply existing popular NLP data augmentation techniques to image descriptions and questions. Evaluation of proposed data augmentation techniques shows the effectiveness of them. Especially, back translation for questions has by far the best results. Comparison against deep visual feature-based models shows textual representations of images are competitive with deep visual features. Thank you for listening.
Hello everyone, this is my honor to be here to present this work, which is entitled Language-Guided Multimodal Fusion for Video Action Recognition. And I'm Zhenhao Xiao, and this work is co-authored by Yikang Li and Chumen Ho, and we are from Oppo US Research Center. The explosive growth in video and its applications has drawn considerable interest in video action recognition research based on multimodal method. However, the end-to-end training of multimodal video action recognition is non-trivial, because in theory, a multimodal classifier should always outperform the best unimodal classifier, but in practice, we often observe the opposite. The main cause for this performance drop could be due to several reasons. First, conventional training methods such as late feature fusion provides a pool of modality fusion mechanism. Second, multimodal network is much more data hungry because of its complex weight space than the single model network. To address the above challenges, first we propose a bi-modal video encoder to better fuse the multimodal signals. The bimodal video encoder uses a bidirectional attention layer to link different clips, and also use a cross-attention layer to integrate different modalities. And the second idea is that we propose to use a language-guided constructive learning to relax the limitation of data scarcity and learn directly from the vast amount of videos with no text on the internet instead of the traditional class categories. We compare our method with other multimodal and also single model methods, and the result here shows the accuracy improvement brought by our method. So, in summary, in this work, the proposed language-guided multimodal fusion methods successfully close the loop between the vision and language, and the method largely improved the accuracy of video action recognition by the proposed language-guided constructive learning strategy. So, for more details, please refer to our paper. Thank you.
Hi, I am Deniz. I am a PhD student at India, collaborating with Intel Digital. I am presenting our paper on the hidden treasure of dialogue in video question answering. Our goal is knowledge-based video question answering on TV shows. Recent works rely on human-generated external sources. Instead of using human-generated sources, we only use automatically generated knowledge. To better understand knowledge-based video question answering, I will give you an example from the NovaTV dataset. An episode contains multiple scenes along with associated question. Here is the one scene with its question. The scene contains a discussion about a robot competition. The question is asking the robot's name. This cannot be answered only from the given scene because the robot's name is not mentioned. This is another scene from the same episode. Sheldon says their robot's name is Monty. By using this scene, the question can be answered. This indicates that a high-level understanding of the whole episode is required for knowledge-based video question answering, while external knowledge may not be necessary. We propose to use scene dialogue summarization to generate scene summaries. This is the summary for the first scene, and this is for the second one. We obtain the entire dialogue summary by combining scene dialogue summaries. We can answer the question by using episode dialogue summary as an input for the video query method. In this way, human annotated knowledge is replaced by this automatically generated episode summary. This is the first time dialogue summarization is applied to video question answer. Here is the order of the proposed method. First, we convert inputs to plain text description. Converted inputs are processed independently in streams, along with the question and each answer. Then, for each stream, we produce a score per an answer. We use BERT model for stream training. Finally, stream embeddings are fused, and a prediction is made. This plot shows question answering accuracy for different question types, along with overall accuracy. Our method outperforms the state-of-art on the NovaTV dataset by a large margin for all question types, without using question-specific human annotation or human-made pilot summaries. If you are interested, please visit our project page. Thank you.
Hello, My name is John Cadigan, and I will be describing resilient data augmentation approaches to multimodal verification in the news domain. In this work, we demonstrate the resiliency of two data augmentation approaches with state-of-the-art results against manipulations specifically designed to thwart the exact multimodal embeddings we are using as the basis for all our multimodal features from the news clippings dataset. Here's an overview of the system. It receives an image and caption. It disambiguates the entities in the caption, such as Jones to Terry Jones, the Monty Python actor. It then compares extra data associated with each detected entity to the image in order to verify it with a model by using clip to embed everything into the same space. Entity linking allows the first method of data augmentation to create more features for our model. In addition to the base clip score, we compare entity strings to the image in a zero-shot style application of clip. We also compare images to images. Cross-domain similarity local scaling is the second method of data augmentation, which uses the images and captions remaining from the visual news set unused by news clippings. For a reference image, we calculate the average cosine similarity with its neighboring captions, vice versa for a caption. We then compare the reference image caption similarity with the average of the neighborhood. The intuition is that some regions of the manifold are denser than others, needing higher or lower contrast. Here are the results. We have complementary gains from each method, which helps us achieve 3% higher accuracy than a fine-tuning approach alone. I'd like to thank you for listening and DARPA for funding this research.
This is a summary of our contributions. First of all, we introduce the study of a new problem. We provide two new benchmarks to aid the study of this problem. We introduce two novel yet simple approaches for solving this problem. And finally, we provide new evaluation algorithms better suited for measuring the performance on long-tail datasets. In this paper, we make the first large-scale study concerning the task of long-tail visual relationship recognition, dubbed LTVRR. In this setup, the subject, relationship, and object classes each follow a long-tail distribution. We also study this problem on a much larger scale than have previously been done. To begin our study, we introduce two LTVRR-focused benchmarks. First, GQALT. GQALT is built upon the GQA dataset. We perform some filtration on the data to better fit the LTVRR setup. We can see the long-tail distribution of the dataset on the right. Second, VG8K. VG8K is built upon the widely used visual genome dataset. We filter the data to create a smaller version of visual genome dubbed VG8K that still retains the long-tail aspect of the original dataset, as can be seen on the right, while being more manageable. Here's our approach. Using the standard classification low entropy loss on its own tends to heavily favor head classes at the expense of tail classes. The visual linguistic hubless mini-batch level loss, dubbed VilHub, is inspired by the bilingual lexical induction literature in NLP. VilHub loss encourages high entropy predictions across the mini-batch, which helps the tail classes. To further refine the results, we created a relationship mix-up augmentation strategy dubbed RelMix, inspired by manifold mix-up. 3 triplets are selected from the image, 2 from the tail and 1 from the head. We combine them in a strategic manner to enforce the presence of tail features in the augmented triplet. Here are some quantitative results of the VilHub loss. As we increase the weight assigned to the VilHub loss, we can see the performance improving on the medium and few shot classes. We created a challenge to encourage further research in this area. You can learn more on the challenge website below. For more details, please visit the project page. Thank you for your time.
Hi, I'm Shamil, and I'm excited to share our work on neural event semantics for grounded language understanding. Our work is about understanding language in visually grounded contexts, about events and images. Traditional neural networks have been successful at modeling language and vision together, but they still suffer from limitations to generalization. Consider this picture of some simple shapes, and some language grounded in this image. A red circle is above a green square. A model should say that this statement is true for this image. But if these events, red circles and green squares, were specifically unseen combinations of colors and shapes during training, it'll have a hard time generalizing compositionally. Recent work, such as neural module networks, address this by using the structure of language to predict a layout of a series of nested processing steps. Here, words are functions, and semantic composition is function composition. This functionist structural layout can be challenging to learn, often requiring low-level ground truth supervision and reinforcement learning techniques. In our work, we revisit this fundamental idea by changing the underlying semantics foundation to improve learnability and generalizability. We propose Neural Event Semantics, or NES, a new framework for compositional grounded language understanding. We design NES by generalizing key elements of conjunctivist event semantics. In NES, all words are event classifiers, whose score is composed by multiplication. Instead of a functionist layout, compositional structure is determined by routing event inputs with an attention operation to words based on language context. NES is end-to-end differentiable and learns interpretable word-level classifiers without any low-level ground truth supervision. And NES improves generalization on both synthetic and human-generated grounded language benchmarks. For more, please visit our project website. Thank you.
Hi everyone, I am Digbala and I will be presenting our work on understanding of emotion perception from art. The evoked emotion in viewers from an artwork is highly subjective, and it has been studied in the domain of neuroscience through a combination of fMRI and behavior analysis. In case of computational domain, artwork from WikiArt has been annotated for emotions and explanations of why certain people feel these emotions. To truly understand an artwork, we would require image-centric affective cues and the associated explanations. If the explanations are just used here, a text classifier predicts sadness, but if the image content is taken into context, then the feeling that one would get is of containment. Now we propose multimodal model adaptations based on dual stream and single stream models. For dual stream, we look at early fusion and weighted late fusion models. For single stream models, we focus on MMBT with the possibility of configuring it for image-based features. We show our results on the Artemis dataset with the same splits as the original paper. For the image-based features, we consider bottom-up and wheel features of top 50 salient regions. For the text part, we consider 768 dimension representations in pre-trained BERT model. We compare our results with fine-tuned BERT-based text classifier and fine-tuned image-only classifiers based on VG16 and ResNet 50. In case of visualizations, we show that MMBT improves upon overtly positive and negative classes. Also, we show GradCam visualizations for certain correct regions associated with correct predictions. For MMBT, we show the top 3 image regions in terms of gradient-based attributions for correctly predicted class. So in summary, single-stream models perform better than dual-stream models and image-only models. And on the visual side, if one wants to improve understanding of emotion, one can look at art style-based features and also holistic features based on color and lighting. Thank you.
All right. I mean, this was a great collection of work, very diverse, very broad scope of topics. I would really be happy if folks who are on Zoom could turn their videos on and just give yourselves and others a round of applause for quite an impressive and sort of interesting type of work. If you're unable to show your video, that's understandable. But if you can, I think this will really create some experience, of a community. So unless you're in bed, you can't really turn the camera on, which is fine. Don't about that. So let me see how we proceed from here. Okay, my laptop is stuck from this present mode. All right. So we really wanted to have this live question answering session before we move on to the individual sort of poster setting, where sometimes folks don't get as much attention. Perhaps we do hope that there will be attendance there. But right now, I think we could use this opportunity to just internally at least exchange comments, questions, impressions from the work. And especially if you haven't seen this earlier, you could, ask other authors questions about their work. So I could maybe start to start this. The last work, the understanding of emotion from art. So is the task here? Do we have the author?
Yeah.
What I saw. Oh yeah, hi.
Hey.
Is the task actually to infer the emotions from image alone, or from image and the caption?
So yeah, we try to understand initially from images, and then we try to see can we exploit complementary information from the captions as well as the image. So we saw couple of cases out there where you can actually use both the information from the modalities. So it's more like a study on how we can use like either image and then like text as well, like just only text? And then can we use complementary information from both the modalities to predict emotions?
My intuition would be that text would be an extremely like straightforward cue here. Like it should be like the sentiment-based analysis has been there for a while now. So do you think that is the language only like pretty much doing most of the work here, or to what extent is image important?
So I could show only one example here, but there were like a couple of examples where like the caption was specifically like targeted to a person's expression, but that expression, if it is considered directly from the artwork itself, like from the image or like as a particular image region, that would help more in understanding that the emotion that is annotated for that image and the caption pair. So to answer your question, text is a very powerful signal here, what we found out. But like, for example, we also looked at art styles in general, like how art styles are kind of like useful for emotion understanding. So individual art styles could help in improving the current results that we have now. So, but yeah, this is more from understanding like how different regions are actually contributing to the emotion prediction.
Great, thank you. Let's see. Let's see first who is actually present. So we have some of the authors I recognize. So while I'm looking, maybe Marcus has a question. Go ahead.
Yeah, I mean, I highly encourage everyone to, all of the authors also to ask questions. Just raise their hand, and then Anya can maybe take the next person, and it can be more interactive, not just organizers asking questions. I think Emma, am I not correct? Denise, I think you did the Know It VQA.
Yes. Yes.
Can you say a bit how much important it is to understand? I think my understanding is you even have features across the entire episode. So how important did you find was it to understand really the entire episode for this versus maybe not more localized things?
The dataset actually 60% of question is knowledge base of question. Basically, dataset has several types of questions like visual, textual, knowledge, and temporal. So to be answered the knowledge based question, basically the understand of the whole episode or whole TV show is required. So in the sense of the dataset construction, textual part or episode knowledge is really important. So for example, I don't remember exactly, but I think 20% of question is visual type of question. Basically, you only need to look at what is happening in the video and the less of the question. So in this sense, yes, episode dialogue summary is really important for this dataset specifically. Yeah, is it mostly like we try to understand the long term of video that we should be able to extract information from the whole episode, basically.
Okay, cool. Thank you.
Andrew?
Yeah, I had a question for the same author actually. So I saw in the work you look at some of the questions will be asking for fine-grained details like the name of the robot, and then you will rely on this sort of summarization technique of dialogue, and hoping that will sort of bring in this far-reaching, long-range moments when it occurred. I'm wondering how you ensure that the summarization retains fine-grained details. That seems like the sort of thing that a summarization technique would get rid of.
Yes, so we didn't do specifically to understand because basically we don't know where is the answer actually from the episode. Basically what we did, we take each dialogue. So it's defined already in the dataset. It's around 20-second video. We have a subtitle on it. So we extract summaries from 20 seconds. And when we collect all the scenes, summaries, we obtain episode dialogue summary. In this sense, we think that we are capturing most of the information, but yeah, we might miss some of them. So yeah, we won't make sure. But normally, what of the previous work on it, they use like a plot summaries. It is basically human annotated sources from the internet. Basically, there are some fan page, people just watch the TV show and write the summaries. This type of summaries is like a really well written, but it is kind of short. But when we extract the episode dialogue summaries, it's quite longer. Then as far as we observe, we have more information than the pilot summary, even it's noisy. So yeah, we thought that we are capturing more information comparing to pilot summaries. I can say.
Great, thanks.
Welcome.
Great.
Okay, do we have questions from the audience? I had a question in the meanwhile to the authors of the work on the long tail recognition of visual relationships. So I guess we have two authors actually present, right? Sharif and Aniket. And so maybe I misunderstand something, but you are also proposing a new benchmark. And so it seems like you are using the existing benchmarks to kind of just focus on the long tail out of those data sets. But I thought that there is already some prior work which is explicitly like for visual genome, which basically would just focus on the long tail. So what is different about how you go about constructing your benchmark and that prior work, which sort of looked at the entire, data set kind of, so everything and the tail, but is it just the tail or like what's going on?
We basically we worked on two data sets, the visual genome and GQA. For visual genome, working on the whole data set was very challenging because the scale was very large. So we created a smaller, we picked a smaller version of it, and we chose the data in a way to be still long tail, but being more manageable than working on the entire visual genome. So yeah, basically it's built upon visual genome, or we chose it from visual genome, but it's focusing on the long tail while being feasible to work with instead of the whole visual genome dataset.
Okay, got it. I had a question, but I don't think the author is there. Do we have anybody from the work on conditional image generation? I don't think so. Nope. And anybody from the work on the egocentric biochemical dataset, Taichi? Imagine we are not in a good time zone for some of the authors. Feel free to jump again with any questions or comments.
Maybe I can jump in. I think it's Shyammal Buch. I don't know how to pronounce the name. You did this compositional work, right?
Yeah.
So I think before in the workshop today we talked a bit about how this would relate to robustness and grounding. Did you observe things that the compositional models were also grounded well, and do you find them being robust? Maybe it's to outliers or to new splits. I guess that's definitely the most compositional aspect of it, but maybe the grounding aspect especially.
Yeah. So we in our work we examined both synthetic settings and real world language settings, as in human generated language settings, and we showed some effectiveness in the paper of this framework on both generalizing in contexts where the training data set is in some sense adversarial, that you're specifically holding out certain compositions of things, and also learning about attributes and relationships and so on in a way that's generalizable even to zero-shot contexts, where you're generalizing to grounding for new objects, so from chairs to beds and lamps and so on, and with these compositional frameworks, and with specifically some of the edits that we propose with the newer framework NESS, we observe improved robustness and systematicity in these contexts.
Okay, great. And sort of how do you measure grounding? And if so, how do you measure grounding?
Well, we focus like our primary metrics for accuracy are largely on the accuracy of the entailment. That is the more traditional task of language is it selecting the right object, or is it saying the right output for the thing. The second task, which is a reference game, is a little bit more about grounding. And the reference game is set up in a way where you have 3 objects in context, and these objects are selected to be somewhat similar, and it's a reference game. So there's both a speaker and a listener, and both of them are provided the same set of objects but shuffled, so you can't just say the one on the left. And the speaker has to give some language description of, describing some sort of attributes or whatever of the target object. The other 2 objects are distractors, and then the listener has to determine based on this language which one what's the grounding to which of the 3 objects they're sort of referencing. So in this task, the accuracy is whether or not you've selected the correct object from the set of objects.
Okay, thanks.
A quick comment / shout out. Hi, John. nice to meet you from being stuck in multiple virtual events before. Nice that you guys used the data set, the news clippings data set. And do you have any comments or feedback actually about using the data set, and any issues or any things that you think are capturing like the realistic misinformation or not, actually what's missing maybe?
I think it's a really good test bed. I'm pretty happy with it, but maybe I'm biased because I've done decently with it. And real adversaries out there, they'll be doing really tricky things. But I think it's pretty close in that you have various manipulations with respect to people and places. And some of them are very hard, though. It's kind of hard to come up with automatically with a set that's, solvable, like reasonably solvable. But yeah, it's a good data set. And I was really interested in the VilHub work because I was using cross-domain similarity local scaling, and that's one of the approaches to sort of work with hubness, and so it'll be interesting to see how methods in bilingual lexicon induction can help or illuminate issues in visual grounding. So I'll definitely check that paper out.
Thank you.
I had a question for John as well, actually. Hey, John, can I just verify something with the paper? So do I understand correctly that you use clip embeddings for verifying identity between these sort of images and the representative images you find in Wikipedia and so on? Is that correct?
Yes.
Yeah, so I think that's a really interesting result because in some experimenting I'd done with clip, I'd seen that it retains information about certain identities. But it seems as though how it's trained, it should surely not be discriminative to such fine-grained details such as facial identity. Did you find that it worked better for very famous people? That's something that I've maybe seen before, because it's maybe seen lots of pictures of those people in its training set.
I couldn't say. I can't, and I'm actually a little terrified of trusting it as a method for identifying people. There's been some follow-on work where we've actually used a facial recognition model, at least the embeddings of one such model. And we have gains by using that with images. So that does tell me that something it's not quite as good, I guess. There's some complementary aspect to using embeddings from a ArcFace or something. So
Yeah, I've found myself that it can sort of classify Dwayne The Rock Johnson with sort of amazing confidence, but not faces it hasn't seen before. Yeah, great, thank you.
That goes back to the long tail issues.
Yep.
Oh, all right. So we are almost at the end of the Spotlight sort of Q&A session. Sorry if you didn't get to everyone. We'll continue the conversations now in the poster session. So just sharing the screen with you all just to show that you can find this Gatherly link right here. For some reason, the website links became inactive. Never mind that. So let's try and see what happens if we use this Gatherly, and I believe it should just take us to our. All right. To our Okay, this is the live demo. And looks good. So I guess we'll be seeing different rooms for different workshops. And then when you click on one, it takes you there. And what do you see now?
I think you have to go to elevator, select floor, and this is where you select it from.
The 8th floor.
Select.
Oh. Okay. Thank you. Okay, and so yeah, see you there. Thanks for joining the Spotlight session.
And I mean that also I think concludes the live stream of this workshop. Thanks everyone for joining. Thanks to all the invited speakers, and thanks for the poster presenters, and thank you, Anja, for guiding us through this last part, and thanks everyone else.
Thank you all. Thanks for participating. It was great. It was great having all the papers and all the discussions. Thank you. And I think for our live stream, I guess Mohammed will end that.
I think I cannot end it. I need to. Can you assign me as a host again?
Or whoever is a host can actually stop it. Andrew, I think you can just stop the live stream.